Dr. Charles Severance is one of the world's most popular software instructors, and he's the instructor for this C programming course. This course is a little different than some of our other courses. Dr. Chuck is going to take you through a classic and important book on C programming. You will occasionally have to pause the video to do some assignments to check your comprehension. It's going to be a challenge, but it will definitely be worth it if you want to have a deep understanding of the C programming language. And if you're completely new to programming, you may want to watch Dr. Chuck's Python for Everybody course first.
Welcome to C Programming for Everybody. My name is Charles Severance, and I'm your instructor for this course. This course and website is dedicated to learning the classic version of C programming language from the 1978 book, written by Brian W. Kernighan and Dennis M. Ritchie. This book places the reader in the middle of the 1970s transition from a hardware-centered computer science to a focus on writing portable and efficient software. C was used to develop operating systems like UNIX, MINIX, and Linux. Programming languages like Perl, Python, Java, and JavaScript and Ruby are all written in C. Software like early TCP/IP networking stack implementations that made the internet possible were written in C. And the first web browsers and web servers were written in C. Writing software in C enabled major advances in computer architecture and performance. Operating systems, compilers, and utilities could be recompiled to work on a new hardware platform once we had a C compiler for the new hardware. So much software has been written in C over the past 40 years that there's a very good chance that much of the software that you use every day was either written in C or written in a programming language that was written in C. So we study C less as a programming language to use on a daily basis and more as the foundation of modern software and computing. In many ways, C is the technology equivalent of the Rosetta Stone in that it provides a connection between the programming languages of the past and the programming languages of the present. The name CC4E in www.cc4e.com refers to the original Unix command cc, which was the command that you used to compile your C program. CC stood for C compiler, and it is featured on the first page of the first chapter of the KNRC book. Programmers like me from the 1970s and 1980s typed CC on Unix systems like the AT&T 3B2 to compile and run their first Hello World program in C. This material is being presented under fair use as we are making use of material from a copyrighted work that is out of print and not broadly available in any format. The book is also not available in any accessible format. We are making use of this material in a teaching and research context with a focus on studying its contribution to computing history. The material is available for free and online to anyone who wants to learn about the history of the C language, computing, and computer architecture. Welcome to the course. Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernigan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 0, Introduction. C is a general-purpose programming language. It has been closely associated with the Unix system since it was developed on that system, and since Unix and its software are written in C. The language, however, is not tied to any one operating system or machine, and although it has been called a system programming language because it is useful for writing operating systems, it has been used equally well to write major numerical, text processing, and database programs. C is a relatively low-level language. This characterization is not pejorative. It simply means that C deals with the same sort of objects that most computers do, namely characters, numbers, and addresses. These may be combined and moved about with the usual arithmetic and logical operators implemented by actual machines. C provides no operations to deal directly with composite objects such as character strings, sets, lists, or arrays considered as a whole. There is no analog, for example, of the PL1 operations which manipulate an entire array or string. The language does not define any storage allocation facility other than static definition and the stack discipline provided by the local variables of functions. There is no heap or garbage collection like that provided by Algol 68. Finally, C itself provides no input-output facilities. There are no read or write statements and no wired in-file access methods. All of these higher level mechanisms must be provided by explicitly called functions. I would note that the lack of a heap or garbage collection feature in C is both one of the great strengths of the language and at the same time is likely the reason that the average programmer will never develop or maintain a major C application during their career. C provides a simple feature using malloc and free functions that allow a programmer to request a certain amount of memory be allocated dynamically, use the memory, and then return the memory to the C runtime library for reuse. For example, to convert a JPEG image to a PNG image, our application will read the JPEG data into memory, then convert the image into a PNG image in memory, and then write the PNG data out to a file. We don't know how large the images will be in advance, so we request whatever size we need from C and then give it back when we're done. The term heap refers to the memory that C manages on our behalf when we need to borrow a bit of memory and give it back later. There are a couple of issues with a simple heap implementation. First, if we forget to call free when we are done with the memory, we have created a memory leak, and our program will eventually run out of memory and abort. C places the onus of giving back any dynamically allocated memory on the programmer. Modern languages like Java, JavaScript, and Python keep track of when we stop using dynamic memory, using a dynamic memory layer that can automatically reclaim the memory. The more difficult problem is after a series of calls to malloc and free, the heap space becomes fragmented and some cleanup is needed. This cleanup is called garbage collection. Efficient memory allocation and garbage collection has been the subject of decades of computer science research. The Java language has built a number of increasingly effective garbage collection approaches over the years. Kernigan and Ritchie, in one simple paragraph, define most of the problem as out of scope for the C language, which makes it a bit challenging for us to make good use of dynamic memory allocation in C. But when we do it properly, it performs very well. If you are currently using a language like Java, Python, or PHP, every time you create a new string through concatenation without thinking about memory allocation, remember to appreciate the decades of work by computer scientists that made it easy for you. Kernigan and Ritchie knew that garbage collection was difficult, so they left it out of the C language and put it into a runtime library. Back to Chapter 0. Similarly, C offers only straightforward single-thread control flow constructions, tests, loops, grouping, and subprograms, but not multiprogramming, parallel operations, synchronization, or coroutines. Though the absence of some of these features may seem like a grave deficiency. You mean I have to call a function to compare two character strings? Keeping the language down to modest dimensions has brought real benefits. Since C is relatively small, it can be described in a small space and learned quickly. A compiler for C can be simple and compact. Compilers are also easily written using current technology. One can expect to prepare a compiler for a new machine in a couple of months, and to find that 80% of the code of a new compiler is common with existing ones. This provides a high degree of language mobility. Because the data types and control structures provided by C are supported directly by most existing computers, the runtime library required to implement self-contained programs is tiny. On the PDP-11, for example, it contains only the routines to do 32-bit multiplication and division and to perform subroutine entry and exit sequences. Of course, each implementation provides a comprehensive, compatible library of functions to carry out input-output, string handling, and storage allocation operations. But since they are only called explicitly, they can be avoided if required, and they can also be written portably in C itself. Again, because the language reflects the capabilities of current computers, C programs tend to be efficient enough that there is no compulsion to write assembly language. Instead, the most obvious example of this is the UNIX operating system itself, which is written almost entirely in C. Of 13,000 lines of system code, only about 800 lines at the very lowest level are in assembler. In addition, essentially all of the UNIX application software is written in C. The vast majority of UNIX users, including one of the authors of this book, do not even know the PDP-11 assembly language. I would note that in this preface, the authors are carefully explaining the fact that many of the well-established programming languages of the 1960s and 1970s, like Fortran, COBOL, Pascal, ALGOL, and PL1, were solving many of the use cases that were needed by us programmers by adding syntax to the languages. The creators of C and UNIX were advocating for a more minimal set of programming language constructs and more reliance on calling function in provided runtime libraries to meet programmer use cases. It may have seemed a strange approach for experienced programmers in the 1980s, but over time it has allowed C to expand to meet a very wide range of programmer needs without requiring major revisions to the core language or compiler. Back to Chapter 0. Although C matches the capabilities of many computers, it is independent of any particular machine architecture, and so with a little care, it is easy to write portable programs, that is, programs which can be run without change on a variety of hardware. It is now routine in our environment that software developed on Unix is transported to local Honeywell, IBM, and Interdata systems. In fact, the C compilers and runtime support on these 4 machines are much more compatible than the supposedly ANSI standard versions of Fortran. The Unix operating system itself now runs on both the PDP-11 and the Interdata 832. Outside of programs which are necessarily somewhat machine-dependent, like the compiler, assembler, and debugger, software written in C is identical on both machines. Within the operating system itself, the 7,000 lines of code outside of the assembly language support and the I/O device handlers is about 95% identical. As a note, before Unix and C, if you were running the vendor operating system and writing in the best language for systems like the PDP-11 and Interdata 732, the user experience was completely different. Today we take for granted that we expect to be able to download the same application for Windows, Mac OS, or a Linux system. Even in the 1970s, those that were using Unix and C could write code once and move it between 2 hardware platforms and expect that it would work with no or relatively few changes. Back to Chapter 0. For programmers familiar with other languages, it may prove helpful to mention a few historical, technical, and philosophical aspects of C for contrast and comparison. Many of the most important ideas of C stem from the considerably older but still quite vital language BCPL, developed by Martin Richards. The influence of BCPL on C proceeded indirectly through the language B, which was written by Ken Thompson in 1970 for the first Unix system on the PDP-7. Although it shares several characteristic features with BCPL, C is in no sense a dialect of it. BCPL and B are typeless language. The only data type is the machine word, and access to other kinds of objects is by special operators or function calls. In C, the fundamental data objects are characters, integers of several sizes, and floating point numbers. In addition, there is a hierarchy of derived data types created with pointers, arrays, structures, unions, and functions. C provides the fundamental control constructions required for well-structured programs: statement grouping, decision-making with if, looping with termination test at the top using for and while, or at the bottom using do, and selecting one of a set of possible cases, switch. All of these were provided in BCPL as well, though with somewhat different syntax. That language anticipated the vogue for structured programming by several years. C provides pointers and the ability to do address arithmetic. The arguments to functions are passed by copying the value of an argument, and it is impossible for the called function to change the actual argument in the caller. When it is desired to achieve call by reference, a pointer may be passed explicitly, and the function may change the object to which the pointer points. Array names are passed as the location of the array origin, so array arguments are effectively call by reference. Any function can be called recursively, and its local variables are typically automatic, or created anew with each invocation. Function definitions may not be nested, but variables may be declared in a block-structured fashion. The functions of a C program may be compiled separately. Variables may be internal to a function, external, but known only within a single source file, or completely global. Internal variables may be automatic or static. Automatic variables may be placed in registers for increased efficiency, but the register declaration is only a hint to the compiler and does not refer to specific machine registers. C is not a strongly typed language in the sense of Pascal or Algo 68. It is relatively permissive about data conversion, although it will not automatically convert data types with the wild abandon of PL1. Existing compilers provide no runtime checking of array subscripts or argument types, etc. For those situations where strong type checking is desirable, a separate version of the compiler is used. This program is called lint, apparently because it picks up bits of fluff from one's program. Lint does not generate code, but instead applies a very strict check as to many aspects of the program as can be verified at compile and load time. It detects type mismatches, inconsistent argument use, unused or apparently uninitialized variables, potential portability difficulties, and the like. Programs which pass unscathed through lint enjoy, with few exceptions, freedom from type errors about as complete as do, for example, Algol 68 programs. We will mention other lint capabilities as the occasion arises. I would note that separately checking for things that might be wrong into the lint program keeps the C compiler simple and easy to port to a new computer. The lint program was naturally a very portable text processing application. While there's some overlap between a lint program and a compiler, over time there's quite distinct research and expertise in how to lint versus how to compile. Modern lint programs look at programs in far more detail than most compilers. Separating concerns of lint and the C compiler also allowed lint programs to use more memory and take more time to execute than compilers. Since the typical developer might use the compiler many times per day and run lint less often, it was nice for the compiler to run quickly and make light use of computer resources. We call this idea of building two smaller complementary programs that each specialize in one task separation of concerns, and it is an important principle in computer science. By keeping each component simple and focused, we can more easily build, test, and verify each component. UNIX and C showed the benefits of taking many small components approach to solve an overall set of problems. Back to Chapter 0. Finally, C, like any other language, has its blemishes. Some of the operators have the wrong precedence. Some of the syntax could be better. There are several versions of the language extant, differing in minor ways. Nonetheless, C has proven to be an extremely effective and expressive language for a wide variety of programming applications. The rest of this book is organized as follows. Chapter 1 is a tutorial introduction to the central part of C. The purpose is to get the reader started as quickly as possible, since we believe strongly that the only way to learn a new language is to write programs in it. This tutorial does assume a working knowledge of the basic elements of programming. There is no explanation of computers, of compilation, nor the meaning of an expression like n equals n plus 1. Although we have tried where possible to show useful programming techniques, the book is not intended to be a reference work on data structures and algorithms. When forced to make a choice, we have concentrated on the language. Chapters 2 through 6 discuss the various aspects of C in more detail and rather more formally than does Chapter 1, although the emphasis is still on working examples of complete, useful programs rather than isolated fragments. Chapter 2 deals with basic data types, operators, and expressions, and Chapter 3 treats control flow, if-else, while, for, etc. Chapter 4 covers functions and program structure, external variables, scope rules, and so on. Chapter 5 discusses pointers and address arithmetic, and Chapter 6 contains the details of structures and unions. Chapter 7 describes the standard C I/O library, which provides a common interface to the operating system. This I/O library is supported on all machines that support C, so programs which use it for input, output, and other system functions can be moved from one system to another, essentially without change. Chapter 8 describes the interface between C programs and the Unix operating system, concentrating on input-output, the file system, and portability. Although some of this chapter is Unix-specific, programmers who are not using a Unix system should still find useful material here. including some insight on how one version of the standard library is implemented and suggestions on achieving portable code. Appendix A contains the C reference manual. This is the official statement of the syntax and semantics of C, and, except for one owns compiler, the final arbiter of any ambiguities and omissions from earlier chapters. Since C is an evolving language that exists on a variety of systems, some of the material in this book may not correspond to the current state of developments for a particular system. We have tried to steer clear of such problems and warn of potential difficulties. When in doubt, however, we have chosen generally to describe the PDP-11 UNIX system, since that is the environment of the majority of C programmers. Appendix A also describes implementation differences on the major C systems. Chapter 1, a tutorial introduction. Let us begin with a quick introduction to C. Our aim is to show the essential elements of the language in real programs, but without getting bogged down in details, formal rules, and exceptions. At this point, we are not trying to be complete or even precise. We want you to get as quickly as possible to the point where you can write useful programs. And to do that, we have to concentrate on the basics: variables and constants, arithmetic, control flow, functions, and the rudiments of input and output. We are quite intentionally leaving out of this chapter features of C which are of vital importance for writing bigger programs. These include pointers, structures, and most of C's rich set of operators, several control flow statements, and a myriad of details. This approach has its drawbacks, of course. Most notable is that the complete story on any particular language feature is not found in a single place. The tutorial, by being brief, may also mislead. And because they cannot use the full power of C, the examples are not as concise and elegant as they might be. We have tried to minimize these effects, but be warned. Another drawback is that later chapters will necessarily repeat some of this chapter. In any case, experienced programmers should be able to extrapolate from the material in this chapter to their own programming needs. Beginners should supplement it by writing small, similar programs of their own. Both groups can use it as a framework on which to hang the more detailed descriptions that begin in Chapter 2. 1.1. Getting started. The only way to learn a new programming language is by writing programs in it. The first program to write is the same for all languages. Print the words, "Hello, world." This is the basic hurdle. To leap over it, you have to be able to create the program text somewhere, compile it successfully, load it, run it, and find out where your output went. With these mechanical details mastered, everything else is comparatively easy. In traditional C, the program to print "Hello World" is main, open parenthesis, close parenthesis, open curly brace, printf, parenthesis, double quote, hello, comma, space world, \n, double quote, close parenthesis, semicolon, close curly brace. The modern minimal version of this program needs a bit more syntax. We add a single line at the beginning. Hashtag include space left angle brackets stdio.h right angle bracket pound include stdio.h. We have to add that line for the modern program. Back to the book. Just how to run this program depends on the system that you're using. As a specific example, on the UNIX operating system, you must create the source program in a file whose name ends in .c, such as hello.c, and then you compile it with the command cc space hello.c. If you haven't botched anything, such as omitting a character or misspelling something, the compilation will proceed silently and make an executable file called a.out. Running that by the command a.out will produce hello, world as its output. On other systems, the rules will be different. Check with a local expert. On modern systems, we use the GCC compiler with the -ANSI option to accept the legacy syntax of C. So we use GCC space -ANSI space hello.c. And to run the resulting a.out file, you need to prepend the local directory because most shell configurations do not include the current path in the paths to search for applications. So you need to write /a.out. Now for some explanations about the program itself. A C program, whatever its size, consists of one or more functions which specify the actual computing operations that are to be done. C functions are similar to functions and subroutines of a Fortran program or the procedures of PL1, Pascal, etc. In our example, main is such a function. Normally, you are at liberty to give functions whatever names you like, but main is a special name. Your program begins executing at the beginning of main. This means every program must have a main somewhere. Main will usually invoke other functions to perform its job, some coming from the same program and others from libraries of previously written functions. One method of communicating data between functions is by arguments. The parentheses following the function names surround the argument list. Here, main is a function of no arguments, indicated by open parenthesis, close parenthesis. The curly braces enclose the statements that make up the function. They're analogous to the do end of PL1 or the begin end of Algol or Pascal and so on. A function is invoked by naming it, followed by a parenthesized list of arguments. There is no call statement as there is in Fortran or PL1. The parentheses must be present even if there are no arguments. In the above text, the authors were making connections to the popular general-purpose programming languages of the time. When the book was written, it was not all assured that C and C-like languages would ever evolve past writing high-performance applications like operating system kernels and device drivers. By comparing C to these more general-purpose languages, the authors are trying to plant the seed that C could have value as a general-purpose language. Back to the text. The line that says printf parenthesis double quote hello comma space world \n double quote close parenthesis semicolon is a function call, which calls a function named printf with the argument hello world. Printf is a library function which prints the output to the terminal unless some other destination is specified. In this case, it prints the string of characters that make up its argument. Any sequence of any number of characters enclosed in double quotes is called a character string or string constant. For the moment, our only use of the character strings will be as arguments to printf and other functions. The sequence \n in the string is C notation for the new line character, which when printed advances the terminal to the left margin on the next line. If you leave out the \n, a worthwhile experiment by the way, you'll find that your output is not terminated by a line feed. The only way to get a new line character into the printf's argument is with \n. If you try to break it into two lines, like printf quote hello world, and then just hit the return, double quote, close parenthesis, semicolon on a new line, the C compiler will print out unfriendly diagnostics about missing quotes. Printf never supplies a new line automatically, so multiple calls can be used to build up an output line in stages. Our first program could have just as well been written as main open parenthesis, close parenthesis, open curly brace, printf quote hello quote semicolon, printf quote world quote semicolon, printf \n semicolon, and then on a sixth line close curly brace, and it would have produced the identical output. Note that \n represents only a single character. An escape sequence like \n provides a general and extensible mechanism for representing hard to get or invisible characters. Among the others that C provides are \t for tab, \b for backspace, double quote for double quote, and \/ for the backslash itself. 1.2, page 8, variables and arithmetic. The next program prints the following table of Fahrenheit temperatures and their centigrade or Celsius equivalents. Using the formula, C equals parenthesis 5 divided by 9, close parenthesis, F minus 32. The table contains Fahrenheit of 0, Celsius of negative 17.8, Fahrenheit of 20, Celsius of negative 6.7, Fahrenheit of 40, Celsius of 4.4, and so forth. Here is the program itself. For reference, this program is on page 29 of the textbook. So it starts with pound include stdio.h to include the standard library. Then it has a comment that says print the Fahrenheit Celsius table for F equals 0, 20, 300. Close comment. Main, open parenthesis, close parenthesis, open curly brace, int, lower, upper, step, semicolon, float, var, Celsius, lower equals 0, semicolon, followed by a comment, upper equals 300, semicolon, followed by a comment, step equals 20, semicolon, followed by a comment, var equals lower, and then while, open parenthesis, var less than or equal to upper, close parenthesis, open curly brace, Celsius equals parenthesis 5.0 slash 9.0, close parenthesis, asterisk, open parenthesis, var minus 32.0, close parenthesis, semicolon. Then a printf statement, printf, open parenthesis, double quote, percent 4.0f space percent 6.1f backslash n, close quote, var, Celsius, close parenthesis, semicolon. Var equals var plus step, and then a closing curly brace to finish the while statement, and then a closing curly brace to finish the main statement. The first two lines, slash star print Fahrenheit to Celsius table for F equals 0, 20, 300, star slash are a comment, which in this case explains briefly what the program does. Any characters between slash star and star slash are ignored by the compiler. They may be used to freely make the program easier to understand. Comments may appear anywhere a blank or new line can. In C, all variables must be declared before use, usually at the beginning of a function, before any executable statements. If you forget a declaration, you will get a diagnostic from the compiler. A declaration consists of a type and a list of variables that have that type, as in int, lower, upper, step, semicolon, float, var, Celsius, semicolon. The type int implies that the variables listed are integers. Float stands for floating point, i.e., numbers which may have a fractional part. The precision of both int and float depends on the particular machine that you are using. On the PDP-11, for instance, an int is a 16-bit signed number. That is, one that lies between negative 32,768 and positive 32,767. A float number is a 32-bit quantity which amounts to about 7 significant digits, with a magnitude of about 10 to the minus 38 and 10 to the plus 38. Chapter 2 lists the sizes for other machines. I would note that the 1970s was a time of transition in the amount of memory installed in computers. The C language int type was 16 bits in the older but more generally available computers like the PDP-11. C could be used to write programs like the UNIX operating system that made efficient use of available memory. In particular, the 1978 version of C did not require that computers support 32-bit integers. But 32,768 is a pretty small number. The size of an integer affected the maximum size of arrays and strings. A lot of early C programs used the long type to get at least a 32-bit integer capable of representing numbers up to about 2 billion. In modern computers and databases, we tend to choose between 32-bit and 64-bit integers. Back to the text. C provides several other basic data types besides int and float. Char is a character, a single byte. Short is a short integer. Long is a long integer, and double is a double precision floating point. The size of these objects are also machine dependent, and details are in Chapter 2. There are also arrays, structures, and unions of these basic types, and pointers to them and functions that return them, all of which we will meet in due course. The actual computation in our temperature conversion program begins with the assignments lower equals 0, upper equals 300, step equals 20, far equals lower, all ending with semicolon. These set the variables to their starting values. Individual statements are terminated by semicolons. Each line of the table is computed in the same way, so we use a loop which repeats once per line. This is the purpose of the while statement. While, parenthesis, far less than or equal upper, close parenthesis, open curly brace, then the body of the loop, and then close curly brace. The condition in the parentheses is tested. If it is true, i.e. far is less than or equal to upper, the body of the loop, all of the statements included between the open curly brace and the closed curly brace are executed. Then the condition is retested. If true, the body is executed again. When the test becomes false, i.e. far exceeds upper, the loop ends and execution continues at the statement that follows the loop. There are no further statements in the program, so it terminates. The body of a while loop can be one or more statements enclosed in braces, as the temperature converter, or a single statement without braces, as in while, open parenthesis, I less than j, close parenthesis, I equals 2 times I, semicolon. In either case, the statements controlled by the while are indented by one tab stop, so you can see at a glance what statements are inside the loop. The indentation emphasizes the logical structure of the program. Although C is quite permissive about statement positioning, proper indentation and the use of white space are critical in making programs easy for people to read. We recommend writing only one statement per line and usually leaving blanks around operators. The position of the braces is less important. We have chosen one of the several popular styles. Pick a style that suits you and then use it consistently. I would add that with these words, the authors triggered a great debate about how to best indent code and use curly braces that continues to this day. The indentation style used in this book is often referred to as the K&R style. It tends to put open braces at the end of statements like if and while to keep code more compact in terms of the number of lines of code. The best advice is not to debate at all. When you modify someone else's code, just imitate the style that they used when they wrote their code. Back to the text. Most of the work gets done in the body of the loop. The Celsius temperature is computed and assigned to the Celsius variable by the statement Celsius equals, open parenthesis, 5.0 slash 9.0, close parenthesis, asterisk, open parenthesis, far minus 32.0, close parenthesis, semicolon. The reason for using 5.0 slash 9.0 instead of the simpler looking 5 slash 9 is that in C, as in many other languages, integer division truncates so that any fractional part is discarded. Thus, 5 slash 9 is 0. And of course, so would then all the temperatures be 0. A decimal point in a constant indicates that it is floating point, so that 5.0 over 9.0 is 0.555 repeating, which is what we want. We also wrote 32.0 instead of 32, even though since far is a float, 32 would automatically be converted to float before the subtraction. But as a matter of style, it's wise to write floating point constants with explicit decimal points, even when they have integral values. It emphasizes their floating point nature for human readers and ensures the compiler will see things the way you do as well. I would note that for those of you familiar with Python, before Python 3, integer division truncated and returned an integer, just like C. In Python 3, one of the major improvements was that the division of two integers performed the division operation in floating point and returns a floating point result. C and Python 2 made the choice because of efficiency. Integer division with truncation, especially for 16-bit numbers, was quite fast in the 1970s computers compared to floating point division that kept the fractional part intact. Early PDP-11 computers did integer division in hardware, while all floating point was done with loops and functions, so it was far slower. If you wanted to write fast code in the 1970s, you avoided floating point numbers except for special situations. Modern computers usually do 64-bit floating point operations almost at the same speed as integer division, so we don't need to allow programmers to avoid using floating point computations in their code. The detailed rules for when integers are converted to floating point are in Chapter 2. For now, notice that the assignment far equals lower semicolon and the test while far less than or equals upper both work as expected. The int is converted to a float before the operation is done. This example also shows a bit more of how printf works. Printf is actually a general-purpose format conversion function, which we will describe completely in Chapter 7. Its first argument is a string of characters to be printed, with each % sign indicating where one of the other, second, third, etc. arguments is to be substituted and what form it is to be printed in. For instance, in the statement, printf, parenthesis, double quote, %4.0f space %6.1f, \n, double quote, comma far, comma Celsius, the conversion specification %4.0f says that a floating point number is to be printed in a space at least 4 characters wide with no digits after the decimal point. %6.1f describes another number to occupy at least 6 spaces with 1 digit after the decimal point, analogous to the F6.1 of Fortran or the F parentheses 6, 1 of PL1. Parts of a specification may be omitted. %6f says that the number is to be at least 6 characters wide. %.2f requests 2 places after the decimal point, but the width is not constrained. And merely %f says to print the number itself as floating point. Printf also recognizes %d for decimal integers, %o for octal, %x for hexadecimal, and %c for characters, and %s for a character string, and % for the % itself. Each % construction in the first argument of printf is paired with its corresponding second, third, etc. argument. They must line up properly by number and type, or else you'll get meaningless answers. By the way, printf is not part of the C language. There is no input or output defined in C itself. There is nothing magic about printf. It's just a useful function, which is part of the standard library of routines that are normally accessible to C programs. In order to concentrate on C itself, we won't talk much about I/O until Chapter 7. In particular, we'll defer formatted input until then. If you have to input numbers, read the discussion of the function scanf in Chapter 7, Section 7.4. Scanf is much like printf, except that it reads input instead of writing output. The balance between building a feature into the language itself and providing it as a function in a library is something that computer language designers struggle with many years later. For example, in Python 2, print was a language element. In Python 3, one of the non-upwards compatible and somewhat unpopular changes was changing print to be a function. Many programmers feel that a print statement is a more elegant way to express printing, but from a compiler and language design perspective, a function call with a variable number of parameters is seen as technically more elegant and flexible. With Kernigan and Ritchie focused on keeping everything small and portable, they opted to keep all input-output functionality in libraries. The syntax is a little more complex, but given how computing has changed in the past 30 years, it is the right choice. Section 1.3, the for statement. As you might expect, there are plenty of different ways to write a program. Let's try a variation on the temperature converter. This is sample code is on page 11 of the textbook. # include less than stdio.h greater than. Main, open parenthesis, close parenthesis, open curly brace. Int var, that is FAHR, semicolon. For, open parenthesis, far equals 0, semicolon. Far less than or equal to 300, semicolon. Far equals far plus 20, close parenthesis. Printf, open parenthesis, double quote, %4d space %6.1f \n, close quote. Comma, far, comma, open parenthesis 5.0/9.0, close parenthesis, asterisk, open parenthesis, far minus 32, close parenthesis, semicolon. This code produces the same answers as the one before, but it certainly looks different. One major change is the elimination of most of the variables. Only far, F-A-H-R, remains as an int to show the %d conversion in printf. The lower and upper limits of the step size appear only as constants in the for statement itself. The for is a new construction, and the expression that computes the Celsius temperature now appears as the third argument of printf instead of in a separate assignment statement. This last change is an instance of a quite general rule in C. In any context where it is permissible to use the value of a variable of some type, you can use an expression of that type. Since the third argument of printf has to be a floating point value to match the %6.1f, any floating point expression can occur there. The for itself is a loop, a generalization of while. If you compare it to the earlier while, its operation should be clear. It contains three parts separated by semicolons. The first part, far equals 0, is done once, before the loop proper is entered. The second part is the test or condition that controls the loop, far less than or equal to 300. This condition is evaluated. If it is true, the body of a loop, in this case a single printf, is executed. Then the reinitialization step, far equals far plus 20, is done and the condition is reevaluated. The loop terminates when the condition becomes false. As with the while, the body of the loop can be a single statement or a group of statements enclosed in braces. The initialization and reinitialization parts can be any single expression. The choice between while and for is arbitrary and should be based on what seems clearer. The for is usually appropriate for loops in which the initialization and reinitialization are single statements and logically related, since it is more compact than while and keeps the loop control statements together in one place. I would note that the syntax of the for and while loop is a feature of C and derived C-like languages. In modern languages, we tend to have two kinds of loop structures, determinate and indeterminate. The for and the while loop structures in C are both indeterminate because you must read them closely to make sure they are properly constructed and, for example, are not unintentionally infinite loops. An example of a determinate loop is the for each loop in PHP or the for loop in Python. The semantics of both of these loops is to iterate all the elements in a collection. But since collections are never infinite, you can be assured that these determinate loops will not run forever. Section 1.4, Symbolic Constants. A final observation before we leave temperature conversion. It's a bad practice to bury magic numbers or magic constants like 320 or 320 in a program. They convey little information to someone who might read the program later, and they're hard to change in a systematic way. Fortunately, C provides a way to avoid such magic numbers. With the # define construction at the beginning of a program, we can define a symbolic name or symbolic constant to be a particular string of characters. Thereafter, the compiler will replace all unquoted occurrences of the name by the corresponding string. The replacement for the name can actually be any text at all. It's not related to numbers. So this is a sample code on page 13 of the text. # include less than stdio.h greater than. Next line. # define space lower space 0. Next line. # define space upper space 300. # define space step space 20. For these # statements, I would note that they have to start in the first column. The rest of this sample code is the code itself. Main open parenthesis, close parenthesis, open curly brace, int far, F-A-H-R, for open parenthesis, far equals uppercase lower, semicolon, far less than or equal to uppercase upper, semicolon, far equals far plus uppercase step. And then the same print statement. Printf, open parenthesis, double quote, %4d space %6.1f \n, quote, comma, far, comma, %5.0/9.0, close parenthesis, asterisk, open parenthesis, far -32, close parenthesis, semicolon, and then to end the program, close curly brace. The quantities, uppercase lower, uppercase upper, and uppercase step, are constants, so they do not appear in declarations. Symbolic names are commonly written in uppercase, so they can be readily distinguished from lowercase variable names. Notice that there is no semicolon at the end of a # define statement. Since the whole line after the defined name is substituted, there would be too many semicolons in the for. Section 1.5, a collection of useful programs. We are now going to consider a family of related programs for doing simple operations on character data. You will find that many programs are just expanded versions of the prototypes we discuss here. Character input and output. The standard library provides functions for reading and writing a character at a time. GetChar fetches the next input character each time it is called and returns the character as its value. That is, after C equals getChar, open parenthesis, close parenthesis, the variable C contains the next character of input. These characters normally come from the terminal or keyboard, but that need not concern us until Chapter 7. The function putChar, open parenthesis, C, close parenthesis, is the complement of getChar. PutChar, open parenthesis, C, close parenthesis, prints the content of the variable C on some output medium, again usually the terminal or screen. Calls to putChar and printf may be interleaved. The output will appear in the order in which the calls are made. As with printf, there is nothing special about getChar and putChar. They are not part of the C language, but they are universally available. Once again, I would note that the authors are making the case that the syntax of the language should not include syntax for input-output operations, but instead call library functions. Keeping the compiler small and easy to port new systems was important to the creators of C. And even if something like putChar was part of the language syntax, it would be translated at runtime to call a function. Programming languages from the 1960s tended to have a small set of use cases: read some input, run some calculation, and then write some output. So it seemed like a few language elements would be sufficient to describe all programs. But as programs started to make network connections, draw buttons on a screen, or respond to API calls over the network, it would have been difficult to keep expanding the core language syntax for each new use case. But it was extremely natural to add new libraries to languages like C with functions to call to accomplish these new use cases. File copying. Given getChar and putChar, you can write a surprising amount of useful code without knowing anything more about input-output. The simplest example is a program which copies its input to its output, one character at a time. In outline, here's what we do. Get a character. While the character is not the end-of-file signal, output the character we just read and then get a new character. Converting this into C gives us the sample code on page 14 of the textbook. Pound includes stdio.h, main open parenthesis, close parenthesis, open curly brace, int C, semicolon. C equals getchar, open parenthesis, close parenthesis, semicolon. While C not equal EOF, uppercase EOF, close parenthesis, open curly brace, put char C, C equals getchar, semicolon, close parenthesis, close curly brace. The relational operator, exclamation equals, means not equal to. The main problem is detecting the end of the input. By convention, getchar returns the value, which is not a valid character when it encounters the end of input. In this way, programs can detect when they did not get a character and they've actually simply run out of input. The only complication, which is a serious nuisance, is that there are two conventions in common use about what that end-of-file value really is. We have deferred this issue by using the symbolic name EOF, capital EOF, for the value, whatever it might be. In practice, EOF will be either -1 or 0, so the program must be preceded by the appropriate pound define EOF -1 or pound define EOF 0 to work properly. By using the symbolic constant EOF to represent the value that getchar returns when the end of file occurs, we are assured that only one thing in the program depends on the specific value, numeric value of EOF. I would note, most of that is incorrect. Modern C compilers actually define EOF in the stdio.h include file. So you never define EOF in your code. In modern C, the value of EOF is -1. You should just include stdio.h and use predefined EOF constant to check for end of file. The nuisance of different values for EOF was resolved shortly after 1978. Continuing with the text. We also declare C to be an int, not a char, so that it can hold the value which getchar returns. As we'll see in Chapter 2, the value is actually an int because it must be capable of representing end of file in addition to all possible characters. So the program for copying could actually be written more concisely by experienced C programmers. In C, any assignment, such as C equals getchar, open parenthesis, close parenthesis, can be used in an expression. Its value is simply the residual value being assigned to the left-hand side. If the assignment of a character to the variable C is put inside the test part of a while statement, the file copy program can be written as shown in the example code on page 15 of the textbook. Pound include stdio.h, main, open parenthesis, close parenthesis, open curly brace, int space C semicolon. While open parenthesis, C equals getchar, open parenthesis, close parenthesis, not equal EOF, close parenthesis, put char C, parenthesis, C, close parenthesis, semicolon, close curly brace. The program gets a character, assigns it to C, and then tests whether the character was the end-of-file signal. If it was not, the body of the while is executed, printing the character. The while then repeats. When the end of input is finally reached, the while terminates, and so does main. This version centralizes the input. There is now only one call to getchar and shrinks the program. Nesting an assignment is a test of one of the places where C permits a valuable conciseness. It is possible to get carried away and create impenetrable code, though that is a tendency we will try to curb. It's important to recognize that the parentheses around the assignment within the conditional are really necessary. The precedence of exclamation equal, not equals, is higher than that of equals, the assignment operator, which means that in absence of parentheses, the relational test, exclamation equals, would be done before the assignment equals. So the statement C equals getchar, parenthesis, open parenthesis, close parenthesis, not equal EOF is equivalent to C equals get char is equivalent to C equals open parenthesis get char open parenthesis close parenthesis not equal EOF close parenthesis. This has the undesired effect of setting. It is important to recognize that the parentheses around the assignment within the conditional are really necessary. The precedence of exclamation equals is higher than that of equals, which means that in the absence of parentheses, the relational test not equals would be done before the assignment. So the statement C equals get char not equal EOF is equivalent to C equals open parenthesis get char not equal EOF close parenthesis. This has the undesired effect of setting C to 0 or 1 depending on whether or not the call of getChar encountered the end of file. More on this in Chapter 2. The next program counts characters. It is a small elaboration of the copy program. This sample code is on page 16 of the textbook. Pound include stdio.h, main, open parenthesis, close parenthesis, open curly brace, long, nc semicolon, nc equals 0 semicolon, while open parenthesis get char open parenthesis close parenthesis exclamation equal EOF plus plus nc semicolon printf double quote %ld backslash n double quote comma nc parenthesis semicolon close curly brace. The statement plus plus nc semicolon shows a new operator plus plus, which means increment by 1. You could write nc equals nc plus 1, but plus plus nc is more concise and often more efficient. There is a corresponding operator, minus minus, to decrement by 1. The operators plus plus and minus minus can either be prefix operators, plus plus nc, or postfix, nc plus plus. These two forms have different values and expressions, as will be shown in Chapter 2. But plus plus nc and nc plus plus both increment nc. For the moment, we'll stick to the prefix form. The character counting program accumulates its count in a long variable instead of an int. On a PDP-11, the maximum value of an int is 32,767, and it would take relatively little input to overflow that counter if it were declared as an int. In Honeywell and IBM C, long and int are synonymous and much larger. The conversion specification %ld signals to printf that the corresponding argument is a long integer. We again see another reference to the fact that the number of bits of the int type is in transition in 1978. The older PDP-11 used a 16-bit integer to save limited memory on a small, almost obsolete computer, while later computers from IBM and Honeywell have already switched to their int type to be 32 bits. This allowed code originally written for the PDP-11, like UNIX or even the C compiler, to be recompiled on the IBM or Honeywell with very few changes. To cope with bigger numbers, you can use a double, which is a double-length float. We will also use a for statement instead of a while to illustrate an alternate way to write a while loop. This code is the second sample code on page 16 of the textbook. Pound include stdio.h, main open parenthesis close parenthesis open curly brace, double nc semicolon. For open parenthesis nc equals 0 semicolon, getchar open parenthesis close parenthesis not equal EOF semicolon plus plus nc close parenthesis, and then a semicolon. The semicolon in this case is an empty statement because there's nothing in the body of the for loop. And at the end we say printf double quote %.0f backslash n double quote comma nc close parenthesis semicolon close curly bracket. Printf uses %f for both float and double. %.0f suppresses printing of the non-existent fraction part. The body of the for loop here is empty because all the work is done in the test and reinitialization parts of the for loop. But the grammatical rules of C require that a for statement have a body. The isolated semicolon, technically a null statement, is there to satisfy that syntax requirement. We put it on a separate line to make it more visible. Before we leave the character counting program, observe that if the input contains no characters, the while or for test fails on the very first call to getChar, so that the loop program produces 0, the right answer. This is an important observation. One of the nice things about while and for is they are tested at the top of the loop before proceeding with the body. If there is nothing to do, nothing is done, even if that means never going through the loop body. Programs should act intelligently when handed input like no characters. The while and the for statements help ensure that they do reasonable things with boundary conditions. Line counting. The next program counts lines in its input. Input lines are assumed to be terminated by the new line character \n that has been carefully appended to every line written out. This is sample code on line 17 of the textbook. Pound includes stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int C, NL, semicolon. NL equals 0, semicolon. While, open parenthesis, C equals getChar, open parenthesis, close parenthesis, not equal EOF, close parenthesis. If, open parenthesis, C, double equals, single quote, \n, single quote, close parenthesis, plus, NL, semicolon. Printf, double quote, %d, \n, double quote, comma, NL, close parenthesis, semicolon, close curly brace. The body of the while loop now consists of an if, which in turn controls the increment ++NL. The if statement tests its parenthesized condition, and if true, does the statement or group of statements inside braces that follow. We have again indented to show what is controlled by what. The double equal sign is the C notation for is equal to, like fortrans.eq. This symbol is used to distinguish the equality test, the question being asked, from the single equal sign used for assignment. Since assignment is about twice as frequently used as equality testing in typical C programs, it's appropriate that the operator be half as long. A single character can be written between single quotes to produce a value equal to the numerical value of the character in the machine's character set. This is called a character constant. So for example, single quote A single quote is a character constant. In the ASCII character set, its value is 65, the internal representation of the character A. Of course, single quote A single quote is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. These escape sequences that are used in character strings are also legal and character constants. So in tests and arithmetic expressions, single quote \n single quote stands for the value of a new line character. You should note carefully that single quote \n is a single character, and in expressions is equivalent to a single integer. On the other hand, double quote \n double quote is a character string which happens to contain only one character. The topics of strings versus characters is discussed further in Chapter 2. The numeric values that are shown for characters are using the ASCII character set. The character sets in the 1970s were quite intricate. Most were 8 bits long to conserve computer memory and only support 100 or so Latin-like characters. This is why early programming languages use special characters like asterisk and curly brace in their syntax very carefully. They needed to choose characters that were commonly available on computer keyboards from different manufacturers. Modern programming languages like Python 3 and Ruby store internal string values using the Unicode character set, so they are all able to represent all the characters in all languages around the world. Modern languages tend to represent 8-bit values in the range from 0 to 256 using a byte or similar type. Python 2 strings were stored as 8-bit bytes and Python 3 strings are stored as 32-bit Unicode characters. Moving to Unicode was a major effort in the Python 2 to Python 3 transition. Word counting. The fourth in our series of useful programs counts lines, words, and characters, with a loose definition that a word is any sequence of characters that does not contain a blank, a tab, or a new line. This is a very bare bones version of the UNIX utility WC. This example is on page 18 in the textbook. Pound include stdio.h. Pound define yes, 1. Pound define no, 0. Main, open parenthesis, close parenthesis, open curly brace. Int c, nl, nw, nc, inword. Inword equals no. nl equals nw equals nc equals 0. While, open parenthesis, c equals getchar, not equal to EOF, open curly brace, plus plus nc. If, parenthesis, c double equals, quote, backslash n, quote, parenthesis, plus plus nl. If, open parenthesis, c double equals, single quote, space, single quote, double vertical bar, c double equals, single quote, backslash n, single quote, double vertical bar, c equals, single quote, backslash t, single quote, close parenthesis, inward equals no. Else if, open parenthesis, inward equal no, close parenthesis, open curly brace, inward equals yes, semicolon, plus plus nw, semicolon, close curly brace, printf, open parenthesis, double quote, %d, space, %d, space, %d, backslash n, double quote, comma, nl, comma, nw, comma, nc, close, curly brace. Every time the program encounters the first character of a word, it counts it. The variable inward records whether the program is currently in a word or not. Initially, it is not in a word, which is assigned the value no. We prefer the symbolic constants yes and no to the literal values 1 and 0 because they make the program more readable. Of course, in a program as tiny as this, it makes little difference, but in larger programs, the increase of clarity is well worth the modest effort to write it this way, to make it more readable. You will also find that it's easier to make changes to programs where numbers appear only as symbolic constants. The line NL equals NW equals NC equals 0 sets all three variables to 0. This is not a special case, but a consequence of the fact that an assignment has a value and assignments associate right to left. It's really as if we had written NC equals open parenthesis NL equals open parenthesis NW equals 0 close parenthesis, semicolon. The operator double vertical bar means or. So the line if open parenthesis C double equals single quote space single quote vertical bar C double equals single quote backslash N single quote double vertical bar C double equals quote backslash T quote parenthesis says if C is a blank, or C is a new line, or C is a tab. The escape sequence backslash T is a visible representation of the tab character. There's a corresponding operator, which is double ampersand for AND. Expressions connected by double ampersand or double vertical bar are evaluated left to right, and it is guaranteed that the evaluation will stop as soon as the truth or falsehood for the overall expression is known. Thus, if C contains a blank, there is no need to test whether it contains a new line or tab. So these tests are not made. This isn't particularly important here, but is very significant in more complicated situations, as we will soon see. I would note that the double vertical bar and double ampersand are the norm for Boolean operators in C-like languages. When a new language was being designed, it was really easy to just adopt the C convention for logical operators because, while they may seem cryptic, millions of software developers were already familiar with the operators. In this way, the relationship between C and C-like languages is like the relationship between Latin and Romance languages, including English. Back to the text. The example also shows the C else statement, which specifies an alternative action to be done if the condition part of an if statement is false. The general form is if, open parenthesis, expression, close parenthesis, statement 1, else statement 2. One and only one of the two statements associated with an if then else is done. If the expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can actually be, in fact, quite complicated. In the word count problem, the one after the else is an if that controls two statements in braces. Section 1.6, Arrays. Understanding the capabilities and limitations of C arrays is one of the most important topics in our historical look at the C programming language. Most importantly, the number of elements in an array declaration must be a constant at compile time, and the size of an array cannot be adjusted using an array declaration while the program's running. This inability to automatically resize C arrays as data is added leads to a class of security flaws that are generally referred to as buffer overflow, where a program reads more data in that can fit into an array and is tricked to overriding other data or code and compromising an application. Later in this book, we will create dynamic array-like structures in C using pointers and the standard library calloc function. Python has support for non-dynamic arrays, buffers. Python buffers are generally not used except for programmers writing library code that talks to low-level code written in a language other than Python, or talking to operating system things like Linux. The more commonly used Python list and dictionary structures can change their sizes automatically as elements are added and deleted at runtime. Java has support for non-dynamic arrays like C, which are given a length at the moment they are created, and the array length cannot be increased nor decreased without making a new array and copying all the elements from the first to the second array. Java does provide list and map structures that automatically adjust their length as data is added or removed. Java has a class called ArrayList, which can be dynamically extended but provides array-like linear access. It is a list internally, but it can be used like an array externally. The underlying technique that is used to implement language structures like Python's list is dynamic memory allocation and a linked list structure. Linked lists are one of the most important data structures in all of computer science. We will cover dynamic allocation and implementing data structures in C in Chapter 6. For now, we will merely examine the syntax of C arrays, but keep in mind that allocating an array in C is very different than creating a list in Python. Back to the text. Let us write a program to count the number of occurrences of each digit of white space characters, blank tab and new line, and all other characters. This is an artificial problem to solve, but it permits us to illustrate several aspects of C in one program. There are 12 categories of input, so it is convenient to use an array to hold the number of occurrences of each digit rather than 10 individual variables. Actually 12 individual variables. Here is one version of the program on page 21 in the textbook. And I would note that as these programs get larger and larger, it is harder and harder for you to just listen to me read them, and you have to go look at them in the textbook. So I recommend that you go check out the textbook in page 20 and find this actual code. Pound include stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int C, comma I, comma n white, comma n other, semicolon. Int n digit, open square bracket 10, close square bracket, semicolon. n white equals n other equals 0, semicolon. 4, open parenthesis, I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis, n digit, open square bracket, I, close square bracket, equals 0, semicolon. Now we're going to have a loop to read all of our input, while double open parentheses, C equals getChar, open parenthesis, close parenthesis, and another close parenthesis, not equal EOF, close parenthesis. If, open parenthesis, C greater than or equal to, single quote, 0, single quote, double ampersand, C less than or equal, single quote, 9, single quote, close parenthesis, plus plus, n digit, open square bracket, C minus single quote 0, single quote, close square bracket, semicolon. Else if, open parenthesis, C double equals space, quote, space, quote, or double vertical bar, C double equals single quote backslash n single quote, double vertical bar, C double equals single quote backslash T single quote, close parenthesis, plus plus n white, semicolon, else plus plus n other. That if statement was a sort of a 3-branch if, checking to see if we were doing a digit, a white space character, or some other character. At the end of the while loop, or not the end of the while loop, and so we say printf, parenthesis, double quote, digits equals, double quote, close parenthesis, semicolon. Now we'll note in this that there is no new line. So we can have these printfs kind of concatenate outward without going to a separate line. 4, parenthesis, I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis. Printf, double quote, space, %d, double quote, comma, n digit, open square bracket, I, close square bracket, close parenthesis, semicolon. Printf, open parenthesis, double quote, backslash n, white space equals, %d, comma, other equals, %d, backslash n, double quote, comma, n white, comma, n other, close parenthesis, semicolon, close curly brace. Let's go through the code. The declaration int, n digit, open square bracket, 10, close square bracket, semicolon, declares n digit to be an array of 10 integers. Array of subscripts always start as 0 in C rather than 1 as in Fortran or PL1, so the elements are n digit sub 0, n digit sub 1, dot dot dot, n digit sub 9. Square brackets are the sub. This is reflected in the for loops, which initialize and print the array. A subscript can be any integer expression, which of course includes integer variables like I and integer constants. This particular program relies heavily on the properties of character representation of the digits. For example, if C greater than or equal to single quote 0, single quote, double ampersand, C less than or equal to single quote 9, single quote, close parenthesis, determines whether it's a digit. That is, if the numeric value of the digit and the numeric value of the digit is C minus double quote 0, double quote. This only works if double quote 0, double quote 1, etc. are positive and increasing order. And there's nothing but digits between 0 and 9. Fortunately, this is true for all conventional character sets. By definition, arithmetic involving chars and ints converts everything to int before proceeding. So char variables and constants are essentially identical to ints in arithmetic contexts. This is quite natural and convenient. For example, C minus single quote 0, single quote is an integer expression that gives us a value between 0 and 9, an integer value between 0 and 9, corresponding to the character quote 0 quote 2 quote 9 quote stored in C, and is thus a valid subscript for the 10-element array n digit. The decision as to whether the character is a digit, a white space, or something else is made by the sequence if, open parentheses, C greater than or equal to, quote 0 quote, double ampersand, C less than or equal, quote 0 quote, quote 9 quote, close parenthesis, plus plus n digit, open square bracket, c minus quote 0 quote, close bracket, semicolon. Else if c double equals single quote, or c double equals single quote backslash n, or c double equals single quote backslash t. Plus plus n white, else plus plus n other. The pattern, if in parentheses condition statement, else if parentheses condition statement, else statement, occurs frequently in programs as a way to express a multi-way decision. The code is simply read from the top of the until the bottom, until some condition is satisfied. At that point, the corresponding statement part is executed and the entire construction is finished. Of course, statement can be several statements enclosed in braces. If none of the conditions are satisfied, the statement after the final else is executed, if present. If the final else and statement are omitted, as in the word count program, no action takes place. There can be an arbitrary number of else if condition statements, groups between the initial if and the final else. As a matter of style, it is advisable to format this construction, as we have shown, with proper indentation, so that long decisions do not march off the right side of the page. The switch statement, to be discussed in Chapter 3, provides another way to write multi-way branching that is particularly suitable when the condition being tested is simply whether some integer or character expression matches one of a set of constants. For contrast, we will present a switch version of this program in Chapter 3. Functions. In C, a function is equivalent to a subroutine or function in Fortran, or a procedure in PL1, Pascal, etc. A function provides a convenient way to encapsulate some computation in a black box, which can then be used without worrying about its innards. Functions are really the only way to cope with the potential complexity of large programs. With properly designed functions, it is possible to ignore how a job gets done. Knowing what is done is sufficient. C is designed to make the use of functions easy, convenient, and efficient. You will often see a function only a few lines long called only once, just because it clarifies some piece of code. So far, we have used functions like printf, getChar, and putChar that have been provided for us. Now it's time to write a few of our own. Since C has no exponentiation operator like the double asterisk of Fortran or PL1, let us illustrate the mechanics of function definition by writing a function power, open parenthesis, m, comma, n, close parenthesis, to raise an integer into a positive power n. That is, the value of power, parenthesis 2, comma 5, is 32. This function certainly doesn't do the whole job of exponentiation, since it only handles positive powers of small integers, but it is best to confuse only one issue at a time. Here is the function power and a main program to exercise it so you can see the whole structure at once. This sample code is on page 23 of the textbook. Pound include stdio.h. Main, open curly brace, int I, semicolon. For parenthesis I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis. Printf, double quote, %d space, %d space, %d backslash n, double quote, comma. I, comma, power, open parenthesis 2, comma I, close parenthesis, comma, power, open parenthesis, -3, comma I, close parenthesis, semicolon, close curly brace, the end of the main. Now we begin the function. Power, open parenthesis, x, comma, n, close parenthesis. Int, x, comma, n, semicolon, open curly brace. Int, I, comma, p. P equals 1. For, open parenthesis, I equals 1, semicolon, I less than or equal to n, semicolon, plus plus I. P equals p times x, semicolon. Return, open parenthesis, p, close parenthesis, semicolon, close curly brace. Each function has the same form. Function name, open parenthesis, argument list, if any, followed by argument declarations, if any, followed by the body of the function, which includes declarations and statements. The functions can appear in either order and in one source file or two. If, of course, the source file appears in two files, you will have to say more to compile and load it than if all appears in one. But that's an operating system matter, not a language attribute. For the moment, we'll just assume that both functions are in the same file, so whatever you learned about C programs, running them will not change. The function power is called twice in the line printf, open parenthesis, double quote, %d space %d space %d \n, double quote, comma I, comma power, open parenthesis, 2 comma I, close parenthesis, comma power, open parenthesis, -3, comma I, close parenthesis, close parenthesis. Each call passes two arguments to the power function, which each time returns an integer to be formatted and printed. In the expression, power, open parenthesis, 2 comma I, is just an integer as 2 and I are. Not all functions produce an integer value, and we'll take this up in more detail in Chapter 4. In power, the arguments have to be declared appropriately so their types are known before the beginning of the body of the function. This is done by the line int x, n, semicolon that follows the function name. The argument declarations go between the argument list and the opening left brace. Each declaration is terminated by a semicolon. The names used for power and for its arguments are purely local to power and not accessible to any other functions. Other routines can use the same names for their variables without conflict. This is also true of the variables I and p within the function. The I in power is unrelated to the I in main. The value that power computes is returned to main by the return statement, which is just as in PL1. Any expression must occur within the parentheses. A function need not return a value. A return statement with no expression causes control, but no useful value to be returned to the caller, as does falling off the end of a function by reaching the terminating right curly brace. Section 1.8, Arguments, Call by Value. One aspect of C function, which may be unfamiliar to programmers who are used to other languages, particularly Fortran and PL1, in C, all function arguments are passed by value. This means that the called function is given the values of its arguments in temporary variables, actually on a stack, rather than their addresses. This leads to some different properties than are seen with call by reference languages like Fortran and PL1, in which the called routine has handled the address of the argument, not its value. It may seem strange that the authors are calling so much attention to the fact that function arguments are passed call by value in the very first chapter. Most modern programming languages like Python, PHP, or Java pass single value arguments by value by default. And to pass in an argument by reference, you need to do something special, like adding the ampersand in the function declaration in PHP. Passing by reference was the norm before C, and passing by value was the norm after C. Since modern languages were deeply influenced by and often written in C, passing by value is the norm for modern languages. It's nice because it isolates the data in the calling code from the called code. So the called code can't easily mess with its arguments, either intentionally or by mistake, and create an unexpected side effect and possibly a bug or security flaw in the calling code. It was a bit of work to make pass by value work in C. C implements a call stack where a bit of memory is automatically allocated at each function call, and C makes a copy of the values in the calling code to pass them into the called code in a way that the calling code can see the values and change their local copies without affecting the values in the calling code. The same call stack that made it possible for C function arguments to be passed by value also made it possible for a function to call itself recursively. Fortran functions could not be called recursively until the 1990 version of Fortran. If you know your Python, you know that simple variables like integers and strings are passed by value, while structured data like dictionaries and lists are passed by reference, i.e., the called function can modify its arguments. We will later see this in C as well. Talking about call stacks, recursive functions, and the fact that arrays and structures are called by reference is jumping ahead somewhat. So for now, let's just remember the author's point that normal values like integers and floats are passed by value in C. Back to the text. The main distinction is that in C, the called function cannot alter a variable in the calling function. It can only alter its private temporary copy. Call by value is an asset, however, not a liability. It usually leads to more compact programs with fewer extraneous variables, because arguments can be treated as conveniently initialized local variables in the called routine. For example, here is a version of power which makes use of this fact. This code is on page 24 of the text. Power, open parenthesis, x, comma, n, close parenthesis. Int, x, comma, n, semicolon, open curly brace. Int, I, comma, p, semicolon. For, open parenthesis, p equals 1 semicolon, n greater than 0 semicolon, minus minus n, close parenthesis, p equals p times x, semicolon, return, open parenthesis, p, close parenthesis, semicolon, close curly brace. The argument n is used as a temporary variable and is counted down until it becomes 0. There is no longer a need for the variable I, as in the previous example. Whatever is done to n inside the power function has no effect on the argument that power was originally called with. When necessary, it is possible to arrange for a function to modify the variable in the calling routine. The caller must provide the address of their variable to be set, technically a pointer to the variable, and the called function must declare the argument to be a pointer and reference the actual variable indirectly through it. We will cover this in detail in Chapter 5. When the name of an array is used as an argument, the value passed to the function is actually the location or address of the beginning of the array. There is no copying of the elements in the array. By subscripting this value, the function can access and alter any element of the array in the calling code. This is the topic of the next section. Now, I would recommend that you're careful looking at the code samples in the rest of this chapter. Recall that in C, array sizes do not grow and shrink dynamically at all after they're allocated. The authors statically allocate character arrays capable of handling up to 1,000 characters long. Their code works, but it is somewhat brittle. So look at the next two sections as examples of C syntax with many important concepts about character strings stored as arrays and calling patterns when passing arrays to functions as parameters, but not exactly the best practice when handling dynamically sized data. Back to the text. Probably the most common type of array in C is an array of characters. To illustrate the use of character arrays and functions to manipulate them, let's write a program that reads a set of lines and prints the longest. The basic outline is simple enough. While there's another line, if it's longer than the previous longest, save it and its length, and then at the very end, print the longest line. The outline makes it clear that the program divides naturally into pieces. One piece gets a new line, another checks it, another saves it, and then the rest controls the process. Since things divide so nicely, it would be well to write them that way too. Accordingly, let's write first a separate function called getLine to fetch the next line of input. This is a generalization of getChar. To make the function useful in other contexts, we'll try to make it as flexible as possible. At the minimum, getLine has to return a signal about possible end of file. A more generally useful design would be to return the length of the line, or 0 if the end of file is encountered. 0 is never a valid line length since every line has at least one character. Even a line containing only a new line has length 1. I would note that here in Chapter 1, we have changed the book's original use of the function named getLine to get_line in the code examples because it conflicts with the stdio.h that defines getLine as a library function. In this chapter, the authors are providing examples around function naming and linking In later chapters, code samples will simply use the built-in get line without an underscore to read an input. When we find a line that is longer than the previous longest, it must be saved somewhere. This suggests a second function, copy, to copy the new line to a saved place. Finally, we need a main program to control getLine and copy. Here is the result. The sample code for this is on page 26. And it's a bit long, so you might want to take a look at the sample code in a browser. Pound include stdio.h. Pound define max line 1000. Main, open paren and close paren, open curly brace, int len semicolon, which is the current line length, int max semicolon, which is the maximum length we've seen so far, char line, open square bracket, max line, close square bracket, semicolon. A character array, that's the current input line, and then char save, open square bracket, max line, close square bracket, semicolon, which is a character array that has the longest line where we're going to save it. Onto the code. Max equals 0. While open parenthesis, len equals get line, open parenthesis, line, comma, max line, close parenthesis, greater than 0. If len is greater than max, open curly brace, max equals len to save it, and then copy line, comma, save, close curly brace. If open parenthesis, max greater than 0, i.e. there was a line, printf, open parenthesis, double quote, %s, double quote, comma, save, close curly brace to end the main program. Now we're in the first function. GetLine, open parenthesis, s, comma, lim, close parenthesis. Char, s, open bracket, close bracket, semicolon. Since it's being passed in as an argument, we don't need to know the length of it. And the next argument is int lim semicolon. So getLine takes a character array of unknown length and a limit that tells us the length of the character array. Open curly brace, int c comma I semicolon. 4, open parenthesis, I equals 0 semicolon. I less than lim minus 1, double ampersand, parenthesis, c equals get char, open parenthesis, close parenthesis, not equal EOF, and, double ampersand, c not equal, single quote, backslash n, single quote, semicolon, plus I. And in the body of the loop, it's s, open square bracket, I, close square bracket, equals c. From now on, I'll read that s sub I equals c. At the end of the loop, we say if, open parenthesis, c double equals, single quote, backslash n, single quote, close parenthesis, open curly brace, s sub I equals c plus I, close curly brace. S sub I equals, quote, backslash 0, quote, semicolon, return, open parenthesis, I, close parenthesis, semicolon, close curly brace. And that's the end of the getLine function. And now we're on to the copy function. Copy, open parenthesis, S1, S2, close parenthesis. The purpose of this function is to copy S1 to S2, assume that S2 is big enough. The declaration is char S1, open square bracket, close square bracket, comma, S2, open square bracket, close square bracket. As a note, these arrays have a size. We just don't know what they are, and we hope that they're large enough. The body of the copy function starts with open curly brace, int I semicolon, I equals 0, while open parenthesis, S2 sub I equals S1 sub I, close parenthesis, not equal, single quote, backslash 0, single quote, plus I. close curly brace to end the copy function. Main and getLine communicate both through a pair of arguments and a returned value. In getLine, the arguments are declared by the lines char s open square bracket close square bracket semicolon int lim semicolon, which specify that the first argument is an array of unknown length and the second is an integer. The length of the array s is not specified in getLine since it's determined in main. getLine uses return to send a value back to the caller, just as the function power did. Some functions return a useful value. Others, like copy, are only used for their effect and return no value. getLine puts the character \0, the null character whose integer value is 0, at the end of the array it's creating to mark the end of the string of characters. This convention is also used by the C compiler. When a string constant like double quote HELLO \n double quote is written in a C program, the compiler creates an array of characters containing the characters of the string and adds a \0 at the end to terminate it so that functions such as printf can detect the end. So that would lead to an array that has HELLO \n\0. So it's a 5-character array with a new line, which is a 6th character, and then \0, which is an actual character. Again, we don't know, the arrays don't know their length, and so you use the \0 as the indicator of the end of a string. The %s format specification in printf expects a string represented in exactly this form. If you examine copy, you will discover that it too relies on the fact that its input argument s1 is terminated by \0, and it copies this character, \0, into the output argument s2. All of this implies that \0 is not part of normal text. It's merely a marker. It is worth mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its limit? getLine works properly in that it stops collecting when the array is full, even if no new line has been seen. By testing the length in the last character returned, main can determine whether the line was too long, then cope with it as it wishes. In the interests of brevity, we have ignored this issue. There is also no way for a user of getLine function to know in advance how long an input line might be, so getLine checks for overflow. On the other hand, a user of the copy function already knows or should be able to find out how big the strings are, so we have chosen not to add error checking to it. Section 1.10, Scope, External Variables. The variables in main, line, save, etc. are private or local to main. Because they are declared within main, no other function can have direct access to them. The same is true of the variables in the other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a routine comes into existence only when a function is called and disappears when the function is exited. It is for this reason that such variables are usually known as automatic variables, following terminology in other languages. We'll use the term automatic henceforth to refer to these dynamic local variables. Chapter 4 discusses the static storage class in which local variables do retain their values between function invocations. Because automatic variables come and go with function invocation, they do not retain their values from one call to the next and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables which are external to all functions, that is, global variables which can be accessed by name by any function that cares to. This function is rather like Fortran common or PL1 external, Because external variables are globally accessible, they can be used instead of arguments to communicate data between functions. Furthermore, because external variables remain in existence permanently rather than appearing and disappearing as functions are called and exited, they retain their values even after the functions that set them are done. An external variable has to be defined outside of any function. This allocates actual storage for it. The function also must be declared on each function that wants to access it. This may be done either by an explicit extern declaration or implicitly by context. To make the discussion concrete, let's rewrite the longest line program with line, save, and max as external variables. This requires changing the calls, declarations, and bodies of all three functions. This sample code is on page 29 of the textbook, and it's pretty long, but I'll read it for you. Pound include stdio.h. Pound define max line 1000. And we're still outside of main. Char line, open bracket max line, close bracket, semicolon. Char save, open bracket max line, semicolon. Int max semicolon. Those are our three global variables. Starting the main open paren, close paren, open curly brace. Int len, extern int max. So we're saying that this is an integer, but it's also not to be allocated inside of main. Extern char save, open square bracket, close square bracket. The length of the save array is defined above, so we don't need to define it here. Max equals 0, semicolon, while double parenthesis len, double left parenthesis len equals get line, parenthesis, greater than 0, parenthesis. If parenthesis len greater than max, open curly brace, max equals len, copy, open parenthesis, no parenthesis, semicolon, no parameters to copy, because it's going to simply talk to the global variables, close curly brace. After the loop finishes, we say if, open parenthesis, max greater than 0, then printf, open parenthesis, double quote, %s, double quote, comma, save, close parenthesis, semicolon, close curly brace, and that is the end of the main. So now we have the getLine function, which is specialized to deal with external variables. Okay. So we start getLine, open parenthesis, close parenthesis, no parameters, open curly brace, int, c, I, semicolon. These are local variables. Extern char line, open curly brace, close curly brace, semicolon. This is our reference inside of getLine to the global variable line. For open parenthesis, I equals 0, semicolon, I less than max line minus 1. Max line minus 1, max line is a predefined constant at compile time. For I less than max line minus 1, double ampersand, parenthesis, C equals get char, open parenthesis, close parenthesis, not equal EOF, double ampersand, i.e. and, C not equal single quote backslash N, single quote semicolon, plus I. Line sub I equals C. That's the for loop that in effect reads characters one at a time and puts them in line. But after the for loop, we say if, open parenthesis, C double equals single quote backslash N single quote, close parenthesis, open curly brace, line sub I equals C plus I, close curly brace. This ensures that we append the new line to the function. Line sub I equals single quote backslash 0 backslash, that's semicolon. That's the string termination character. Return I. Return open parenthesis I close parenthesis. This is the length that getLine is returning. And then close curly brace to end the getLine function. And then we have the copy function, and again it takes no parameters. Copy open parenthesis close parenthesis curly brace int I extern char line open bracket close bracket comma, save, open bracket, close bracket, semicolon. I equals 0, while, parenthesis, open parenthesis, save sub I equals line sub I, close parenthesis, is not equal, quote, backslash 0, quote, plus plus I. Close curly brace for copy. So the external variables in main, getLine, and copy are defined by the very first lines in the example above, outside of main, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like the declarations we used previously, but because they occur outside of any function, including outside the main function, the variables are external. Before a function can use or access an external variable, the name of the variable must be made known to the function. One way to do this is to write an extern declaration in the function. The declaration is the same as before except for the added keyword extern. In certain circumstances, the extern declaration can be omitted. If the external definition of the variable occurs in the same source file before it's used in a particular function, then there's no need for an extern declaration in the function. The extern declarations in main and getLine and copy are thus redundant. In fact, common practice is to place all definition of all external variables at the beginning of the source file and then omit all extern declarations. If the program is in several source files and a variable is defined in, say, file 1 and used in file 2, then an extern declaration is needed in file 2 to connect the two occurrences of the variables. This topic is discussed at length in Chapter 4. You should note that we are using the words declaration and definition very carefully when we refer to external variables in this section. Definition refers to the place where the variable is actually created or assigned storage. Declaration refers to places where the nature of the variable is stated, but no storage is allocated. By the way, there is a tendency to make everything in sight an extern variable because it appears to simplify things. Argument lists are short and variables are always there when you want them, but external variables are always there also when you don't want them. The style of coding is fraught with peril since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify when it becomes necessary. The second version of the longest line program is inferior to the first, partly because of these reasons, and partly because it destroys the generality of two quite useful functions by hardwiring them into the names of the variables they will manipulate. Section 1.11, Summary. At this point, we have covered what might be called the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size. And it's probably a good idea if you paused long enough to do so. The exercises that follow are intended to give you suggestions for programs of somewhat greater complexity than the ones presented in this chapter. After you have this much C under control, it will be well worth your effort to read on, for the features covered in the next few chapters are where the power and expressiveness of the language begin to become apparent. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 2. Types, Operators, and Expressions. Variables and constants are the basic data objects manipulated in a program. Declarations list the variables to be used and state what type they have and perhaps what their initial values are. Operators specify what is to be done to them. Expressions combine variables and constants to produce new values. These are the topics of this chapter. Section 2.1, Variable Names. Although we didn't come out and say so, there are some restrictions on variable and symbolic constant names. Names are made up of letters and digits. The first character must be a letter. The underscore counts as a letter. It is useful for improving the readability of long variable names. Upper and lower case are different. Traditional C practice is to use lowercase for variable names and all uppercase for symbolic constants. Only the first 8 characters of an internal name are significant, although more may be used. For external names, such as function names and external variables, the number must be less than 8 because external names are used by various assemblers and loaders. Appendix A lists the details. Furthermore, keywords like if, else, int, float, etc. are reserved. You can't use them as variable names, and they must be in lowercase. I would note that in modern C languages, the limitation of the first 8 characters of a variable name being unique has been extended. In most C variants, at least 30 characters of a variable are treated as unique. The 8-character limitation was to reflect the typical limitation of identifier length in assembly language programming and runtime linkers of the time. Naturally, it's wise to choose variable names that mean something, that are related to the purpose of the variable, and are unlikely to get mixed up typographically. Section 2.2, Data Types and Sizes. There are only a few basic data types in C. Char, which is a single byte, capable of holding 1 character in the local character set. Int, an integer, typically reflecting the natural size of integers on the host machine. Float, a single precision floating point. And double is a double precision floating point. In addition, there are a number of qualifiers which can be applied to int: short, long, and unsigned. Short and long refer to different sizes of integers. Unsigned numbers obey the arithmetic of modulo 2 to the n, where n is the number of bits in an int. Unsigned numbers are always positive. The declarations for qualifiers look like short int x semicolon, long int y semicolon, unsigned int z semicolon. The word int can be omitted in such situations and typically is. The precision of these objects depends on the machine at hand. The table below shows some representative values. On a DEC PDP-11, a char is 8 bits. On int is 16, a short is 16, a char is 32, a float is 32, a double is 64. On a Honeywell 6000, which uses ASCII character set, a char is 9 bits, an int is 36 bits, a short is 36 bits, a char is 36 bits, and a float is 36 bits, and a double is 32 bits. On the IBM 370, which is EBCDIC, in its character set, a char is 8 bits, an int is 32 bits, a short is 16 bits, a char is 32 bits, a float is 32 bits, and a double is 64 bits, and so on. The intent is that short and long should provide different lengths of integers where practical. Int will normally reflect the most natural size of a particular machine. As you can see, each compiler is free to interpret short and long as appropriate for their own hardware. About all you should count on is that short is no longer than long. In this table, we see that in the mid-1970s, C was designed to support a range of computer generations. The PDP-11 was a common previous generation computer that had less memory, so variable sizes were kept small. The more modern computers in the chart had a bit more memory and could afford to have slightly larger sizes. The idea of a natural size is the size that could be loaded, computed, and stored in usually a single machine language instruction. You knew as a programmer that when you used int, the machine code you would generate would not need to include extra instructions for a simple line of code like x equals x plus 1 semicolon. Modern int values in C are 32 bits long, and long values are 64 bits long. Even though modern computers can do 64-bit computations in a single instruction, using the shorter int type when appropriate can save on memory storage and memory bandwidth using int values. Interestingly, the length of a 32-bit int leads to a UNIX and C problem with dates that is called the year 2038 problem. A common way to represent time in UNIX C programs was as a 32-bit integer of the number of seconds since January 1st, 1970. It was quick and easy to compare or add or subtract these second counter dates in code and even in databases. But the number of seconds since January 1st, 1970 will overflow a 30-bit number on the 19th of January in 2038. By now, in order to avoid problems, most systems have converted to storing these number of second values in long or 64-bit values, which gives us almost 300 billion years until we need to worry about overflowing second timer counters again. Back when C was developed, we had two different character sets and two different character variable lengths. The world generally standardized on the ASCII character set for the core Western characters and the Unicode/UTF-8 to represent all characters in all languages worldwide. But that is a story for another time. For now, just think of the char type as also a byte type. It is 8 bits in length and can store ASCII. Modern languages like Python or Java have excellent support for wide character sets. In our historical look at C, we will not cover wide or multi-byte characters. Also, if you look at the float and double types, you will see different bit sizes. Even worse, each of these computers in the 1970s did floating point computation using slightly different hardware implementations, and the same code run on different computers would give slightly different results and have unpredictable behavior on overflow, underflow, and other extraordinary floating point operations. This was solved by the introduction of the IEEE 754 standard in 1985, which standardized floating point format. This standardized both the length of the float and the double, but also ensured that the same set of floating point calculations would produce the exact same result on different processors. 2.3 Constants. Int and float constants have already been disposed of, except to note that the usual 123.456 E-7 or 0.12 E3 scientific notation for floats is also legal. Every floating point constant is taken to be double, so the E notation serves for both float and double. Long constants are written in the style 123 capital L. An ordinary integer constant that is too long to fit into an int is also assumed to be a long. There is a notation for octal and hexadecimal constants. A leading 0 on an int constant implies octal, and a leading 0x or 0x uppercase indicates hexadecimal. For example, the decimal 31 can be written as 037 in octal and 0x1f or 0x1f, where f is capitalized, in hex. Hexadecimal and octal constants may also be followed by the letter L to make them long. A character constant is a single character written in single quotes, as in quote x quote. The value of the character constant is the numeric value of the character in the machine's character set. For example, the ASCII character set 0 or quote 0 quote is 48, and an EBCDIC quote 0 quote is 240, both quite different from the numeric value 0. Writing quote 0 quote instead of a numeric value like 48 or 240 makes the program independent of the particular value. Character constants participate in numeric operations just like any other numbers, although they are most often used in comparisons with other characters. A later section treats conversion rules. Certain non-graphic characters can be represented in character constants by escape sequence, like \n for new line, \t for tab, \0 for null, \\/ for \/ itself, and \quote for single quote, etc. These look like two characters, but they're actually only one. In addition, an arbitrary byte-sized bit pattern can be generated by writing single quote, \, and then 3 digits, single quote, where the 3 digits is 1 to 3 octal digits, as in #define space form feed, single quote, \014, single quote, which is ASCII for a form feed. We mention form feed here because in the 1970s, we sent much of our output to printers, physical printers. A form feed was the character we would send to the printer to advance to the top of a new page. The character constant, quote, \0, quote, represents the character with the value 0. Quote, \0, quote, is often written instead of 0 to emphasize the character nature of some expression. A constant expression is an expression that only involves constants. Such expressions are evaluated at compile time rather than runtime, and accordingly may be used in any place a constant may be, as in #define max line 1000, char line open bracket max line +1 close bracket semicolon, or seconds equals 60 times 60 times hours. A string constant is a sequence of 0 or more characters surrounded by double quotes, as in double quote I space am space a space string double quote, or double quote, which is a way to show an empty string. The quotes are not part of the string, but only serve to delimit it. The same escape sequences used for character constants apply in strings. \double quote represents the double quote character. Technically, a string is an array whose elements are single characters. The compiler automatically places the null character, \0, at the end of each such string, so programs can conveniently find the end. This representation means that there is no real limit on how long a string can be, but programs have to scan 1 to completely determine its length. The physical storage required is one more location than the number of characters written between the quotes. The following function, strlen, taking the parameter s, returns the length of the character string s, excluding the terminal \0. Strlen, open parenthesis, s, close parenthesis. Char, s, open bracket, close bracket, semicolon. Open curly brace. Int space I, semicolon. I equals 0, semicolon. While, parenthesis, s, sub I, exclamation equals, quote, \0, quote, close parenthesis, plus I, semicolon, return, parenthesis I, parenthesis, semicolon, close curly brace. Be careful to distinguish between the character constant and the string that it contains a single character. Single quote x, single quote, is not the same as double quote x, double quote. The former is a single character used to produce the numerical value of the letter x in the machine's character set. The latter is a character string that contains one character, the letter x, and a \0. Section 2.4. All variables must be declared before use, although certain declarations can be made implicitly by context. A declaration specifies a type and is followed by a list of one or more variables of that type, as in int lower, upper, step, semicolon. Char, c, line, open bracket 1000, close bracket, semicolon. Variables can be distributed among declaration in any fashion. The list above could be equally well written as int lower, semicolon, int upper, semicolon, int step, semicolon, char, c, semicolon, char, line, open bracket 1000, close bracket, semicolon. The latter form takes more room, but it is convenient for adding a comment to each declaration or for subsequent modifications. Variables may also be initialized in their declaration, although there are some restrictions. If the name is followed by an equal sign in a constant, that serves as an initializer, as in char \equals single quote \, single quote, semicolon. Int I equals 0, semicolon. Float EPS equals 1.0 e minus 5, semicolon. If the variable in question is external or static, the initialization is done once only, conceptually, before the program starts executing. Explicitly initialized automatic variables are initialized each time the function they are in is called, Automatic variables for which there is no explicit initializer have undefined, that is, garbage values. External and static variables are initialized to 0 by default, but it is a good style to state the initialization anyway. We will discuss initialization further as new data types are introduced. Section 2.5, Arithmetic Operators. The binary operators are plus, minus, asterisk, and slash, and the modulus operator %. There is a unary minus but no unary plus. Integer division truncates any fractional part. The expression x%y produces the remainder when x is divided by y, and is thus 0 when y divides x exactly. For example, a year is a leap year if it is divisible by 4 but not by 100, except that years divisible by 4 are leap years. Therefore, if parenthesis year %4 equals 0 and year %100 not equal 0, or year %400 equals 0, it's a leap year, else it's not. The % operator cannot be applied to float or double. The plus and minus operators have the same precedence, which is lower than the identical precedence of asterisk, slash, and %, which are in turn lower than unary minus. Arithmetic operators group from left to right. A table at the end of this chapter summarizes precedence and associativity for all operators. The order of evaluation is not specified for associative and commutative operators like asterisk and plus. The compiler may rearrange a parenthesized computation involving these. Thus, a plus open parenthesis b plus c close parenthesis can be evaluated as open parenthesis a plus b close parenthesis plus c. This rarely makes any difference, but if a particular order is required, explicit temporary variables might be used. The action on overflow or underflow depends on the machine at hand. I would note that the above paragraph allows the compiler to reorder computations, even in the presence of parentheses, is known as the K&R C arrangement license. As the authors state, it almost never makes a difference unless an expression contains a value computed in a function call, or is there a pointer lookup to find a value for the computation that might fail. The rule was subtly adjusted in the ISO version of C, but ISO C still does not strictly force the order of otherwise commutative operations, even in the presence of parentheses. The good news is that as long as you keep your expression simple, you don't have to worry about this rule. Sometimes the real value of parentheses is to communicate your intentions to the human readers of your code. If you are writing code that depends on the order of overflow, function calls, and pointer dereferences in a single mathematical expression, perhaps you should break your expression into multiple statements. Section 2.6, Relational and Logical Operators. The relational operators are greater than or equal, less than or equal. They all have the same precedence. Just below them in precedence are the equality operators, double equals and exclamation equals, which have the same precedence. Relationals have lower precedence than arithmetic operators, so expressions like I less than lim minus 1 are taken as I less than open parenthesis lim minus 1 close parenthesis, as would be expected. More interesting are the logical connectives double ampersand and double vertical bar, and or. Expressions connected by double ampersand or double vertical bar are evaluated left to right, and the evaluation stops as soon as the truth or falsehood of the result is known. These properties are critical in writing programs that work. For example, here is a loop from the input function getLine, which we wrote in Chapter 1. For parenthesis I equals 0 semicolon, I less than lim minus 1 double ampersand, parenthesis C equals getChar open parenthesis close parenthesis, not equal single quote backslash n single quote, double ampersand, C, exclamation equal EOF, semicolon, plus plus I, close parenthesis, S sub I equals C. Clearly, before reading a new character, it is necessary to check that there's room to store the array, so the test I less than lim minus 1 must be made first. Not only, but if this test fails, we must not go on and read another character. Similarly, it would be unfortunate if C were tested against EOF before getChar was called. The call must occur before the character C is checked against EOF. The precedence of double ampersand and is greater than that of double vertical bar or, and both are lower than the relational inequality operators. So expressions like I less than lim minus 1, double ampersand, parentheses C equals getChar, open paren, close paren, not equal, single quote, backslash n, single quote, double ampersand, C not equal EOF, needs no extra parentheses. But since the parenthesis of not equals is higher than assignment, parentheses do need to be added in open paren, C equals getChar, open paren, not equal, backslash n, to achieve the desired result. Let's take a brief digression. One of the great debates of the 1970s was how to use structured programming to avoid any use of goto statements that lead to completely unreadable spaghetti code. Structured code was easier to read, debug, and validate. Structured code advocated for if-then-else, else-if, while-do loops, and do-while loops, where the loop exit test was at the top or the bottom of the loops, respectively. There was a move from flowcharts with lines, boxes, and arrows to structured programming techniques like Nashi-Schneiderman diagrams that used nested boxes to emphasize the structured nature of the code. The proponents of each approach tended to approach the problem based on the language they used. ALGOL and Pascal programmers were strong advocates of structured programming, and those languages had syntax that encouraged the approach. Fortran programs had decades of flowchart use and flowchart style thinking, and tended to avoid full adoption of structured programming. Kernigan and Ritchie chose a middle path and made it so that C could support both approaches to avoid angering either side of the structured programming debate. One area where the structured code movement kept hitting a snag was implementing a loop that reads a file and processes data until it reaches the end of file. The loop must be able to handle an empty file or no data at all. There are three ways to construct a read and process until EOF loop, and none of the approaches are ideal. The loop constructions that you can do are a top-tested loop with a priming read before the loop, a bottom-tested loop with a read as the first statement in the loop and an if-then-else as the rest of the body of the loop, a top-tested infinite loop with a priming read and a middle test and exit, and a top-tested loop with a side effect read in the test of the loop, which is the way that Kernigan and Ritchie chose to document in this chapter. All of this serves to explain the syntax. While, open parenthesis, C equals getChar, open paren, close parenthesis, not equal EOF, close parenthesis, open curly brace, body of the loop, close curly brace. This construct is a top-tested loop, which most programmers prefer, and it folds the priming read and puts its value inside the variable C. But since getChar might also return EOF, we need to check if we actually receive no data at all and need to avoid executing the body of the loop or exit the loop. If EOF were defined as 0 instead of -1, the loop could have been written while open parenthesis C equals getChar, open paren, close parenthesis, open curly brace, body of the loop, close curly brace. Now, the getChar function returns a character or 0, and the test itself is looking at the side effect or residual value of the assignment statement to decide to start and or continue the loop body. The problem with using 0 as end of file, if you are reading a binary file like JPEG data, a 0 character might make perfect sense, and we would not want to incorrectly end the loop because of a 0 character in input data that is not end of file. So we get the double parentheses syntax. the side effect call to get char, and test the return value within the while test. I'm quite confident that this is far more detail that you wanted here in Chapter 2, but it is as good a time as any to understand how much thought goes into a programming language, how it is designed and documented. By the time we finish Chapter 3 and look at the break and continue statements, which are in languages like Python and Java, you will see that this 50-year-old structured programming debate is still unresolved in the minds of many software developers. Back to the book. The unary negation operator, logical negation operator, converts a non-zero or true operand into 0 and a 0 or false operand into 1. A common use of exclamation, which we often call bang, is in constructions like if, open parenthesis, exclamation point inward, close parenthesis, rather than if, open parenthesis, inward equal 0. It is hard to generalize about which of these two forms is better. Construction like exclamation inward read quite nicely as if not inward, but more complicated ones can be hard to understand. Section 2.7, Type Conversions. When operands of different types appear in expressions, they are converted to a common type according to a small number of rules. In general, the only conversions that happen automatically are those that make sense, such as converting an integer to a floating point in an expression like f plus I. Expressions that don't make sense, like using a float in a subscript, are disallowed. First, chars and ints may be freely intermixed in arithmetic expressions. Every char in an expression is automatically converted to an int. This permits considerable flexibility in certain kinds of character transformations. One is exemplified by the function a to I, which converts a string of digits into its numeric equivalent. A to I, open parenthesis, s, close parenthesis. Char, s, open bracket, close bracket, semicolon. Open curly brace. Int, I, comma, n, semicolon. N equals 0. For, parenthesis, I equals 0, semicolon. S sub I greater than or equal to, quote, 0, quote, double ampersand. S sub I less than or equal to, double, quote, 9, quote, semicolon, plus plus I, close parenthesis. N equals 10 asterisk n plus S sub I minus single quote 0, single quote, semicolon. Return open parenthesis n, close parenthesis, semicolon, close curly brace to end the function. As we discussed in Chapter 1, the expression S sub I minus quote 0, quote, gives the numeric value of the character stored in S sub I because the values 0, 1, etc. form a continuously increasing positive sequence. Another example of the char to int conversion is the function lower, which maps a single character to lowercase for the ASCII character set only. If the character is not an uppercase letter, lower is returned unchanged. Here's a function. Lower, open parenthesis, c, close parenthesis, int c, semicolon, open curly brace. If, open parenthesis, c greater than or equal to, quote, capital A, quote, double ampersand, c less than or equal to, quote, z, quote, uppercase z, parenthesis, return, open parenthesis, c plus, quote, lowercase a, quote, minus, quote, uppercase a, quote, close parenthesis, semicolon, else return c. This works for ASCII because the corresponding upper and lowercase letters are a fixed distance apart as numeric values, and each alphabet is contiguous. There is nothing but letters between A and Z. This latter observation is not true of the EBCDIC character set on IBM 360-370 architectures, so this code fails on such systems. It converts more than letters. There is one subtle point about the conversion of characters to integer. The language does not specify whether the variables of type char are signed or unsigned quantities. When char is converted to an int, can it ever produce a negative number? Unfortunately, this varies from machine to machine, reflecting differences in architecture. On some machines, PDP-11 for instance, a char whose leftmost bit is 1 will be converted to negative integer using sign extension. On others, a char is promoted to an int by adding zeros at the left end and is thus always positive. The definition of C guarantees that any character in the machine standard character set will never appear to be negative, so these characters may be used freely in expressions as positive quantities, but arbitrary bit patterns stored in character variables may appear to be negative on some machines, yet positive on others. The most common occurrence of this situation is when the value -1 is used for EOF. Consider the code char C semicolon. C equals get char open paren close paren semicolon. If open paren C double equals EOF close paren ... On a machine which does not do sign extension, C is always positive because it returns a char. Yet EOF is negative. As a result, this test always fails. To avoid this, we have been careful to use int instead of char for any variable which holds a value returned by the function getChar. The real reason for using int instead of char is not related to any questions of possible sign extensions. It is simply that getChar must return all possible characters so that it can be used to read arbitrary input, and in addition, a distinct EOF value. Thus, its value cannot be represented as a char, but must instead be stored as an int. As an aside, since the book was written before the getChar function was standardized, the text is somewhat vague in this section. Shortly after the book was published, getChar was put into the stdio.h library and declared to return an integer so as to accommodate all possible characters and the integer -1 value to indicate the end of file. The above code would be better written with C declared as an integer. Int C semicolon. C equals getChar, open paren, close paren, semicolon. If, open paren, C double equal EOF, close paren, ... While the conversion from char to int may or may not have sign extension, and yes, it still depends on the implementation 50 years later, the conversion from int to char is predictable, with the top bits being simply discarded. If you're using the library function getS to read a file line by line, we don't need to worry about this conversion. Since getS returns a pointer to a character array, i.e. a string, it indicates it has reached end of file by returning the null pointer, i.e. there is no more data to give. Back to the textbook. Another useful form of automatic type conversions is that relational expressions like I greater than j and logical expressions constructed by double ampersand and double vertical bar, and or respectively, are defined to have the value 1 if true and 0 if false. Thus, the assignment isDigit equals C greater than or equal to quote 0 quote double ampersand C less than or equal to quote 9 quote sets the variable isDigit to 1 if C is a digit and 0 if it's not. In the if test in a test part of an if, while, or for, true just means non-zero. Implicit arithmetic conversions work much as expected. In general, if an operator like C or asterisk for multiplication, which takes two operators, i.e. a binary operator, if it has operands of different types, the lower type is promoted to the higher type before the operation proceeds, and the result is the higher type. More precisely, for each arithmetic operator, the following sequence of conversion rules is applied. Char and short are converted to int, and float is converted to double. Then, if either operand is double, the other is converted to double, and the result is double. Otherwise, if either operand is long and the other is converted to long, the result is long. Otherwise, if either operand is unsigned, the other is converted to unsigned, and the result is unsigned. Otherwise, the operands must be int, and the result is int. Note that all float values in an expression are converted to double. All floating point arithmetic in C is done in double precision. Conversions take place across assignments. The value of the right side is converted to the type of the left, which is the type of the result. A character is converted to an integer either by sign extension or not, as described above. The reverse operation int to char is well behaved. Excess high order bits are simply discarded. Thus in int I semicolon char C semicolon, I equals C, C equals I, the value of C is unchanged. And this is true whether or not sign extension is involved. If x is float and I is int, then x equals I and I equals x both cause conversions. Float to int causes truncation of any fractional part. Double is converted to float by rounding. Longer ints are converted to shorter ones or to chars by dropping excess high-order bits. Since a function argument is an expression, type conversions also take place when arguments are passed to functions. In particular, char and short become int and float becomes double, and that is why we have declared function arguments to be int and double even when the function is called with char and float. Finally, explicit type conversions can be forced, also we call it coerced, in any expression with a construct called the cast. In the construction, open parenthesis type name, close parenthesis expression, the expression is converted to the named type by the conversion rules above. The precise meaning of cast is in fact as if the expression were assigned to a variable of the specified type, which is then used in place of the whole construction. For example, the library square root, sqrt, expects a double argument and will produce nonsense if inadvertently handed something else. So if n is an integer, sqrt, open parenthesis, double, close parenthesis, n, close parenthesis, converts n to double before passing it to sqrt. Note that the cast produces the value of n in the proper type. The actual content of n is not altered. The cast operator has the same precedence as other unary operations as is summarized in the table at the end of this chapter. Section 2.8, Increment and Decrement Operators. C provides two unusual operators for incrementing and decrementing variables. The increment operator, plus plus, adds 1 to its operand. The decrement operator, minus minus, subtracts 1. We have frequently used plus plus to increment variables, as in if open parenthesis C equals single quote backslash n single quote close parenthesis plus plus and L semicolon. The unusual aspect is that plus plus and minus minus may be used either as prefix operators, i.e. before the variable as in plus plus n, or postfix after the variable n plus plus. In both cases, the effect is to increment n, but the expression, the residual value of the expression plus plus n, increments n before using its value, while n plus plus increments n after its value has been used. This means that in a context where the value is used, not just the effect, plus plus n and n plus plus are different. If n is 5, then x equals n plus plus semicolon sets x to 5, the old value. But x equals plus plus n semicolon sets x to 6, the new value. In both cases, n becomes 6. The increment and decrement operators can only be applied to variables. An expression like x equals open parenthesis I plus j, close parenthesis plus plus is illegal. In a context where no value is wanted, just incrementing effect, as in if open parenthesis C double equals single quote backslash n single quote close parenthesis n L plus plus semicolon, choose prefix or postfix according to taste. But there are situations where one or the other is specifically called for. For example, consider the function squeeze, s, c, which removes all occurrences of the character c from the string s. Squeeze, open parenthesis, s, c, close parenthesis. Char, s, open bracket, close bracket, semicolon, int c, semicolon. Open curly brace, int I, j, semicolon. For parenthesis, I equals j equals 0, semicolon, s sub I not equal to single quote backslash 0 single quote semicolon I plus plus close parenthesis. If open parenthesis s sub I not equal to c close parenthesis, s sub j plus plus close parenthesis equals s sub I. and outside the for loop totally, S sub j equals backslash quote, S sub j equals quote, backslash 0 quote, semicolon, close curly brace. Each time a non-C, a character other than what's in the variable C, occurs, it is copied into the current J position, and only then is J incremented to be ready for the next character. This is exactly equivalent to if, open parenthesis, S sub I not equal to C, close parenthesis, open curly brace, S sub J equals S sub I, semicolon, J plus plus, semicolon, close curly brace. Another example of a similar construction comes from the getLine function we wrote in Chapter 1, where we can replace if, open parenthesis, C double equals, quote, backslash n, quote, close parenthesis, open curly brace, S sub I equals C, semicolon, plus plus I, semicolon, close parenthesis, by the far more compact if parenthesis, C double equals, quote, backslash n, quote, close parenthesis, S sub I plus plus equals C, semicolon. In a third example, the function stircat concatenates the string T to the end of the string S. Stircat does assume that there's enough space in S to hold the combination. Here's the code. Stircat, open parenthesis, S comma T, close parenthesis. Char, S, open bracket, close bracket, comma, T, open bracket, close bracket, semicolon. Open curly brace. Int, I comma J, semicolon. I equals J equals 0, semicolon. While, open paren, S sub I not equal, single quote, backslash 0, single quote, close paren, I plus plus. In this, we'd find the end of S. While, open parenthesis, S sub I plus plus equals T sub J plus plus, close parenthesis, not equal, backslash 0, close parenthesis, semicolon. That code copies the rest of T into S, close curly brace. As each character is copied from T to S, the postfix plus plus is applied to both I and J to make sure they are in position for the next pass through the loop. Section 2.9, Bitwise Logical Operators. C provides a number of operators for bit manipulation. These may not be applied to float or double. Ampersand is bitwise AND. Vertical bar is bitwise inclusive OR. Caret is bitwise exclusive OR. Less than is left shift, and greater than is right shift. And tilde is one complements, and it's a unary operator. The bitwise AND operator, ampersand, is often used to mask off some set of bits. For example, C equals N ampersand 0, 1, 7, 7. Sets to 0 all but the lower 7 bits of N. The bitwise OR operator is used to turn bits on. X equals X vertical bar mask. Sets to 1 the X bits that are set to 1 in mask. You should carefully distinguish the bitwise operator ampersand and vertical bar from the logical connectives double ampersand and double vertical bar, which imply left to right evaluation of a truth value. For example, if X is 1 and Y is 2, then X single ampersand Y is 0, while X double ampersand Y is 1. Think about that for a moment. The shift operators less than and greater than perform left and right shifts respectively of their left operand by the number of bit positions given by the right operand. Thus, X less than 2 shifts X left by 2 positions, filling the vacated bits with 0. This is the equivalent to multiplication by 4. Right shifting an unsigned quantity fills the vacated bits with 0. Right shifting a signed quantity will fill the signed bits, or arithmetic shift, on some machines, such as PDP-11, and with 0 bits logical shift on other. The unary operator tilde yields the ones complement of an integer. That is, it converts each 1 bit into a 0 bit and vice versa. This operator typically finds use in expressions like X ampersand tilde 077, which masks the last 6 bits of x to 0. Note that x ampersand tilde 077 is independent of word length and is thus preferable to, for example, x ampersand 0177700, which assumes that x is a 16-bit quantity. The portable form involves no extra cost since tilde 077 is a constant expression and thus evaluated at compile time. To illustrate the use of some of the bit operators, consider the function getBits, open parenthesis, x, comma, p, comma, n, which returns the right-adjusted n-bit field of x that begins at position p. We assume that bit position 0 is at the right end and that n and p are sensible positive values. For example, getBits, open paren, x, comma, 4, comma, 3, close paren, returns the 3 bits in bit positions 4, 3, and 2 right adjusted. Here we go with the code. GetBits, open paren, x, comma, p, comma, n, unsigned, x, comma, p, comma, n, semicolon, open curly brace. Return, open parenthesis, x, greater than, open parenthesis, p plus 1 minus n, close parenthesis, and ampersand, tilde, open parenthesis, tilde 0, less than, n, close parenthesis, semicolon, close curly brace. X, greater than, parenthesis, p plus 1 minus n, close parenthesis, moves the desired field to the right end of the word. Declaring the argument x to be unsigned ensures that when it is right shifted, vacated bits will be filled with zeros, not signed bits, regardless of the machine the program is run on. Tilde 0 is all 1 bits. Shifting it left n bit positions with tilde 0 tilde 0 less than n creates a mask with the zeros in the rightmost n bits and ones everywhere else. Complementing that with tilde makes a mask with ones in the rightmost bits. Bitwise operators may seem unnecessary for modern computers, but if you look at the internal structure of TCP/IP packets, the values are packed very tightly into the headers in order to save space. C made it possible to write portable TCP/IP implementations on a wide range of hardware architectures. Bitwise operators also play an important role in encryption, decryption, and checksum calculations. Modern languages like Java and Python support bitwise operators following the same patterns that we established in C, so that things like TCP/IP and encryption algorithms can also be implemented in these languages. By defining these operators, it kept software developers from needing to write non-portable assembly language to implement these low-level features in operating systems and libraries. Section 2.10, Assignment Operators and Expressions. Expressions such as I equals I plus 2, in which the left-hand side is repeated on the right, can be written in the compressed form I plus equals 2, using an assignment operator like plus equals. Most binary operators like plus that have a left and right operand, have a corresponding assignment operator, op equals, where op is one of plus, minus, asterisk for multiplication, slash for division, percent for modulo, less than, left shift, greater than, right shift, ampersand, bitwise and, caret, exclusive or, vertical bar, bitwise or. If E1 and E2 are expressions, then E1 operand equals E2 is equivalent to E1 equals E1 operand E2, except that E1 is only computed once. Note the parentheses around E2. X star equals Y plus 1 is actually X equals X times parenthesis Y plus 1, close parenthesis, rather than X times Y plus 1. As an example, the function bitCount counts the number of 1 bits in its integer argument. Here's the code. BitCount, open parenthesis, n, close parenthesis, unsigned, n, semicolon, open curly brace, int b, 4, open parenthesis, b equals 0, semicolon, n, exclamation equals 0, semicolon, n, greater than equal 1, close parenthesis, if, open parenthesis, n ampersand 0, 1, close parenthesis, b plus plus semicolon, return, open paren, b, close paren, semicolon, curly brace. Quite apart from its conciseness, assignment operators have the advantage in that they correspond better to the way people think. We say add 2 to I, or increment I by 2, not take I, add 2, and put the result back in I. Thus, I plus equal 2. In addition, for a complicated expression like val, open bracket, yypv, open bracket, p3 plus p4, close bracket, plus yypv, open bracket, p1 plus p2, close bracket, plus equals 2, the assignment operator makes code easier to understand, since the reader doesn't have to check painstakingly that two long expressions are indeed the same or wonder why they're not. An assignment operator may even help the compiler to produce more efficient code. We have already used the fact that the assignment statement has a side effect value and can occur in expressions. The most common example is while, open parenthesis, C equals getchar, open parenthesis, close parenthesis, exclamation equal EOF, close parenthesis, and then the rest of the loop. Assignments using other assignment operators, plus equal, minus equal, can also occur in expressions, although it's a less frequent occurrence. The type of an assignment expression is the type of its left operand. Section 2.11, Conditional Expressions. The statements, if, parenthesis, A greater than B, close parenthesis, Z equals A, semicolon, else Z equals B, semicolon, of course, compute Z in the maximum of A and B. The conditional expression, written with a ternary operator, which is question mark and colon, provides an alternate way to write this and similar constructions. In the expression E1 question mark E2 colon E3, the expression E1 is evaluated first. If it is non-zero, true, then the expression E2 is evaluated, and that is the value of the conditional expression. Otherwise, E3 is evaluated, and that is the value. Only one of E2 and E3 are evaluated. Thus, to set Z to the maximum of A and B, we say Z equals parenthesis A greater than B, close parenthesis, question mark, A colon B. And this implements Z equals max of A and B. It should be noted that the conditional expression is indeed an expression and can be used just as any other expression. If E1 and if E2 and E3 are different types, the type of the result is determined by the conversion rules described earlier in this chapter. For example, if f is a float and n is an int, then the expression parenthesis n greater than 0, close parenthesis, question mark f colon n is of type double, regardless of whether n is positive or not. Parentheses are not necessary around the first expression of a conditional expression since the precedence of question mark colon is very low, just above assignment. They are advisable anyway, however, since they make the condition part of the expression easier to see. The conditional expression often leads to succinct code. For example, this loop prints n elements of an array, 10 per line, with each column separated by one blank, and with each line, including the last, terminated by exactly one new line. Here's the code. For parenthesis I equals 0, semicolon, I less than n, semicolon, I plus plus, close parenthesis. Printf, open parenthesis, double quote, %6d, %c, double quote, comma, a sub I, comma, open parenthesis, I %10, double equal 9, or double vertical bar, I double equal n minus 1, close parenthesis, question mark, single quote, backslash n, single quote, colon, single quote, space, single quote, close parenthesis, semicolon. A new line is printed after every 10th element and after the nth, and all elements are followed by one blank. Although this might look tricky, it's instructive to try to write it without the conditional expression. Section 2.12, Precedence and Order of Evaluation. The table below summarizes the rules for precedence and associativity of all operators, including those which we have not yet discussed. Operators on the same line have the same precedence. rows are in order of decreasing precedence. So for example, asterisk, slash, and percent all have the same precedence, which is higher than that of plus and minus. Parentheses, square brackets, the arrow operator, and the dot operator are first with the left to right associativity. Next precedence is exclamation, tilde, plus plus, minus minus, single minus. The cast, multiplication, bitwise and, size of, with right to left associativity. Then multiplication, division, and modulo with left to right associativity. Then plus and minus with left to right associativity. Then left shift, which is less than, and right shift, which is right greater than, with left to right associativity. Then logical operators, less than or equal to, greater than or equal to, with left to right associativity. Then comparison, double equals, not equal, exclamation equal, left to right. Then we have some bitwise operators, the bitwise and with left to right associativity. Then the bitwise exclusive or with left-right associativity, which is a caret. Then the single vertical bar, which is bitwise or with left to right associativity. Then we have ampersand, which is and, the logical and, left to right associativity. Then double vertical bar, which is the logical or with left to right associativity. Then the ternary operator, which is question mark and colon with right to left associativity. Then the assignments, equals, plus equals, minus equals, etc., with right to left associativity. And then the comma, which we'll cover in the next chapter, with left to right associativity. The operators dash, greater than, and dot are used to access members of structures. They'll be covered in Chapter 6, along with size of, and then in Chapter 5, we'll discuss asterisk, indirection, and ampersand, address of. Note that the precedence of the bitwise logical operators ampersand, caret, and vertical bar falls below double equals and exclamation equals. This implies that bit testing expressions like if, parenthesis, x, ampersand, mass, close parenthesis, equal 0, close parenthesis, must be fully parenthesized to get proper results. As mentioned before, expressions involving one or more of the associative and commutative operators like multiply, plus, bitwise and, bitwise or, and bitwise exclusive or can be rearranged even when parenthesized. In most cases, this makes no difference whatsoever. In situations where it might, explicit temporary variables can use to force a particular order of evaluation. C, like most languages, does not specify in what order operands of an operator are evaluated. For example, in a statement like x equals f open parenthesis close parenthesis plus g open parenthesis close parenthesis semicolon, f may be evaluated before g or vice versa. Thus, if f or g alters an external variable that the other depends on, x can depend on the order value of evaluation. Again, intermediate results can be stored in temporary variables to ensure a particular sequence. Similarly, the order which function arguments are evaluated is not specified. So, the statement printf open parenthesis double quote %d space %d \n double quote comma plus n comma power open parenthesis 2 comma n close parenthesis is wrong. It can and often does produce different results on different machines, depending on whether or not n is incremented before power is called. The solution, of course, is to write ++n semicolon printf open parenthesis double quote %d space %d \n double quote comma n comma power open parenthesis 2 comma n close parenthesis. Function calls, nested assignment statements, and increment and decrement operators cause side effects. Some variable is changed as a byproduct of the evaluation of an expression. In any expression involving side effects, there can be subtle dependencies on the order in which variables taking part in the expression are stored. One unhappy situation is typified by the statement, a sub I equals I plus plus. The question is whether or not the subscript is the old value of I or the new value. The compiler can do this in different ways and generate different answers depending on its interpretation. When side effects, i.e. assignment to actual variables, takes place, is left to the discretion of the compiler, since the best order strongly depends on machine architecture. The moral of this discussion is writing code which depends on the order of evaluation is a bad programming practice in any language. Naturally, it is necessary to know what things to avoid, but if you don't know how they are done on various machines, that innocence may help to protect you. The C verifier lint will detect most dependencies on order of evaluation. I would add that the real moral of the story is to use side effect operators very carefully. They are generally only used in idiomatic situations and then written using simple code. The authors are happy to tell you everything that you can do in C in great detail. And they are also suggesting that just because you can do something does not mean that you should do something. Remember that a key aspect of writing programs is to communicate with future human readers of your code, including you reading your own code in the future. With modern-day compilers and optimizers, you gain little performance by writing dense or obtuse code. Write the code, describe what you want done, and let the compiler find the best way to do it. One of the reasons that a common senior project in many computer science degrees was to write a compiler is to make sure that all computer scientists understand that they can trust the compiler to generate great code. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 3, Control Flow. The control flow statements of a language specify the order in which the computations are done. We have already met the most common control flow constructions of C in earlier examples. Here we will complete the set and be more precise about the ones discussed above. 3.1 Statements and Blocks. An expression such as x equals 0 or I++ or printf open paren ... close paren becomes a statement when it is followed by a semicolon, as in x equals 0 semicolon, I++ semicolon, printf open parentheses something, close parenthesis, semicolon. In C, the semicolon is a statement terminator rather than a separator as it is in ALGOL-like languages. The braces, the curly braces, open curly brace and close curly brace, are used to group declarations and statements together into a compound statement or block so that they are syntactically equivalent to a single statement. The braces that actually surround the statements of a function are one obvious example. Braces around multiple statements after an if, else, while, or for are another. Variables can actually be declared inside any block. We will talk about this in Chapter 4. There is never a semicolon after the right curly brace that ends a block. Ah, C, how do I love thee? Let me count the ways. Quote by Dr. Chuck with homage to Elizabeth Barrett Browning. The humble semicolon is why spacing and line ends do not matter in C and C-like languages. It means that we as programmers can focus all of our white space and line ends on communicating our intent to humans. This freedom is not an excuse to write obtuse code or dense code. For example, see the obfuscated Perl contest, but instead, freedom to describe what we mean or use spacing to help us understand or maintain our code. We can take a quick look at how a few other C-like languages that came after C treat the semicolon. Java is just like C in that the semicolon terminates statements. Python treats the semicolon as a separator, like Algol, allowing more than one statement on a single line. But since Python treats the end of a line as a statement separator, you generally never use semicolon in Python. But for people like me who automatically add a semicolon when typing code too fast, at least Python ignores the few semicolons I mistakenly add to my code out of habit. JavaScript treats the semicolon as a separator, but since JavaScript ignores the end of the line, it's treated as white space. Semicolons are required when a block of code consists of more than one statement. When I write JavaScript, I meticulously include semicolons at the end of all statements because any good programmer can write C in any language. Back to the text. 3.2. If-else. The if-else statement is used to make decisions. Formally, the syntax is if, parentheses, expression, parentheses, statement 1, else, statement 2, where the else part is optional. The expression in parentheses is evaluated. If it evaluates to true, that is, the expression has a non-zero value, statement 1 is done. If it is false, the expression is 0. And there's an else part, statement 2 is executed instead. Since an if simply tests the numeric value of the expression, certain coding shortcuts are possible. The most obvious is writing if, open parenthesis, expression, instead of if, open parenthesis, expression, not equal 0, close parenthesis. Sometimes this is natural and clear, other times it's cryptic. Because the else part of an if-else is optional, there is an ambiguity when an else is omitted from a nested if sequence. This is resolved the usual way. The else is associated with the closest previous elseless if. For example, if, open parenthesis, n greater than 0, close parenthesis, if, open parenthesis, a greater than b, close parenthesis, z equals a, semicolon, else z equals b. The else with the z equals b goes with the inner if, as we have shown by the indentation in the above example. If that's not what you want, braces must be used to force the proper association. If n greater than 0, open curly brace, if a greater than b, z equals a, semicolon, close curly brace, else z equals b. This ambiguity is especially pernicious in situations like if, open parenthesis, n greater than 0, for, open parenthesis, I equals 0, semicolon, I less than n, semicolon, I plus plus, close parenthesis, if, open parenthesis, s sub I greater than 0, close parenthesis, open curly brace, printf, string, dot, 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 close parenthesis, semicolon, return, open parenthesis, I, close parenthesis, semicolon, close curly brace, else, and this is where it's wrong, printf, open parenthesis, error, n is 0, close parenthesis, semicolon. The indentation in the above example shows unequivocally what you want, but the compiler does not get the message and associates the else with the inner if. This bug can be very hard to find. By the way, notice that there is a semicolon after z equals a in if, open parenthesis, a greater than b, close parenthesis, z equals a, semicolon, else z equals b, semicolon. That is because grammatically, a statement follows the if, and an expression like z equals a is always terminated by a semicolon. Section 3.3, else if. The construction if, open parenthesis, expression, close parenthesis, statement, else, blank, if, open parenthesis, expression, close parenthesis, statement, else, if, open parenthesis, expression, close parenthesis statement, else statement occurs so often that is worth a brief separate discussion. The sequence of ifs is the most general way of writing a multi-way decision. The expressions are evaluated in order. If any expression is true, the statement associated with it is executed, and this terminates the whole chain. The code for each statement is either a single statement or a group of statements in braces. The last else handles the none of the above or default case where none of the other conditions was satisfied. Sometimes there is no explicit action for the default. In that case, the trailing else statement can be omitted, or it may be used for error checking to catch an impossible condition. To illustrate three-way decision, here is a binary search function that decides if a particular value x occurs in the sorted array v. The elements of v must be in increasing order. The function returns the position, a number between 0 and n-1, if x occurs in v, n-1 if not. This sample code is on page 54. It is the first example on page 54 in the book. Binary, open parenthesis, x, comma, v, comma, n, close parenthesis. Int x, comma, v, open square bracket, close square bracket, comma, n, semicolon, open curly brace. Int low, comma, high, comma, mid, semicolon. Low equals 0, semicolon. High equals n-1, semicolon. While, open parenthesis, low less than or equal to high, close parenthesis, open curly brace. Mid equals open parenthesis, low plus high, close parenthesis, /2, semicolon. If, open parenthesis, x less than v sub mid, close parenthesis, high equals mid-1, semicolon. Else, if, open parenthesis, x greater than v sub mid, close parenthesis, low equals mid plus 1. Else, return, open parenthesis, mid, close parenthesis, semicolon, close curly brace, closing the while, and then return, open parenthesis, -1, close parenthesis, semicolon, close curly brace to end the function. The fundamental decision in this code is whether x is less than, greater than, or equal to the middle element v sub mid at each step. This is a natural for else if. I would note that in the above examples, the else and the if in C are two language constructs that are just being used idiomatically to construct a multi-way branch or else if pattern with indentation that captures the idiom. If we are pedantic about the indentation of the above sequence, we would be separating the else and if and indenting each succeeding block further as follows, with brackets or added for clarity. If, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, if, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, and now we're quite indented at this point, if, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, statement, close curly brace, close curly brace, close curly brace. Java and JavaScript keep the else and if as separate language elements and document their idiomatic usage and indentation just like C. But in Python, elif is a single keyword and a new language construct that achieves the same idiom as shown below. If, open parenthesis, expression, close parenthesis, colon, block. elif, open parenthesis, expression, close parenthesis, colon, block. elif, if elif, parenthesis, expression, parenthesis, colon, block, else, colon, block. The C, Java, JavaScript, and Python idioms thankfully look the same when the idiomatic indentation is used. Even Fortran 77 supports the else-if construct to implement multi-way logic. Section 3.4, switch. The switch statement is a special multi-way decision maker that tests whether an expression matches one of a number of constant values and branches accordingly. In Chapter 1, we wrote a program to count the occurrences of each digit, white space, and all other characters using a sequence of if-else, if-else. Here's the same program with a switch. This is the first example program on page 55. Pound include less than stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int c, comma I, comma n white, comma n other, comma n digit, open square bracket, 10, close square bracket, a 10 element array. N white equals n other equals 0, for I equals 0, I less than 10, I plus plus, n digit sub I equals 0. While parenthesis, parenthesis, c equals getchar, open paren, close paren, not equal EOF, close paren, switch, open parenthesis, c, close parenthesis, open curly brace. Case, quote 0, quote, colon, case, quote 1, quote, colon, case, quote 2, quote, colon, case, quote 3, quote, colon, case, quote 4, quote, colon, case, quote 5, quote, colon, case, quote 6, quote, colon, case, quote 7, quote, colon, case, quote 8, quote, colon, case, quote 9, quote, colon, n digit sub c minus quote 0, quote, close bracket, plus plus, break. Now that bit of code right there was to take all of 0 through 9 and guide it to the line of code that incremented the particular element of the n-digit array by 1. Continuing after the break, semicolon. Case, quote, space, quote, colon, case, quote, backslash n, quote, colon, case, quote, backslash t, quote, colon, n white, plus plus, semicolon, break. Default, colon, n other, plus plus, colon, break, semicolon, close curly brace. Print f, open parenthesis, double quote, digits equals, double quote, close parenthesis, semicolon. For, open paren, I equals 0, I less than 10, I, semicolon, I plus plus, close parenthesis. Print f, open parenthesis, percent, space, percent d, close double quote, comma, n digit sub I, close parenthesis, semicolon. Print f, quote, backslash n, white space equals, percent d, comma, other equals percent d, backslash n, double quote, comma, n white, comma, n other, close parenthesis, semicolon, close curly brace. The switch statement evaluates the integer expression in parentheses, in this case the character c, and compares its value simultaneously to all the cases. Each case must be labeled by an integer or character constant or constant expression. If a case matches the expression value, execution starts at that case. The case labeled default is executed if none of the other cases is satisfied. Default is optional. If it isn't there and none of the cases matches, no action at all takes place. Cases in default can occur in any order. Cases must all be different. The break statement causes an immediate exit from the switch. Because the cases serve as labels, after the code for one case is done, execution falls through to the next unless you take explicit action to escape. Break and return are the most common ways to leave a switch. A break statement can be used to force an immediate exit from a while, for, and do loops, as well as will be discussed later in this chapter. Falling through the cases is a mixed blessing. On the positive side, it allows multiple cases for a single action, as with blank tab or new line in this example. But it also implies that normally each case must end with a break to prevent falling through to the next. Falling through from one case to another is not robust, being prone to disintegration when the program is modified. With the exception of multiple labels for a single computation, fall-throughs should be used sparingly. As a matter of good form, put a break after the last case, in this case default, although it's logically unnecessary. Someday, when another case gets added at the end, this bit of defensive programming will save you. The switch statement. What is there to say? I think that the switch statement was added to C to compete with the earlier Fortran computed goto statement, or just to keep low-level assembly language programmers from switching into assembly language to implement the concept of a branch table. The authors spend most of the previous section apologizing for the switch statement, so you should perhaps take this as a hint and never use it. There are very few situations where a branch table outperforms a series of this if-then-else checks, and those are likely deep in a library or operating system code. Programmers should only use switch if they understand what a branch table is and why a branch table is more efficient for the particular bit of a program they're writing. Otherwise, just use else if and do the readers of your code a favor. 3.5 loops, while and for. We have already encountered the while and for loops. In while open parenthesis expression close parenthesis statement, the expression is evaluated. If it is non-zero, the statement is executed and the expression is reevaluated. This cycle continues until the expression becomes a zero, at which point execution resumes after the statement. The for statement, for open parenthesis expression 1 semicolon, expression 2 semicolon, expression 3 close parenthesis statement is equivalent to expression 1 semicolon while open parenthesis expression 2 close parenthesis open curly brace statement expression 3 semicolon close curly brace. Grammatically, the three components of the for are expressions. Most commonly, expression 1 and expression 3 are assignments or function calls, and expression 2 is a relational expression. Any of the three parts can be omitted, although the semicolons must remain. If expression 1 or expression 3 is left out, it is simply dropped from the expansion. If the test expression 2 is not present, it is taken as permanently true. So, the code for open parenthesis semicolon semicolon close parenthesis open curly brace close curly brace is an infinite loop, presumably to be broken by some other means such as a break or a return. Whether to use while or for is largely a matter of taste. For example, in the code, while open parenthesis C equals getchar open close parenthesis equal quote space quote, or C quote backslash n quote, or C quote backslash T quote close parenthesis semicolon, skipping white characters, there is no initialization or reinitialization, so a while seems more natural. The for is clearly superior when there is simple initialization and reinitialization, since it keeps the loop control statements close together and visible at the top of the loop. This is the most obvious in for open paren I equals 0 semicolon I less than n semicolon I plus plus close paren, which is the C idiom for processing the first n elements of an array, the analog of a Fortran or PL1 do loop. The analogy is not perfect, however, since the limits of a for loop can be altered within the loop and the controlling variable I retains its value when the loop terminates for any reason. Because the components of the for are arbitrary expressions, for loops are not restricted to arithmetic progressions. Nonetheless, it is bad style to force unrelated computations into a for. It is best reserved for loop control operations. As a larger example, here is another version of the a to I function for converting a string to its numeric equivalent. This one is more general. It copes with optional leading white space and an optional plus or minus sign. Chapter 4 shows A to F, which does the same conversion for floating point numbers. The basic structure of the program reflects the form of the input. Skip white space if any, get the sign if any, get the integer part, and convert it. Each step does its part and leaves a clean slate for the next. The whole process terminates on the first character that would not be part of a number. This is the first example on page 58 of the textbook. A to I, open paren, S, close paren, which is going to convert S to an integer. Char, S, open square bracket, close square bracket, semicolon. Open curly brace, int, I, comma, n, comma, sign, semicolon. For I equals 0, S sub I equal, quote, space, quote, or S sub I equals, quote, backslash, end quote, or S sub I equals, backslash, quote, backslash, T, quote, semicolon, I plus plus, semicolon. Skip white space. This is a for loop with an empty loop body. Sign equals 1, semicolon. If S sub I equal plus, or S sub I equal, quote, minus quote, close parenthesis, sign equals, and here we use a ternary operator, open parenthesis, S sub I plus plus, equal, quote, plus quote, close parenthesis, question mark, 1, colon, minus 1, semicolon. For, open parenthesis, n equals 0, semicolon, S sub I greater than or equal to, quote, 0, quote, and S sub I less than or equal to, quote, 9, quote, I plus plus, close parenthesis. N equals 10 times n plus S sub I minus, quote, 0, quote, semicolon. Return, open parenthesis, sign times n, close parenthesis, semicolon. Close curly brace to end the function. The advantages of keeping loop control centralized are even more obvious when there are several nested loops. The following function is a shell sort for sorting an array of integers. The basic idea of the shell sort is that in early stages, far apart elements are compared rather than adjacent ones, as in simple interchange sorts. This tends to eliminate large amounts of disorder quickly, so later stages have less work to do. The interval between the compared elements is gradually decreased to 1, at which point the sort becomes effectively an adjacent interchange method. This sample code is the second example in page 58 of the textbook. Shell, open parenthesis, v, comma, n, close parenthesis, int, v, open square bracket, close square bracket, comma, n, semicolon. Open curly brace, int, gap, comma, I, comma, j, comma, temp. For, open paren, gap equals n divided by 2, semicolon, gap greater than 0, semicolon, gap slash equals 2, close parenthesis. For, open parenthesis, I equals gap, semicolon, I less than n, I plus, close parenthesis. For, and now we're 3 deep nested in the for loops. For, open parenthesis, j equals I minus gap, semicolon, j greater than or equal to 0, and v sub j greater than v sub j plus gap, semicolon, j minus equals gap, close parenthesis, open curly brace, temp equals v sub j. V sub j equals v sub j plus gap, semicolon, v sub j plus gap equals temp, semicolon. Just a swap of v and v sub j plus gap, v sub j and v sub j plus gap. Close curly brace, and that closes the innermost for loop, and then the next close curly brace closes the function. There are 3 nested loops. The outermost loop controls the gap between the compared elements, shrinking it from n over 2 by a factor of 2 each pass until it becomes 0. The middle loop compares each pair of elements that is separated by gap. The innermost loop reverses any elements that are out of order. Since gap is eventually reduced to 1, all elements are eventually ordered correctly. Note that the generality of the for makes the outer loop fit the same form as the others, even though it is not an arithmetic progression. One final C operator is the comma, which most often finds use in the for statement. A pair of expressions separated by a comma is evaluated left to right, and the type and value of the result are the type and value of the right operand. Thus, in a for statement, it is possible to place multiple expressions in the various parts. For example, to process two parallel indices. This is illustrated in the function reverse, which reverses the function string in place. This code is from page 59 of the textbook, and it is the first example on page 59. Pound include less than string.h greater than. Reverse open paren s close paren. Char s open square bracket close square bracket semicolon. Open curly brace. Int c comma I comma j. For open parenthesis I equals 0 comma j equals strlen sub s minus 1 semicolon. I less than j semicolon. I plus plus comma j minus minus close parenthesis open curly brace. C equals s sub I equals s sub j semicolon, s sub j equals c semicolon, close curly brace to end the function. The commas that separate the function arguments, variables, declarations, etc., are not comma operators and do not guarantee left to right evaluation. Section 3.6, loops, do while. The while and for loops share the desirable attribute of testing the termination condition at the top rather than at the bottom, as we discussed in Chapter 1. The third loop in C, the do while, tests at the bottom after making each pass through the loop body. The body is always executed at least once. The syntax is as follows. Do statement while open parenthesis expression close parenthesis semicolon. The statement is executed, then the expression is evaluated. If it is true, statement is evaluated again, and so on. If the expression becomes false, the loop terminates. As might be expected, do while is much less used than while and for, accounting perhaps 5% of all loops. Nonetheless, it is from time to time valuable as in the following function I to A, which converts a number to a character string, the inverse of A to I. The job is slightly more complicated than it might be thought at first, because the easy methods of generating the digits generate them in the wrong order. We have chosen to generate the string backwards and then reverse it. This is the first sample code on page 60 of the textbook. I to A, open parenthesis, n comma s, close parenthesis. Char s, open square bracket, close square bracket, semicolon. Int n semicolon. Open curly brace. Int I comma sign semicolon. If open parenthesis, sign equals n, close parenthesis, less than 0, close parenthesis, n equals minus n semicolon. That's a bit of a complex if, I would say there. It has an assignment statement that both copies n into sign and then evaluates as to whether or not it's less than 0. The n or sign is less than 0 because it's a side effect assignment statement with a residual value. But the net result is sign contains n, and then it's negated. Then n is made positive. So, continuing. I equals 0, semicolon. Do, open curly brace, s sub I plus plus equals n modulo 10 plus quote 0 quote semicolon. Close curly brace. While parenthesis n slash equals 10 close parenthesis greater than 0 close parenthesis semicolon. If open parenthesis sign less than 0 close parenthesis s sub I plus plus equals quote dash quote or minus sign semicolon. S sub I equals quote slash 0 quote semicolon, in a sense to terminate the string, and then we call the function reverse open parenthesis s close parenthesis semicolon close curly brace. The do while is necessary, or at least convenient, since at least one character must be installed in the array s regardless of the value of n. We have also used braces around the single statement that makes up the body of the do while, even though they are unnecessary, so the hasty reader will not mistake the while part for the beginning of a while loop. I would note that it's important for any language to provide top-tested loops and bottom-tested loops. But don't feel bad if you write code for years and never feel like a bottom-tested loop is the right way to solve a problem you're facing. It is usually rare to write a loop that you insist will run once regardless of its input data. Section 3.7, Break. It is sometimes convenient to be able to control loop exits other than by testing at the top or the bottom. The break statement provides an early exit from a for, while, or do, just as it does from the switch statement. A break statement causes the innermost enclosing loop or switch to be exited immediately. The following program removes trailing blanks and tabs from the end of each line of input using a break to exit from a loop when the rightmost character is non-blank, non-tab is found. This example code is on page 61 of the textbook, and it is the first example on that page. Pound include less than stdio.h, pound define max line 1000, main open parenthesis, close parenthesis, open curly brace, int n semicolon, char line open bracket, max line close bracket, semicolon. While open paren, n equals get line, open paren, line, comma, max line, close paren, greater than 0, close paren, open curly brace. While open parenthesis, minus n greater than or equal to 0, close parenthesis. If, open parenthesis, line sub n not equal quote space quote, and line sub n not equal quote backslash t quote, and line sub n not equal quote backslash n quote, close parenthesis, break. Line sub n plus 1 equals quote backslash 0 quote semicolon, printf double quote %s backslash n double quote comma line close parenthesis semicolon. Close curly brace to end the while, and then close curly brace to end the main. Get line returns the length of the line. The inner while loop starts at the last character of line. Recall that -n decrements n before using the value and scans backward looking for the first character that is not a blank tab or new line. The loop is broken when 1 is found, or when n becomes negative, that is, when the entire line has been scanned. You should verify that this is the correct behavior, even when the line contains only whitespace characters. An alternative to break is to put the testing in the loop itself. While, open parenthesis, n equals get line, open parenthesis, line, comma, max line, close parenthesis, greater than 0, close parenthesis, open curly brace. While, open paren, minus n greater than or equal to 0, and open paren, line sub n equal, quote space, quote, or line sub n equals, quote, backslash t, quote, or line sub n equals, quote, backslash n, quote, close paren, semicolon, dot, close curly brace. This is inferior to the previous version because the test is harder to understand. Tests which require a mixture of and, or, not, and parentheses should generally be avoided. 3.8 Continue. The continue statement is related to break, but less often used. It causes the next iteration of the enclosing loop, for, while, or do, to begin. In the while and do, this means that the test part is executed immediately. In the for, control passes to the reinitialization step. By the way, continue applies only to loops, not to switch. A continue inside a switch statement inside of a loop causes the next loop iteration. As an example, this fragment processes only positive elements in the array A. Negative values are skipped. For, open paren, I equals 0, semicolon, I less than n, semicolon, I plus plus, close paren, open curly brace. If, open paren, A sub I less than 0, close paren, continue. This line skips the negative elements and then the rest of the body of the loop, will run only for the positive elements of the loop, and the loop finishes with a closed curly brace. The continue statement is often used when part of the loop that follows is complicated, so that reversing a test and indenting another level would nest the program too deeply. It's time for a bit of an aside. Now that we have seen the break and continue language structures in C that also have made it into C-like languages and learned about middle-tested loops, it is time to revisit the structured programming debate and the need for priming operations when a program must process all data until it finishes and still handle the there is no data at all situation. In the previous chapter, the authors somewhat skirted the issue by using a top-tested while loop and a side effect statement with residual value that was compared to EOF to decide when to exit the loop. Int C : while open parenthesis C equals getchar open paren close parenthesis not equal EOF close parenthesis open curly brace process your data close curly brace. And just for fun, now that we do know about the for loop, let's rewrite this loop as a for loop to make sure we really understand how for loops work. Int C : for open paren C equals getchar open paren close paren C not equal EOF C equals getchar open paren close paren curly brace process your data close curly brace for the for loop. Now you will almost never see a read all characters until EOF written this way because it is not the way K&R told us. K&R told us to use a while loop for this. But the for loop formulation is probably clearer to many than the while formulation, especially to a reader who is not familiar with the assignment side effect idiom commonly used in C. In particular, the for formulation does not require that the assignment statement has a residual value of the value that was assigned. The first part of the for is a priming read. The second part of the for is a top-tested exit criteria that works both for no data and after all data has been read and processed. And the third part of the for is done at the bottom of the loop to advance to the next character or encounter EOF before going back to the top and doing the loop test. The call to getchar is done twice in the for formulation of the read all available data loop, and while we don't like to repeat ourselves in code, if it is a small and obvious bit of code, perhaps this code is more clear with a bit of repetition. So, with all this as background, you can take this page of the document and sit down with a friend at a coffee shop and debate as long as you like about which is the better formulation for the read all available data. But if at that coffee shop you ask Dr. Chuck's opinion, neither of these is ideal because in the real world, we build data-oriented loops that usually do a lot more than get one character from standard input. My formulation of a data loop will upset the structured programming purists and probably upset Kernigan and Ritchie as well. But I write code in the real world, so here is my version. Int C : while open paren 1 close paren open curly brace C equals getchar if open paren C double equals EOF close paren break process your data and then close curly brace to end the loop. And if I wanted to skip blanks and new lines, I could use both break and continue, further angering the structured programming purists. Int C : while open parenthesis 1 close parenthesis open curly brace C equals getchar open parenthesis close parenthesis if open parenthesis C equal EOF close parenthesis break if open parenthesis C equal quote space quote or C equal quote backslash end quote close parenthesis continue, then process your data close parenthesis. I use this middle tested approach because usually the data I am processing is coming from a more complex source than the keyboard, and I don't want a function with 2 to 3 parameters stuck inside of a side effect statement in a while test. And also sometimes you want an exit loop not just based on the return value from the function, but instead based on the complex structure that came back from the function itself. As these data processing loops get more complex, the middle tested loop is a tried and true pattern. Even Kernigan and Ritchie point out its benefits above. And with that, I have now triggered endless coffee shop conversations about the best way to write a data handling loop. Section 3.9, Go-Tos and Labels. C provides the infinitely abusable go-to statement and labels to branch to. Formally, the go-to is never necessary, and in practice, it is almost always easy to write code without it. We have not used go-to in this book. Nevertheless, we will suggest a few situations where go-tos might find a place. The most common use is to abandon processing in some deeply nested structure, such as breaking out of two loops at once. The break statement cannot be used directly since it leaves only the most innermost loop. Thus, for open parenthesis, close parenthesis, for open parenthesis, close parenthesis, open curly brace, do some stuff, if open parenthesis, disaster, close parenthesis, go to error, semicolon, close curly brace, and then error, colon, and then clean up the mess. This organization is handy if the error handling code is non-trivial and if errors can occur in several places. A label has the same form as a variable name and is followed by a colon. It can be attached to any statement in the same function as the goto. Another example, consider the possibility of finding the first negative element in a two-dimensional array. Multi-dimensional arrays are discussed in Chapter 5. One possibility is for open parenthesis I equals 0, semicolon, I less than n, semicolon, I plus plus, close parenthesis, for open parenthesis j equals 0, semicolon, j less than m, semicolon, j plus plus, close parenthesis, if open parenthesis v sub I sub j less than 0, close parenthesis, go to found. Otherwise, and then you handle, and you keep going. And then found colon is where it comes to, jumps to. Code involving a goto can always be written without one, but though perhaps at the price of somewhat repeated tests or an extra variable. For example, the array search becomes found equals 0. For open parenthesis I equals 0, semicolon, I less than n, ampersand, ampersand, exclamation, found, semicolon, I plus plus. For open parenthesis j equals 0, semicolon, j less than m, ampersand, ampersand, exclamation, found, semicolon, j plus plus. Found equals v sub I sub j less than 0. If found, continue, else not found. Although we are not dogmatic about the matter, it does seem that go-to statements should be used sparingly, if at all. I would add, before we leave control flow, I need to say that I agree with structured programming experts as well as Kernigan and Ritchie in that the go-to is universally a bad idea. There are a lot of little details that make them a real problem. Things like how the stack works in function calls and how code blocks happen and patching the stack up correctly when a go-to happens in the middle of a deeply nested mess. You might be tempted to use a go-to when you want to exit multiple nested loops in a single statement. Break and continue only exit the innermost loop. The authors use this example above, but are quite lukewarm when describing it as the use of goto. Usually, if your problem is that complex, putting things in a function and using return or adding a few if statements is a better choice. The Dr. Chuck middle-tested loop data processing solves this because the loop is always the innermost loop. Also, as new languages were built, the concept of exceptions became part of language design and was a by far more elegant solution to a path of some deeply nested code that just needs to get out. So most of the time, you think that goto might be a good idea, you should lean towards a throw-catch pattern to make your intention clear. It is one of the reasons why we prefer languages like Java or Python over C when writing general-purpose code. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 4, Functions in Program Structure. Functions break large computing tasks into smaller ones and enable people to build on what others have done instead of starting over from scratch. Appropriate functions can often hide details of operation from parts of the program that don't need to know about them, thus clarifying the whole and easing the pain of making changes. C has been designed to make functions efficient and easy to use. C programs generally consist of numerous small functions rather than a few big ones. A program may reside on one or more source files in any convenient way. The source files may be compiled separately and loaded together, along with previously compiled functions from libraries. We will not go into that process here, since the details vary according to the local system. Most programmers are familiar with library functions for input and output, like getChar and putChar, and numerical computations like sine, cosine, and square root. In this chapter, we will show more about writing new functions. 4.1 Basics. To begin, let us design and write a program to print each line of input that contains a particular pattern or string of characters. This is a special function of the UNIX utility program grep. For example, searching for the pattern the in the set of lines, now is the time for all good men to come to the aid of their party, will produce the output, now is the time men to come to the aid of their party. The basic structure of the task falls neatly into three pieces. While there's another line, if that line contains a pattern, print it. Although it's certainly possible to put the code for all of this in one main routine, a better way is to use the natural structure to advantage by making each part a separate function. Three small pieces are easier to deal with than the one big one, because irrelevant details can be buried in the functions, and the chance of unwanted interactions minimized. And the pieces might even be useful later in their own right. While there is another line is getLine, a function we wrote in Chapter 1, and printit is printf, which someone has already provided for us. This means that we need to only write a routine which decides if the line contains an occurrence of the pattern. We can solve that problem by stealing a design from PL1. The function index s, t returns the position or index in the string s where the string t begins, or -1 if s doesn't contain t. We use 0 rather than 1 as the starting position in s because C arrays always begin at position 0. When we later need more sophisticated pattern matching, we only have to replace index. The rest of the code can remain the same. Recall that because the modern stdout.h defines a getLine function, whenever the book writes this function to teach a feature of functions, we rename it to get_line. Given this much design, filling in the details of the program is straightforward. Here's the whole thing, so you can see how the pieces fit together. For now, the pattern to be searched for is a literal string in the argument of index, which is not the most general of mechanisms. We will return shortly to a discussion of how to initialize character arrays, and in Chapter 5, we will show how to make the pattern a parameter that is set when the program is run. This is also a new version of getLine. You might find it instructive to compare it to the one in Chapter 1. Pound include stdio.h. Pound define maxLine 1000. Main, open parenthesis, close parenthesis, open curly brace. Char line, open square bracket, maxLine, close square bracket, semicolon. While, parenthesis, getLine, open parenthesis, line, comma, maxLine, close parenthesis, greater than 0, close parenthesis, if, open parenthesis, index, open parenthesis, line, comma, double quote, the, double quote, close parenthesis, greater than or equal to 0, close parenthesis, printf, open parenthesis, double quote, %s, double quote, comma, line, close parenthesis, semicolon, and a closed curly brace to finish the main function. Next function is getLine. GetLine, open parenthesis, s, comma, lim, close parenthesis. Char s, open square bracket, close square bracket, semicolon. Int lim, semicolon. Open curly brace. Int c, comma, I, semicolon. For I equals 0, semicolon, I less than lim minus 1, and paren c equals get char, open paren, close paren, not equal EOF, double ampersand, c not equal, double quote, backslash n, double quote, semicolon, plus plus I, close parenthesis, s sub I equals c. That loop basically read until it found a new line or end of file. If, open parenthesis, c double equals, quote, backslash n, quote, close parenthesis, open curly brace, s sub I equals c, plus plus I, semicolon, close curly brace, closing the if. S sub I equals, quote, backslash 0, quote, semicolon, to terminate the string properly. Return, open paren, I, close paren, semicolon, to return the length of the line, and then close curly brace to finish the getLine function. And now the new code. Index, open parenthesis, s, comma, t, close parenthesis. Char, s, open square bracket, close square bracket, comma, t, open square bracket, close square bracket, semicolon. I would note that when we are declaring a character array and we don't give the length of the array, that means that we're inside of a function. The length of the array exists, but it was from the calling code. So char, s, open square bracket, close square bracket, t, open square bracket, close square bracket, semicolon means parameters s and t are strings of some length, and we will use backslash 0 to know when that length is done. Beginning the code in index with an open curly brace. Int I, comma, j, comma, k, semicolon. And then we have two nested for loops. For open paren I equals 0, s sub I not equal to, quote, backslash 0, quote, semicolon, I plus plus, open curly brace. For j equals I, comma, k equals 0, semicolon, t sub k not equal to backslash 0, and, double ampersand, s sub j double equals t sub k, semicolon, j plus plus, k plus plus, semicolon. If open paren t sub k double equals, quote, backslash 0, quote, close paren, return open paren I, close paren, semicolon, close curly brace, return open paren minus 1, close paren, semicolon, curly brace. Each function has the form, name, argument list, if any, in parentheses, argument declarations, if any, open curly brace, declarations and statements, if any, close curly brace. As suggested, various parts may be absent. A minimal function is dummy, open paren, close paren, open curly brace, close curly brace, which does nothing. A do-nothing function is sometimes useful as a placeholder during program development. The function name may also be preceded by a type if the function returns something other than an integer value. This is the topic of the next section. A program is just a set of individual function definitions. Communication between the functions is, in this case, by arguments and values returned by the functions. It can also be via external variables. The functions can occur in any order in the source file, and the source program can be split into multiple files, so long as no function is split. The return statement is the mechanism for returning a residual value from the called function to its caller. Any expression can follow return. Return, open parenthesis, expression, close parenthesis. The calling function is free to ignore the returned value if it wishes. Furthermore, there is no need to have an expression after the return. In that case, no value is returned to the caller. Control also returns to the caller with no value when execution falls off the end of the function by reaching the right closing brace. It is not illegal, but probably a sign of trouble if a function returns a value from one place and no value from another place. In any case, the residual value of a function which does not return one is certain to be garbage. The C verifier lint checks for such errors. The mechanics of how to compile and load a C program which resides on multiple source files vary from one system to the next. On the UNIX system, for example, the cc command mentioned in Chapter 1 does the job. Suppose that three functions are in three files called main.c, getLine.c, and index.c. Then the command cc main.c, getLine.c, index.c compiles the three files and places the resulting relocatable object code in files main.o, getLine.o, and index.o, and loads them all into an executable file named a.out. If there is an error, say in main.c, that file can be recompiled by itself and the result loaded with the previous object files with the command cc main.c, getLine.o, index.o. The cc command uses the .c suffix versus the .o suffix naming convention to distinguish source files from object files. I would note that this cc example, exactly as the authors wrote it, does not quite work as described in modern C compilers. If you want to compile your source code and leave the compiled object code around after the compile, you add the -c option to the compiler call. Modern C compilers generally do accept multiple files with either .c or .o suffixes and combine them into a runnable application. Section 4.2, Functions Returning Non-Integers. So far, none of our programs has contained any declaration of the type of a function. This is because, by default, a function is implicitly declared by its appearance in an expression or statement, such as while, open paren, get line, open paren, line, comma, max line, close paren, greater than 0, close paren. If a name which has not been previously declared occurs in an expression and is followed by a left parentheses, it is declared by context to be a function name. Furthermore, by default, the function is assumed to return an int. Since char promotes to int in expressions, there is no need to declare functions that return char. These assumptions cover the majority of classes, including all of our examples so far. I would add, that's not quite true anymore. In modern C languages, you are required to provide a type for each function. If you leave off the type for a function declaration, at a minimum, you will get a stern warning message. But sometimes functions do not intend to return anything at all, and so the void type was invented to indicate that a function returns nothing. The rule of requiring a type on a modern function definition in C, even if it's void, allows the compiler to check to make sure all of your return values in a function match the expected return type. Back to the text. But what happens if a function must return some other type? Many numerical functions like square root, sine, and cosine return double. Other specialized functions return other types. To illustrate how to deal with this, let us write and use the function a to f, which converts its argument string s to its double precision floating point equivalent. A to f is an extension of a to I, which we wrote versions of in chapters 2 and 3. It handles an optional sign and decimal point and the presence or absence of either the integer or fractional part. We note that this is not a high-quality input conversion routine. Doing everything takes a bit more space than we care to use here in this book. First, a to f must declare the type of the value it returns since it's not int. Because float is converted to double in expressions, there is no point in saying that a to f returns float. We might as well make use of the extra precision and thus declare it to return double. The type name precedes the function name, like this. Double, a to f, open parenthesis, s, close parenthesis. Char, s, open square bracket, close square bracket, open curly brace. Double, val, comma, power, int, I, comma, sign, semicolon. For, I equals 0, semicolon, s sub I, double equals, quote, space, quote, or s sub I, double equals, quote, backslash n, quote, or s sub I double equals quote backslash t quote semicolon I plus plus semicolon. That skips the white space. Sign equals 1. If s sub I double equals quote plus quote, or s sub I double equals quote minus quote, sign equals, and now we're going to use a ternary operator here, paren s sub I plus plus, close bracket, double equals quote plus quote, close paren, question mark, 1 colon minus 1 semicolon. And that basically tells us it makes sign be 1 or negative 1 based on the presence or absence of a plus or minus. For val equals 0 semicolon, s sub I greater than or equal to quote 0 quote, double ampersand, s sub I less than or equal to double quote 9 quote I plus plus, close paren. Val equals 10 times val plus s sub I minus quote 0 quote semicolon. What this is doing is multiplying the current value by 10, in effect shifting it left, and then adding in that new lower empty spot the digit that we're encountering, which is somewhere between the character 0 and the character 9. Continuing, if parenthesis s sub I double equals quote dot quote, close parenthesis, I plus plus. For open parenthesis power equals 1 semicolon, s sub I greater than or equal to quote 0 quote, double ampersand, s sub I less than or equal to quote 9 quote semicolon I plus plus, open curly brace, val equals 10 times val plus s sub I minus quote 0 quote. Again, shifting the number to the left as we encounter characters. Power star equals 10 semicolon, close curly brace. Return, open parenthesis, sign times val over power, close parenthesis, semicolon. Close curly brace. Second, and just as important, the calling routine must state that A to F returns a non-int value. The declaration is shown in the following primitive desk calculator, barely adequate for checkbook balancing, which reads one number per line, optionally preceded by sign, and adds them all up, printing the sum after each input. This example is from page 70 of the textbook. Pound include stdio.h. Pound define max line 100. Main, open parenthesis, close parenthesis. Open curly brace. Double, sum, comma, A to F, open parenthesis, close parenthesis, semicolon. Char, line, open square bracket, max line, close square bracket, semicolon. Sum equals 0. While, open parenthesis, get line, open parenthesis, line, comma, max line, close parenthesis, greater than 0, close parenthesis, print f, quote, backslash t, percent dot to f backslash n, comma, sum plus equals A to F, open parenthesis, line, close parenthesis, semicolon, close curly brace. That code used the plus equals side effect operator and merged the call to A to F right into the parameter of the second parameter of printf. The declaration double sum A to F open parenthesis close parenthesis says that sum is a double variable and that A to F is a function that returns a double value. As a mnemonic, it suggests that sum and A to F parenthesis ... are both double precision floating point values. Unless A to F is explicitly declared in both places, C assumes it returns an integer, and you will get nonsense answers. If A to F itself and the call to it in main aren't typed inconsistently in the same source file, it will be detected by the compiler. But if, as is more likely, A to F were compiled separately, the mismatch would not be detected, and A to F would return a double, which main would treat as an int, and meaningless answers would result. Lint catches this error. Given A to F, we could, in principle, write A to I to convert a string to an integer in terms of it. Int A to I, open parenthesis, S, close parenthesis, char, S, open square bracket, close square bracket, semicolon, open curly brace, double, A to F, open parenthesis, close parenthesis, semicolon. Return, open parenthesis, A to F, close parenthesis, S, close parenthesis, semicolon, close curly brace. Note the structure of the declarations in the return statement. The value in the expression in return expression is always converted to the type of the function before the return is taken. Therefore, the value of A to F, a double, is converted automatically to int when it appears in a return, since the function A to I returns an int. The conversion of a floating point value to int truncates any fractional part, as we discussed in Chapter 2. More on function arguments. In Chapter 1, we discussed the fact that function arguments are passed by value. That is, the called function receives a private, temporary copy of each argument, not its address. This means that the function cannot affect the original argument in the calling function. Within a function, each argument is in effect a local variable initialized to the value with which the function was called. When an array name appears as an argument to a function, the location of the beginning of the array is passed. Elements are not copied. The function can alter elements of the array by subscripting from this location. The effect is that arrays are always passed by reference. In Chapter 5, we will discuss the use of pointers to permit functions to affect non-arrays in calling functions. A bit of a digression. Since including array as an argument passes the location or memory address of the array into the function can change the items in the array using array subscripts. In particular, the array contents are not copied when an array is passed into a C function. When we get to structs in a future chapter, we will find that the content of structs also are passed using the address of the entire struct, so structs are passed by reference as well. When thinking about pass by reference or pass by value, remember that a char variable is a single item similar to int and passed by value, i.e. it is copied. In C, strings are arrays of characters, so they are passed by reference. Python follows this design for the same efficiency reason as C. Normal single variables like int or float are copied before being passed into a function and therefore passed by value. Collections, like list or dict, are passed into functions by reference, so the contents can be changed within a function. Python strings are not technically copied when being passed into a function, but the way assignments happen in Python make it seem like strings are passed by value, since they can never be modified. You can learn more with a bit of web research, but the easy way is to imagine in Python that strings are passed by value with a clever trick to avoid requiring a copy for every function call. PHP follows the same pattern of passing numbers and strings by value and passing arrays as reference. PHP passes strings by value without requiring a copy, again using clever runtime code. Because in Java, JavaScript, and PHP, strings are objects, of course, which we haven't discussed much yet. Those languages can make sure that strings act as if they were passed by value and not passed by reference, the way they are always passed in C. C made decisions on its runtime based on getting the maximum performance out of the hardware of the 1970s at the expense of making it too easy to write code that overwrites memory and leads to corrupted programs that have dangerous and undefined behavior. Languages like PHP, Java, and JavaScript add a small amount of runtime overhead to do things like store the length of an array and make sure we programmers don't over-reference the array and overwrite random bits of our program's code or data. The creators of C placed more priority on speed and efficient use of memory than safety. It is like driving an automobile in the rain without ABS, automatic braking system. It is fast but dangerous and should be reserved by highly skilled and very careful programmers and drivers, and those drivers should probably be on a race course. By the way, back to the text. By the way, there is no entirely satisfactory way to write a portable function that accepts a variable number of arguments, because there is no portable way for the called function to determine how many arguments were actually passed in a given call. Thus, you can't write a truly portable function that will compute the maximum of an arbitrary number of arguments, as will the max functions that are built into Fortran and PL1. It is generally safe to deal with a variable number of arguments if the called function doesn't use an argument that was not actually supplied, and if the types are consistent. Printf, the most common C function with a variable number of arguments, uses information from the first argument, which is the formatting string, to determine how many other arguments are present and what their types are. It fails badly if the caller does not supply enough arguments or if types are not what the first argument says. It is also non-portable and therefore must be modified for different programming environments. Alternatively, if arguments are of known types, it is possible to mark the end of the argument list in some agreed-upon way, such as a special argument value, often 0, that stands for the end of the arguments. Interestingly, modern languages like Python, PHP, and Java go to great lengths to make variable-length argument lists work predictably and portably. The syntax for variable-length argument lists in these languages can be a bit obtuse at times, but at least it's allowed, documented, reliable, and portable. Section 4. External variables. A C program consists of a set of external objects which are either variables or functions. The adjective external is used primarily in contrast to internal, which describes arguments and automatic variables defined inside functions. External variables are defined outside any function and are thus potentially available to many functions. Functions themselves are always external because C does not allow functions to be defined inside other functions. By default, external variables are also global, so that all references to such a variable by the same name, even from functions that are compiled separately, are references to the same thing. In this sense, external variables are analogous to Fortran Common or PL1 external. We will later see how to define external variables in functions that are not globally available, but instead only visible within a single source file. Because external variables are globally accessible, they provide an alternative to function arguments and return values for communicating data between functions. Any function may access an external variable by referring it to by name, if the name has been declared somehow. If a large number of variables must be shared among functions, external variables are more convenient and efficient than long argument lists. As pointed out in Chapter 1, however, this reasoning should be applied with some caution, for it can have a bad effect on program structure and lead to programs with many data connections between functions. A second reason for using external variables concerns initialization. In particular, external arrays may be initialized, but automatic, i.e. internal arrays, may not. We will treat initialization near the end of this chapter. The third reason for using external variables is their scope and lifetime. Automatic variables are internal to a function. They come into existence when the routine is entered and disappear when it's left. External variables, on the other hand, are permanent. They do not come and go, so they retain values from one function invocation to the next. Thus, if two functions must share some data, yet neither calls the other, it is often most convenient if the shared data is kept in external variables rather than passed in and out via arguments. Let's examine this issue further with a larger example. The problem is to write another calculator program better than the previous one. This one permits plus, minus, asterisk, and slash, and equals. Equals will print our answer. Because it is somewhat easier to implement, the calculator will use reverse Polish notation instead of infix notation. Reverse Polish notation is the scheme used by, for example, Hewlett-Packard Pocket calculators. In reverse Polish notation, each operator follows its operands. An infix expression like open parenthesis 1 minus 2, close parenthesis C star, open parenthesis 4 plus 5, close parenthesis equals, is entered as 1, 2 minus 4, 5 plus star equals. Parentheses are not needed in reverse Polish notation. The implementation is quite simple. Each operand is pushed onto a stack. When an operator arrives, the proper number of operands, 2 for binary operators, are popped, the operator applied to them, and the result is pushed back onto the stack. In the example above, 1 and 2 are pushed, then replaced by their difference, -1. Next, 4 and 5 are pushed, then replaced by their sum, 9. And then the product of -1 and 9, which is -9, replaces them on the stack. And then the equal sign operator prints the top element without removing it. So intermediate steps in a calculation can be checked. The operations of pushing and popping a stack are trivial, but by the time error detection and recovery are added, they're long enough so it's better to put each in a separate function than to repeat the code throughout the whole program. And there should be a separate function for fetching the next input operator or operand. Thus, the overall structure of the program is while next operator or operand is not end of file. If it's a number, push it. Else, if it's an operator, pop operands, do the operation, and push the result. Else, error. The main design decision that has not yet been discussed is where the stack is. That is, what routines access it directly. One possibility is to keep it in main and pass the stack and current stack position to the routines that push and pop it. But main doesn't need to know about the variables that control the stack. It should only think about pushing and popping. So we have decided to make the stack and its associated information external variables accessible to push and pop, but not to main. Translating this outline to code is easy enough. The main program is primarily a big switch on the type of operator or operand. This is a more typical use of switch than the one shown in Chapter 3. This sample code is from page 74 of the textbook. Pound include stdio.h. Pound define maxop 20. Pound define number, quote 0, quote. This is going to be a signal we found a number. And pound define too big, quote 9, quote. A signal that the string is too big. Main, open parenthesis, close parenthesis. Open curly brace. Int, type, semicolon. Char, s, open square bracket, maxop, close square bracket, semicolon. Double, op2, a to f, open parenthesis, close parenthesis, comma, pop, open parenthesis, close parenthesis, comma, push, open parenthesis, close parenthesis, semicolon. While, open parenthesis, type equals getUp, open parenthesis, s, comma, maxop, close parenthesis, not equal EOF, close parenthesis. Switch, open parenthesis, type, close parenthesis, open curly brace. Case, number, colon. Note that number is a predefined constant above. Push, open parenthesis, a to f, open parenthesis, s, close parenthesis, semicolon, break. Case, quote plus quote, colon. Push, open parenthesis, pop, open paren, close paren, plus pop, open paren, close paren, semicolon. Break, semicolon. Case, quote, asterisk, quote, colon. Push, open paren, pop, open paren, close paren, asterisk, pop, open paren, close paren, semicolon, break, semicolon. That was the multiplication. Case, quote, minus quote, colon. Op2 equals pop, open paren, close paren. Push, open paren, pop, minus op2, close paren, semicolon. Break, semicolon. That was subtraction. Case, open paren, slash, close paren, colon. Op2 equals pop, open paren, semicolon. If op2 not equals 0.0, push, open paren, pop, open paren, close paren, slash, op2, close paren, semicolon. Else, printf, double quote, 0 divisor popped, backslash n, double quote, close paren, semicolon, break. Case, quote, equal, quote, colon, printf, open paren, double quote, backslash t, %f, backslash n, double quote, comma, push, open paren, pop, open paren, close paren, semicolon. So to print it, we pop it and push it, and then print the residual value of the push function. The next line is break, semicolon. Case, quote, C, quote, colon, clear, open paren, close paren, semicolon, break, semicolon. Case, too big, colon, printf double quote %.20s space dot 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 is too long \n double quote comma s close paren semicolon break semicolon. Default colon printf open paren double quote unknown command %c \n double quote comma type open paren close paren semicolon break semicolon close curly brace to finish the switch statement, and then close curly brace to finish the main. So now we're going to have a separate file that has some of these functions defined. This file is on page 75 of the textbook. This file will be compiled separately, but then later linked all together with the main program. But we're going to define push, pop, and clear in this file. Pound include stdio.h. Pound define maxval 100. Maximum value, that would be the maximum value of our stack, the maximum size of our stack, maximum depth of our stack. Now we are declaring variables outside of any function. These are the external variables. Int sp equals 0, double val, open square bracket, max val, close square bracket, semicolon. And so those variables are external variables, and they're outside of all of the functions, but we can use them in any function, and there's just one copy no matter what function we're using it. So now we define our functions. Double push, open paren f, close paren, double f semicolon, open curly brace. If open paren sp less than max val, close paren, return open paren val, open square bracket, sp plus plus, close square bracket equals f, close paren, semicolon. Else, open curly brace, printf, double quote, error, colon, stack, full, \n, double quote, close paren, semicolon. Clear, open paren, close paren, semicolon. Return, open paren, 0, close paren, semicolon. Close curly brace to finish the else, and then close curly brace to finish the double function, the push function. And now we define the pop. Double pop, open paren, close paren, open curly brace. If open paren sp greater than 0, close paren, return open paren val, open square bracket, minus minus sp, close square bracket, close curly brace, semicolon. Else, open curly brace, printf, open paren, double quote, error, colon, stack, empty, \n, close quote, close double quote, close paren, semicolon. Clear, open paren, close paren, semicolon. Return, open paren, 0, close paren, semicolon. Close curly brace to finish the else, and then close curly brace to finish the double. And the last function we're going to define is the clear function, which is quite simple. Clear, open paren, close paren, open curly brace, sp equals 0, semicolon, close paren. I would note that just read this one carefully. They're very good at using side effect operators and side effect assignments, and to keep this code very simple and succinct. And you really have to understand a lot of the other stuff that you've covered in the book up to this point. Back to the text. The command C clears the stack with the function clear, which can also be used by push and pop in case of error. We'll return to getOp in a moment. As discussed in Chapter 1, a variable is external if it is defined outside the body of any function. Thus, the stack and stack pointer, which must be shared by push, pop, and clear, are defined outside the three functions. But if main itself does not refer to the stack or stack pointer, their representation is carefully hidden. Thus, the code for the equal operator must use push, open paren, pop, parenthesis, close parenthesis, semicolon, to examine the top of the stack without disturbing it. Notice also that because plus and multiplication are commutative operators, the order in which the popped operands are combined is irrelevant, but for the minus and slash operators, the left and right operands must be distinguished. This example code above shows why it's important to remember the K&R C rearrangement license as it applies to operators that are associative and commutative. If the code for the minus operator were written push, open paren, pop, open paren, close paren, minus, pop, open paren, close paren, close paren, semicolon, there is no guarantee that the left pop will run before the right pop. And since these functions access global variables and have side effects, it is important to force the compiler not to rearrange the order of the function calls. To force the evaluation order, the code is broken into two statements. Op2 equals pop, open paren, close paren, semicolon. Push, open paren, pop, open paren, close paren, minus op2, close paren, semicolon. Now you might think that the lesson here is that the K&R C arrangement license, which was done to allow optimization and performance, is a bad idea. But the more important lesson is that writing low-level utility functions like push and pop that use global variables and have side effects is a dangerous pattern in any programming language. Section 4.5, Scope Rules. The functions and external variables that make up a C program need not all be compiled at the same time. The source text of the program may be kept in several files, and previously compiled routines may be loaded from libraries. The two questions of interest are, how are declarations written so that variables are properly declared during compilation, and how are declarations set up so that all the pieces will be properly linked or connected when the program is loaded? The scope of a name is the part of the program over which the name is defined. For an automatic variable declared at the beginning of a function, the scope is the function in which the name is declared, and variables of the same name in different functions are unrelated. The same is true of the arguments of the function. The scope of an external variable lasts from the point at which it is declared in a source file to the end of that file. For example, if val, sp, push, pop, and clear are defined in one file in the order shown above, that is, int sp equals 0, double val, open square bracket, max val, close square bracket, semicolon, double push, open paren, f, close paren, open curly brace, dot, 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 close curly brace, double pop, open paren, close paren, open curly brace, dot, 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 close curly brace, clear, open paren, close paren, open curly brace, dot, 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 close curly brace, then the variables val and sp may be used in push, pop, and clear simply by naming them, and no further declarations are needed. On the other hand, if an external variable is to be referenced before it is defined, or it is defined in a different source file from the one in which it's being used, then an extern declaration is mandatory. It is very important to distinguish between the declaration of an external variable and its definition. A declaration announces the property of the variable, its type, its size, etc. A definition also causes storage to be allocated. If the lines int sp semicolon, double val, open square bracket, max val, close square bracket, semicolon, appear outside any function, they define the external variables sp and val and cause the storage to be allocated, and also serve as the declaration for the rest of that source file. On the other hand, the lines extern int sp, extern double val, open square bracket, close square bracket, semicolon, declare for the rest of the source file that sp is an int and val is a double array, whose size is determined and allocated elsewhere, but they do not create variables or allocate storage for them. There must be only one definition of an external variable among all the files that make up the source program. Other files may contain extern declarations to access it. There may also be an extern declaration in the file containing the definition. Any initialization of an external variable goes only with the definition. Array sizes must be specified with the definition, but are optional with the extern declaration. Although it is not a likely organization for this program, val and sp could be defined and initialized in one file, and the functions push, pop, and clear defined in another. Then these definitions and declarations would be necessary to tie them together. In file 1, we would see int sp equals 0 semicolon, double val, open square bracket, max val, close square bracket, semicolon, and then in file 2, extern int sp semicolon, extern double val, open square bracket, close square bracket, semicolon. double push open paren f close paren, open curly brace, dot, 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 close curly brace. Double pop open paren close paren, open curly brace, dot, 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 close curly brace. Clear open paren close paren, open curly brace, dot, 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 close curly brace. Because the extern declarations in file 2 lie ahead and outside the three functions, they apply to all. One set of declarations suffices for all of file 2. For larger programs, the #include file inclusion facility discussed later in this chapter allows one to keep only a single copy of the external declarations for the program and have that inserted in each source file as it's being compiled. Let us now turn to the implementation of getup, the function that fetches the next operator or operand. The basic task is easy. Skip blanks, tabs, and new lines. If the character is not a digit or a decimal point, return it. Otherwise, collect a string of digits that might include a decimal point and return number, a single signal that a number has been collected. The routine is substantially complicated by an attempt to handle the situation properly when the input number is too long. Getup reads digits, perhaps with an intervening decimal point, until it doesn't see anymore, but only stores the ones that fit. If there was no overflow, it returns number in the string of digits. If the number was too long, however, getup discards the rest of the input line, so the user can simply retype the line from the point of error. It returns too big as the overflow signal. This example code is from page 78 of the textbook, and you can view it at www.cc4e.com/code, page 78. Getup, open paren s comma lim, close paren, char s open square bracket, close square bracket, semicolon, int lim semicolon, open curly brace, int I comma c semicolon, while open paren c equals get ch open paren, close paren, double equals quote space quote, or c double equals quote backslash t quote, or c double equals quote backslash n quote, close paren, semicolon. Skip all the blanks. If c is not equal quote dot quote and open paren c less than quote 0 quote, vertical bar, c greater than quote 9 quote, close paren, return open paren c, close paren. S sub 0 equals c. For paren I equals 1, semicolon, open paren c equals get char, open paren, close paren, greater than or equal to quote 0 quote, and c less than or equal to quote 9 quote, semicolon, I plus plus, inside the for loop. If I less than lim, s sub I equals c. If open paren c double equals quote dot quote, close paren, open curly brace, we begin to collect the fraction. If open paren I less than lim, close paren, s sub I equals c. For open paren I plus plus, c equals get char, open paren, close paren, greater than or equal to quote 0 quote, ampersand, c less than or equal to quote 9 quote, semicolon, I plus plus, close paren. If open paren I less than lim, close paren, s sub I equals c. Close curly brace to close the if statement where we're collecting the fraction. If open paren I less than lim, close paren, open curly brace, this means the number is good, unget ch, open paren c, close paren, semicolon. S sub I equals quote backslash 0 quote, semicolon, return, open paren number, close paren, and recall that number is a predefined constant. Close curly brace, else open curly brace. If it's too big, we're going to skip to the end of the line. While open paren c not equal quote backslash n quote, and c not equal EOF, open paren c equals get char, open paren, close paren, semicolon, S sublim minus 1 equals quote backslash 0 quote semicolon. Return too big, semicolon. Close curly brace to finish the if, and then close curly brace to finish the function. Recall that too big is a constant that indicates that we've read too much. Back to the text. What are getCH and ungetCH? Well, it is often the case that a programming reading input cannot determine that it is read enough until it is read too much. One instance is collecting characters that make up a number. Until the first non-digit is seen, the number is not complete. But then the program has read one character too far, and that is a character it is not prepared for. The problem would be solved if it were possible to unread the unwanted character. Then every time the program reads one character too many, it could push it back on the input so that the rest of the code would behave as if it had never been read. Fortunately, it is easy to simulate ungetting a character by writing a pair of cooperating functions. GetCH delivers the next input character to be considered. UngetCH puts the character back on the input, so the next call to getCH will return it again. How they work together is simple. UngetCH puts the pushed back characters into a shared buffer, a character array. GetCH reads from the buffer as there's anything there, and then it calls getChar if the buffer is empty. There must be an index variable which records the position of the current character in the buffer. Since the buffer and index are shared by getCH and ungetCH and must retain their values between calls, they must be external to both routines. Thus, we can write getCH and ungetCH and their shared variables as follows. This is on page 79 of the textbook. You can see the code at www.cc4e.com/code and go to page 79. Pound include stdio.h. Pound define buff size 100. Char buff open square bracket buff size close square bracket semicolon. Int buff p equals 0 semicolon. Those were the external variables outside any function. Here's the first function. GetCH open paren close paren open curly brace return open parenthesis buff p greater than 0 close parenthesis question mark buff open square bracket minus buff p close square bracket colon getChar open paren close paren semicolon. Close curly brace to finish the getCH function. The ungetCH function pushes a character back on input. UngetCH open paren c close paren int c semicolon open curly brace. If open paren buff p greater than buff size printf open paren double quote ungetCH colon too many characters \n double quote close paren semicolon. Else buff open square bracket buff p plus close square bracket equals c semicolon, and then close curly brace to finish the ungetCH function. We have used an array for pushback rather than a single character, since the generality may come in handy later. Section 4.6, Static Variables. Static variables are a third class of storage, in addition to the extern and automatic that we've already met. Static variables may either be internal or external. Internal static variables are local to a particular function, just like automatic variables are, but unlike automatics, they remain in existence rather than coming and going each time the function is activated. This means that internal static variables provide private, permanent storage in a function. Character strings that appear within a function, such as the arguments of printf, are internal static. An external static variable is known within the remainder of the source file in which it's declared, but not in any other file. External static thus provides a way to hide names like buff and buff p in the getCH ungetCH combination, which must be external so they can be shared, yet which should not be visible to users of getCH and ungetCH, so there's no possibility of conflict. If the two routines are compiled in one file, as in static char buff open square bracket buff size close square bracket semicolon static int buff p equals 0 semicolon getCH open paren open curly brace close curly brace ungetCH open paren c close paren open curly brace close curly brace, then no other routine will be able to access buff and buff-p. In fact, they will not conflict with the same names in other files of the same program. Static storage, whether internal or external, is specified by prefixing the normal declaration with the word static. The variable is external if it's defined outside of any function, and internal if defined inside a function. Normally, functions are external objects. Their names are known globally. It is possible for a function, however, to be declared static. This makes its name unknown outside the file in which it's declared. In C, static connotates not only permanence, but also a degree of what might be called privacy. Internal static objects are known only inside one function. External static objects, variables, or function are known only within the source file in which they appear. Their names do not interfere with variables or functions of the same name in other files. External static variables and functions provide a way to conceal data objects and any internal routines that manipulate them so that other routines and data cannot conflict, even inadvertently. For example, getCH and ungetCH form a module for character input and pushback. Buff and buff-p should be static, so they are inaccessible from the outside. In the same way, push, pop, and clear form a module for stack manipulations. Val and SP should also be external static. 4.7, Register Variables. The fourth and final storage class is called register. A register declaration advises the compiler that the variable in question will be heavily used. When possible, register variables are placed in machine registers, which may result in smaller and faster programs. The register declaration looks like register int x semicolon, register char c semicolon, and so on. The int part may be omitted. Register can only be applied to automatic variables and the formal parameters of a function. In this latter case, the function declaration looks like f open paren c comma n close paren register int c comma n semicolon open curly brace register int I semicolon and then ... close curly brace. In practice, there are some restrictions on register variables, reflecting the realities of the underlying hardware. Only a few variables in each function may be kept in registers, and only certain types are allowed. The word register is ignored for excess or disallowed declarations, and it is not possible to take the address of a register variable, a topic that will be covered in Chapter 5. The specific restrictions vary from machine to machine. As an example, on the PDP-11, only the first three register declarations in a function are effective, and the types must be int, char, or pointer. As a quick aside, the description of the details of the implementation of the register modifier on the PDP-11 is a delightful peek into how the C compiler generated runtime code on that particular system in the 1970s. As compilers have become more sophisticated, the compiler could decide which variables to keep in registers far better than the programmer could. And since how variables would be allocated to registers might be different on different hardware architectures, the register indication is generally ignored by modern C compilers, so you should probably never use it in your code. As a matter of fact, I wrote the following sample C program and compiled it with the -S option so I could see the generated assembly language with and without the register declaration. With optimization, there was no difference between the code generated with or without the register declaration. The reason the generated assembly code was identical once you take a look at it was, regardless of the use of the register keyboard, was that the C optimizer on my ARM-based computer in 2022 realized the best way to implement the code was to keep both of the variables in registers, because the loop code was so simple and the CPU in my computer has plenty of registers and optimized any loading and storing of the data for these variables right out of the program. In 1978, the authors likely included the register function as a feature to convince experienced assembly language programmers that they should write all but the lowest level code in C. So write a little tiny bit in C and then, write a little tiny bit in assembly language and write everything else in C. So here's an example that's not in the textbook. It's on page 81. If it were in the textbook, you can see this code at www.cc4e.com/code, page 81. And this is code that I wrote to play with the register keyword to mostly convince myself it was pointless to use it. But here we go. Pound include stdio.h, int main, open paren, close paren, open curly brace, int compute, semicolon, register int iter, semicolon, scanf, open paren, double quote, %d, close quote, comma, ampersand, compute, close parenthesis, semicolon. Printf, open parenthesis, double quote, compute, space, %d, \n, double quote, comma, compute, close parenthesis, semicolon. 4, open paren, iter equals 0, semicolon, iter less than 1000, semicolon, iter plus plus, close parenthesis, open curly brace, compute equals open parenthesis, compute times 22, close parenthesis, times 7. If compute greater than 1000, compute equals compute modulo 1000, close curly brace. Printf, open paren, double quote, compute, space, %d, \n, close quote, comma, compute, semicolon, close curly brace. Now, some of these, I wrote this code in a way that tries to convince the optimizer that I'm actually going to use these values. That's why I read the value from input as compared to a constant. It would actually, the optimizer is so smart that it would just eliminate all the constant calculations. So, but that's my sample playing with register. Section 4.8, block structure. C is not a block-structured language in the sense of PL1 or ALGOL, in that functions may not be defined within other functions. On the other hand, variables can be defined in a block-structured fashion. Declarations of variables, including initializations, may follow the left brace that introduces any compound statement, not just the one that begins a function. Variables declared this way supersede any identically named variables in outer blocks and remain in existence until the matching right brace. For example, if open parenthesis n greater than 0, close parenthesis, open curly brace, int I, semicolon, declare a new I, for open parenthesis I equals 0, semicolon, I less than n, semicolon, I plus plus, close parenthesis, and the rest of the for loop, and then a close curly brace for the if. The scope of the variable I is in the true branch of the if. This I is unrelated to any other I in the program. Block structure also applies to external variables. Given the declarations, int x semicolon, f open parenthesis, close parenthesis, open curly brace, double x semicolon, close parenthesis. Then within the function f, occurrences of x refer to the internal double variable. Outside of f, they refer to the external integer. This is same is true of the names of formal parameters. For example, int z semicolon outside of any function, f open parenthesis z close parenthesis, double z semicolon, open curly brace, close curly brace. Within function f, z refers to the formal parameter, not the external variable. Section 4.9, initialization. Initialization has been mentioned in passing many times so far, but always peripherally to some other topic. This section summarizes some of the rules now that we have discussed the various storage classes. In absence of explicit initialization, external and static variables are guaranteed to be initialized to 0. Automatic and register variables have undefined or garbage values. Simple variables, not arrays or structures, may be initialized when they are declared by following the name with an equal sign and a constant expression. Int x equals 1, semicolon. Char s quote equals single quote, single quote, semicolon, a constant of a single character that is a single quote itself, Long day equals 60 times 24, semicolon, which is the minutes in a day. For external and static variables, the initialization is done once conceptually at compile time. For automatic and register variables, it is done each time the function or block is entered. For automatic and register variables, the initializer is not restricted to being a constant. It may, in fact, be any valid expression involving previously defined values, even function calls. For example, the initializations of the binary search program that we wrote in Chapter 3 could be written as binary, open parenthesis, x, comma, v, comma, n, close parenthesis, int, x, comma, v, open square bracket, close square bracket, comma, n, semicolon. Open curly brace. Int low equals 0, semicolon, int high equals n minus 1, semicolon, and int mid, followed by the rest of the function, and then close curly brace. Instead of initializing these as the first executable statements, and we would do this with binary, open paren, x, comma, v, comma, n, close paren, int x, comma, v, open square bracket, close square bracket, comma, n, semicolon, open curly brace. Int low, comma, mid, comma, high, semicolon. Low equals 0, semicolon, high equals n minus 1, semicolon, and so forth. In effect, initializations of automatic variables are just shorthand for assignment statements. Which form to prefer is largely a matter of taste. We have generally used explicit assignments because initializers and declarations are harder to see. Automatic arrays may not be initialized. External and static arrays may be initialized by following the declaration with a list of initializers enclosed in braces and separated by commas. For example, the character counting program of Chapter 1, which originally was main, open parenthesis, close parenthesis, open curly brace, int c, comma I, comma n white, comma n other, int n digit, open square bracket 10, close square bracket, semicolon, n white equals n other equals 0, for open parenthesis I equals 0, semicolon, I less than 10, semicolon, I plus plus, close parenthesis, n digit sub I equals 0, and then the rest of the code followed by a close curly brace finishing main. This could be written instead using initializers as follows. Int n white equals 0, semicolon, int n other equals 0, semicolon, int n digit, open square bracket 10, close square bracket equals open curly brace 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, close curly brace. 10 zeros in a row, separated by commas and in braces. And then the main code is simply main, open paren, close paren, open curly brace, int, comma c, comma I, and then the rest of the main code, close curly brace. The idea is that with the initializers, as with the external variables outside of the main function, you do not need to initialize them, even with a for loop in the beginning of the main program. These initializations are actually all unnecessary since they're all 0 anyways, but it's a good form to make them explicit anyway. If there are fewer initializers than the specialized size, the others will be 0. It is an error to have too many initializers. Regrettably, there is no way to specify the repetition of an initializer, nor to initialize an element in the middle of the array without supplying all the intervening values as well. Character arrays are a special case of initialization. A string may be used instead of the braces and commas notation, as in char pattern, open square bracket, close square bracket equals double quote, the double quote, semicolon. This is a shorthand for the longer but equivalent char pattern, open square bracket, close square bracket equals open curly brace, single quote t, single quote, comma, single quote h, single quote, comma, single quote e, single quote, comma, single quote, backslash 0, single quote, close curly brace, semicolon. When the size of an array of any type is omitted, the compiler will compute the length of the array by counting the initializers. In this specific case, the size of pattern is 4, 3 actual characters plus the terminating \0. I would note that the primary difference between C and C-influenced-like languages like Java, PHP, and JavaScript, the key is that C strings are character arrays, while in the other languages, strings are objects. These string objects do have inside themselves an array of bytes or characters, but they also keep track of things like the length of the string and provide functionality like extract a substring in the methods in these objects. In C, there is a set of library functions that perform string operations like compare two strings, while string comparison is built into the string objects in each of the other languages. Strings as character arrays allow programmers to build very fast, low-level code in libraries and operating systems. But to write the code well, you need to understand what is really going on at the low level. Section 4.10, Recursion. C functions may be used recursively. That is, a function may call itself either directly or indirectly. One traditional example involves printing of a number as a character string. As we mentioned before, the digits are generated in the wrong order. Low-order digits are available for high-order digits, but they have to be printed in the other way around. There are 2 solutions to this problem. One is to store the digits in an array as they are generated and then print them in reverse order, as we did in Chapter 3 with I to A. The first version of printd follows this pattern. This is sample code on page 85 of the textbook. You can view the sample code at www.cc4e.com/code, page 85, example 1. Pound include stdout.h, printd, open paren, n, close paren, int n, open curly brace, char s, open square bracket, 10, close square bracket, semicolon, int I, semicolon. If parenthesis n less than 0, parenthesis, open curly brace, put char, open paren, single quote, dash, single quote, close paren, semicolon, n equals minus n, semicolon, close curly brace. I equals 0, semicolon. Do, open curly brace, s sub I++ equals n modulo 10 plus, quote, 0, quote, which gets the next character, while parenthesis n slash equal 10, close parenthesis, greater than 0, close parenthesis, semicolon. Then we reverse the string, while, open paren, minus I greater than or equal to 0, close paren, put char, open paren, s sub I, close paren, semicolon, close curly brace to end the printd function. The alternative is a recursive solution in which each call of printd first calls itself to cope with any leading digits, then prints the trailing digit after that call returns. This is an example on page 85 of the textbook in its example 2. Pound include stdio.h, printd, open paren, n, close paren, int n, semicolon, open curly brace, int I, semicolon. If, open paren, n less than 0, close paren, open curly brace, put char, open paren, single quote, dash, single quote, close paren, semicolon, n equals minus n, semicolon, close curly brace to finish the if. If, open paren, I equals n over 10, close paren, not equal 0, close paren, printd, open paren, I, close paren, semicolon. That's the recursive call. And after the recursive call comes back, we do put char, open paren, n modulo 10 plus single quote, 0, single quote, close paren, semicolon, close curly brace to end the printd function. When a function calls itself recursively, each invocation gets a fresh set of all the automatic variables quite independent of the previous set. Thus, in printd 123, the first printd has n equals 123. It passes 12 to a second printd, then prints 3 when that one returns. In the same way, the second printd passes 1 to a third, which prints it, and then prints 2. Recursion generally provides no saving and storage, since somewhere a stack of values is being processed or has to be maintained, nor will it be faster. But recursive code is more compact and often much easier to write and understand. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in Chapter 6. As an aside, recursion. Recursion is a beloved concept in computer science. It is often taught early in most programming courses because it is just so cool. Most examples are sadly like computing factorial, or the example above, converting an integer to a string, and they're not good uses of recursion actually. But when you do finally find yourself in need of traversing a tree-based structure like an XML document, or parsing a mathematical expression with parentheses, recursion is the ideal solution. So the problem, in a sense, is not recursion, but when it is taught and what examples are used. Interestingly, Kernigan and Ritchie include the correct warning about using recursion when it is not the best solution in the above text, and it bears another read. Back to the book. Recursion generally provides no saving and storage, since somewhere a stack of values is being processed or has to be maintained, nor will it be faster. But recursive code is more compact and often much easier to write and understand. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in Chapter 6. I couldn't have said it better. Section 4.11, the C preprocessor. C provides certain language extensions by means of a simple macro preprocessor. The #define capability, which we have used, is the most common of these extensions. Another is the ability to include the entire contents of other files during compilation. File inclusion. To facilitate handling of #defines and declarations, among other things, C provides a file inclusion feature. Any line that looks like #include space double quote file name double quote is replaced by the contents of the file name. The quotes are indeed mandatory. Often a line or two of this form appears at the very beginning of each source file to include common #define statements and extern declarations for global variables. #includes may be nested. #include is the preferred way to tie declarations together for a large problem and in a large program. It guarantees that all the source files will be supplied with the same definitions and variable declarations, thus eliminating a particularly nasty kind of bug. Of course, when an include file is changed, all the files that depend on it must be recompiled. Macro substitution. A definition of the form #define yes 1 calls for a macro substitution of the simplest kind, replacing a logical name by a string of characters. Names in the #define have the same forms as the C identifiers. The replacement text is arbitrary. Normally, the replacement text is the rest of the line. A long definition may be continued by pasting a backslash at the end of the line to be continued. The scope of the name defined with #define is from its point of definition to the end of the source file. Names may be redefined, and a definition may use previous definitions. Substitutions do not take place within quoted strings. So, for example, if yes is a defined name, there would be no substitution in printf, open paren, double quote, yes, double quote, close paren. Since implementation of #define is a macro pre-pass, not part of the compiler proper, there are very few grammatical restrictions on what can be defined. For example, Algol fans can say #define then, and then nothing, #define begin, open curly brace, #define end, semicolon, close curly brace, and then write, approximate Algol, if paren I greater than 0, close paren, then begin A equals 1, semicolon, B equals 2, end. It is also possible to define macros with arguments, so the replacement text depends on the way the macro is called. As an example, define a macro called max, like this. pound define, max, open paren, a, comma, b. Open paren, a, close paren, greater than, open paren, b, close paren, question mark, open paren, a, close paren, colon, open paren, b, close paren. Now, the line x equals max, open paren, p plus q, comma, r plus s, close paren, semicolon, will be replaced in the preprocessor by the line x equals open paren, p plus q, close paren, greater than, open paren, r plus s, close paren, question mark, open paren, p plus q, close paren, colon, open paren, r plus s, close paren, semicolon. This provides a maximum function that expands into inline code rather than a function call. So long as the arguments are treated consistently, this macro will serve for any data type. There is no need for different kinds of max for different data types, as there would be with functions. Of course, if you examine the expansion of max above, you will notice some pitfalls. The expressions are evaluated twice. It is bad if they involve side effects like function calls, increment operators, or perhaps push and pop like we've used before. Some care has to be taken with parentheses to make sure the order of evaluation is preserved. Consider the macro pound define square open paren x close paren equals x times x. When it is invoked as square open paren z plus 1 close paren. There are even some purely lexical problems. There can be no space between the macro name and the left parentheses that introduces the argument list. Nevertheless, macros are quite valuable. One practical example is the standard I/O library to be described in Chapter 7, in which getchar and putchar are defined as macros. Obviously, putchar needs an argument, thus avoiding the overhead of a function call per character process. Other capabilities of the macro processor are described in Appendix A. As a bit of a long aside, in this section we are talking about the preprocessor. It's probably a good time to talk a bit about why we use this terminology. For those of you with a computer science degree from back in the day, many of you wrote a compiler as a senior project, just like I did. Building a compiler was a great project because part of the goal of computer science is to understand the technologies that make programming possible, from the language syntax down to the hardware. The compiler that translates our source code into machine code is an essential part of the technology stack that we use. Early compilers for languages like the early Fortran variants tended to be translators. They just translated code one line at a time from a high-level language to assembly language. You could think of early Fortran programs in the 1950s and the 1960s as just more convenient ways to write assembly language for programmers that knew assembly language. You always needed to be aware of assembly language and the translation that it was going to write fast Fortran. Programs were small, and optimization was done at the Fortran level, often leading to some hard-to-understand code. By the mid-1970s, programming languages were based on parsing theory, and we used what is called a grammar to define the language. Kernigan and Ritchie kept I/O statements out of the C language to keep its formal definition, i.e. its grammar, as simple as possible. As these new languages emerged, they allowed for a more theoretical and powerful approach to converting source code to machine language. The theoretical advances in compiler and language design meant that parts of the compiler might be reusable across multiple programming languages. Each language could have its own syntax and grammar rules, and they could be plugged into the compiler, and poof, you would have a new programming language. It got to the point where Unix systems had a tool called YAC, which stood for Yet Another Compiler. You would give it a grammar for your new language, and it would make a compiler for you. As a matter of fact, the JavaScript language that was created in 10 days back in 1995 was possible because Brendan Eich had a lot of experience with compiler generators. He defined a grammar for JavaScript and generated his first compiler. Part of what made a compiler generator possible is the idea of a multi-step compiler, or the tasks of a compiler were broken down into a series of simpler and more well-defined steps. Here are the steps of a typical C compiler in the 1970s. First, a preprocessor step that takes C code with syntax like pound define and pound include as its input and produces raw C code output with those instructions processed and or expanded. The preprocessor was a C to C transformation. Next, a parser step that took the raw C code, applied the grammar to the language, and created what is called a parse tree. Think of the tree as a hierarchy of statements grouped into blocks, grouped into functions, etc. Things like a loop or just one node in a parse tree. After that, a code generation would turn the parse tree into some kind of simplistic, portable internal code that expanded things like loops and if-then-else statements into code. After that, a code optimization that looked at the internal code and moved things around, eliminating any redundant computations. Say, don't compute the same things twice. This step is why the authors make such a big fuss about how there are times where C might do things in a slightly different order in an expression, even in the presence of parentheses. Remember the K&R C arrangement license back in Chapter 2? That rule removes constraints on the compiler's optimization step so it can generate the most efficient code. I would note that all the steps up to this point did not depend in any way on the actual machine language of the system that they were running on. This meant a preprocessor, parser, code generator, and code optimizer could literally be written in C and used on any architecture. The final step is a code generator that takes the optimized intermediate code and generates the actual assembly and machine language for the processor. For fun, you can add the -S parameter to your C compiler and see the resulting assembly language output for your system. If you look at the machine language generated on an Intel or AMD processor and compare it to the machine language on an ARM processor, it will look very different. Because all but the final compiler steps did not depend on the computer where the program is being run, you could actually create a C compiler on a new computer architecture by writing a code generator on the new computer, then running all but the last step of the compiler on one computer, then copying the internal code generated by the compiler to the new compiler and running the code generation step on the new computer. Then you actually have a working C compiler on the new computer. And the first step is usually to recompile the C compiler itself from source code to produce a fully native C compiler on the new computer that can compile all the rest of the C code you have, including possibly the mostly portable elements of the UNIX operating system on the new compiler. Yes, describing how to cross-compile and bootstrap a C compiler onto a new computer hardware architecture can give you a headache if you think about it too much. But this notion of bootstrapping a C compiler onto a new architecture was an important technique to move C and then UNIX to a wide range of very different computer architectures. We see this in action as the Unix-like macOS operating system over the past 20 years was delivered initially on a Motorola 68000 family processors, then on PowerPC processors, and then on Intel processors, and most recently on ARM-based processors built by Apple. Using the software portability patterns that come from C and Unix and described by Kernigan and Ritchie in this book, Apple now makes their own hardware that can be tuned and evolved over time as their operating system and their applications requirements dictate. The use of a grammar, by the way, is to define a programming language is one of the reasons that syntax errors are so obtuse. The compiler is not looking at your code like a human. It is following a very set of simple rules to parse your code, and it's stuck with something illogical and gives you a message like unexpected statement, block, or constant on line 17, and the error is nowhere near line 17. Modern compilers are more sophisticated, of course, than the steps above, but these steps give you a sense that the compiler does many things to make it so your code can actually run very efficiently. And given that Kernigan and Ritchie were building a programming language C, a mostly portable operating system written in C, Unix, and a mostly portable C compiler written in C, some of their innovative work and research into compiler design finds its way into this book, so we have a section in this chapter called the C preprocessor. So here we are at the end of chapter 4, and it's a good time to talk about the word address. Up to this point in the book, if you count them, the word address has been used 10 times without a precise definition beyond the notion that data is stored in memory and the address of the data is where the data is stored in memory. In the next chapter, This notion of the address where the data is stored becomes very real and tangible as we explore pointers as well as the ampersand and asterisk operators. Up to now, an experienced JavaScript, PHP, or Java programmer can view C as just another set of similar syntax rules with a few quirky runtime bits. But in the next chapter, we will deeply explore the concept of data allocation and location. It turns out that every programming language pays a lot of attention to data allocation and location, but the runtime environments of modern languages work very hard not to expose you to those details. Just because modern languages hide the difficult bits from us, it does not mean that those languages solve the problem using magic. Eventually, the problem needs to be solved. And that is why the compiler and low-level runtime elements of language like PHP, JavaScript, and Java are usually written in C. So the builders of those languages can solve the difficult data storage and allocation problems for you. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 5, Pointers and Arrays. Before we start Chapter 5, a quick note from your narrator. From time to time, I have been adding some of my interpretation to this book, but I won't be adding anything to this chapter. I think that sections 5.1 through 5.6 contain some of the most elegantly written text in the book. The concepts are clearly stated, and the example code is short, direct, and easy to understand. Pointers are the essential difference between C and any other modern programming language. So pay close attention to this chapter and make sure that you understand it before continuing. This chapter is as strong now as it was in 1978, and so without further ado, we read and listen as Kernigan and Ritchie teach us about pointers and arrays. A pointer is a variable that contains the address of another variable. Pointers are very much used in C, partly because they are sometimes the only way to express a computation, and partly because they usually lead to more compact and efficient code than can be obtained in other ways. Pointers have been lumped with a go-to statement as a marvelous way to create impossible-to-understand programs. This is certainly true when they are used carelessly, and it is easy to create pointers that point somewhere unexpected. With discipline, however, pointers can also be used to achieve clarity and simplicity. This is the aspect that we will try to illustrate. Section 5.1, Pointers and Addresses. Since a pointer contains the address of an object, it is possible to access the object indirectly through the pointer. Suppose that x is a variable, say int, and that px is a pointer, created in some as yet unspecified way. The unary operator ampersand gives the address of an object, so the statement px equals ampersand x semicolon assigns the address of x to the variable px. Px is now said to point to x. The ampersand operator can be applied only to variables and array elements. Construct like ampersand open paren x plus 1 close paren and ampersand 3 are illegal. It is also illegal to take the address of a register variable. The unary operator asterisk treats its operand as the address of the ultimate target and accesses that address to fetch the contents. Thus, if y is also an int, y equals star px semicolon assigns to y the contents of whatever px points to. So the sequence px equals ampersand x semicolon y equals star px semicolon assigns the same value to y as does y equals x. It is also necessary to declare the variables that participate in all of this. Int x comma y semicolon, int star px semicolon. The declaration of x and y is what we have seen all along. The declaration of the pointer px is new. Int star px semicolon is intended as a mnemonic. It says that the combination star px is an int. That is, if px occurs in the context star px, it is equivalent to a variable of type int. In effect, the syntax of the declaration for a variable mimics the syntax of expressions in which the variable might appear. This reasoning is useful in all cases involving complicated declarations. For example, double a to f open parenthesis close parenthesis comma star dp semicolon says that in a particular expression a to f open paren close paren and star dp have values of type double. You should also note the implication in the declaration that a pointer is constrained to point to a particular kind of objects. Pointers can occur in expressions. For example, if px points to the integer x, then star px can occur in any context where x could. Y equals star px plus 1 sets y to 1 more than x. Printf, open parenthesis double quote %d backslash n double quote comma star px close paren prints the current value of x. And d equals square root open paren double close paren star px close paren produces in d the square root of x, which is coerced into a double before being passed to square root. In expressions like y equals star px plus 1, the unary operators star and ampersand bind more tightly than arithmetic operators. So this expression takes whatever px points at, adds 1, and assigns it to y. We will return shortly to what y equals star open paren px plus 1 close paren might mean. Pointer references can also occur on the left side of assignments. If px points to x, then star px equals 0 sets x to 0, and star px plus equals 1 increments it, as does open paren star px close paren plus plus. The parentheses are necessary in this last example. Without them, the expression would increment px instead of what it points to, because unary operators like star and plus plus are evaluated right to left. Finally, since pointers are variables, they can be manipulated as other variables can. If py is another pointer to int, then py equals px copies the contents of px into py, thus making py point to whatever px points to. Section 5.2, Pointers and Function Arguments. Since C passes arguments to functions by call by value, there is no direct way for the called function to alter the variable in the calling function. What do you do if you really have to change an ordinary argument? For example, a sorting routine might exchange two out-of-order elements with a function called swap. It's not enough to write swap open parenthesis a comma b close parenthesis semicolon, where the swap function is defined as, and this is sample source code on page 91 of the textbook, and you can see it at www.cc4e.com/code. This is a wrong swap, by the way. This is showing you the code that you're not supposed to do. Swap, open paren, x comma y, close paren, int x comma y, semicolon, open curly brace, int temp, semicolon, temp equals x, x equals y, semicolon, y equals temp, semicolon, close curly brace. Because of call by value, swap can't affect the arguments a and b in the routine that called it. Fortunately, there is a way to obtain the desired effect. The calling point program passes pointers to the values to be changed. The call is swap, open parenthesis, ampersand a, comma, ampersand b, close parenthesis, semicolon. Since the operator ampersand gives the address of a variable, ampersand a is a pointer to a. In swap itself, the arguments are declared to be pointers, and the actual operands are accessed through them. So the correct code is on page 92. Swap, open paren px, comma, py, close paren, int star px, comma, star py, semicolon, open curly brace, int temp, semicolon. Temp equals star px, semicolon. Star px equals star py, semicolon. Star py equals temp, semicolon, and close curly brace. One common use of pointer arguments is in functions that must return more than a single value. You might say that swap actually returns two values, the new values of its arguments. As an example, consider a function getInt, which performs a free format input conversion by breaking a stream of characters into integer values, one integer per call. GetInt has to return the value that it found or an end-of-file signal when there is no more input. These values have to be returned as separate objects, for no matter what value is used for EOF, that could also be a value of the integer. One solution, which is based on the input function scanf that we will describe in Chapter 7, is to have getInt return EOF as its function value it finds end of file, and any other return value signals a normal integer. The numeric value of the integer it found is returned through an argument, which then must be a pointer to an integer. This organization separates the end-of-file status from the returned numeric value. The following loop fills an array with integers by calls to getInt. Int, comma, n, comma, array, open paren size, close paren, semicolon. For n equals 0, n less than size, double ampersand, getInt, open paren, ampersand v, close paren, not equal EOF, semicolon, n plus plus, close parenthesis, array sub n equals v. Each call sets v to the next integer found in the input. Notice that it is essential to write ampersand v instead of v as the argument to getInt. Using plain v is likely to cause an addressing error, since getInt believes that it's been handed a valid pointer. GetInt is an obvious modification to a to I, which we wrote earlier. The sample code is on page 93 of the textbook, and you can see this sample code at www.cc4e.com/code. Pound include stdio.h. GetInt, open paren, pn, close paren, int star pn, semicolon. Open curly brace, int c comma sign. While open paren c equals get ch, open paren, close paren, double equals, quote space quote, or c double equals quote backslash n quote, or c double equals backslash t quote, close paren, semicolon. This loop we've done before, and it skips the white space. Sign equals 1, semicolon. If open paren c double equals quote plus quote, or c double equals quote minus quote, close paren, open curly brace, sign equals open paren c double equals quote plus quote, close paren, question mark 1 colon minus 1 semicolon. C equals get ch to advance the character, semicolon. and then close curly brace. Those 4 lines record the sign. Now, for star pn equals 0, c greater than or equal to quote 0 quote, and c less than or equal to quote 9 quote, colon, semicolon, c equals get ch, open paren, close curly brace. Star pn equals 10 times star pn plus c minus quote 0 quote. Star pn star equals sign. If open paren c not equal to EOF, close paren, unget ch, open paren c, close paren, semicolon, return c. Throughout getInt, star pn is used as an ordinary int variable. We have also used getch and ungetch as described in Chapter 4, so the one extra character that must be read can be pushed back onto the input. Section 5.3, Pointers and Arrays. In C, there is a strong relationship between pointers and arrays, strong enough that pointers and arrays should really be treated simultaneously. Any operation which can be achieved by array subscripting can also be done with pointers. The pointer version will in general be faster, but at least to the uninitiated, somewhat harder to grasp immediately. The declaration, int a sub 10, defines an array A of size 10 that is a block of 10 consecutive objects named a sub 0, a sub 1, ... a sub 9. The notation a sub I means the element of the array I positions from the beginning. If PA is a pointer to an integer declared as int star PA, then the assignment PA equals ampersand A sub 0 sets PA to point to the 0th element of A. That is, PA contains the address of A sub 0. Now, the assignment x equals star PA will copy the contents of A sub 0 into x. If PA points to a particular element of array A, then by definition, PA points to the next element. No. If PA points to a particular element of an array A, then by definition, PA plus 1 points to the next element. And in general, PA minus I points to I elements before PA, and PA plus I points to I elements after. Thus, if PA points to A sub 0, star, parenthesis, PA plus 1, close parenthesis, refers to the contents of A sub 1. PA plus I is the address of A sub I, and star open paren PA plus I is the contents of A sub I. These remarks are true regardless of the type of the variables in the array A. The definition of adding 1 to a pointer, and by extension all pointer arithmetic, is that the increment is scaled by the size of the storage of the object that is pointed to. Thus, in PA plus I is multiplied by the size of the objects that PA points to before being added to PA. The correspondence between indexing and pointer arithmetic is evidently very close. In fact, a reference to an array is converted by the compiler to a pointer to the beginning of the array. The effect is that the array name is a pointer expression. This has quite a few useful implications. Since the name of an array is a synonym for the location of the 0th element, the assignment PA equals ampersand A sub 0 can also be written as PA equals A. Rather more surprising, at least at first sight, is the fact that a reference to A sub I can also be written as star open paren A plus I close paren. In evaluating a sub I, C converts it to star open paren a plus I close paren immediately. The two forms are completely equivalent. Applying the operator ampersand to both parts of this equivalence, it follows that ampersand a sub I and a plus I are also identical. A plus I is the address of the ith element beyond A. As on the other side of this coin, if PA is a pointer, expressions may use it with a subscript. PA sub I is identical to star open paren PA plus I close paren. In short, any array and index expression can be rewritten as a pointer and an offset, and vice versa, even in the same statement. There is one difference between an array name and a pointer that must be kept in mind. A pointer is a variable, so PA equals A and PA++ are sensible operations. But an array name is a constant, not a variable. Constructions like A equals PA or A++ or P equals ampersand A are illegal. When an array name is passed to a function, what is passed is the location of the beginning of the array. Within the called function, this argument is a variable, just like any other variable. And so an array name argument is truly a pointer, that is, a variable containing an address. We can use this fact to write a new version of strlen, which computes the length of the string. This sample code is on page 95 of the book, and you can see it in www.cc4e.com/code, page 95. Int strlen open paren s close paren char star s semicolon open curly brace int n semicolon for open parenthesis n equals 0 semicolon star s not equal quote \0 quote semicolon s plus plus close paren n plus plus return open paren n close paren semicolon close curly brace. Incrementing s is perfectly legal since it's a pointer variable. S++ has no effect on the character string in the function that called strlen, but merely increments the strlen's private copy of the address. As the formal parameters in a function definition, char s open square bracket close square bracket semicolon and char star s semicolon are exactly equivalent. Which one should be written is determined largely by how expressions will be written in the function. When an array name is passed to a function, the function can, at its convenience, believe that it has been handed either an array or a pointer and manipulate it accordingly. It can even use both kinds of operations if it seems appropriate and clear. It is possible to pass part of an array to a function by passing a pointer to the beginning of the subarray. For example, if A is an array, f open paren ampersand a sub 2 close paren and f open paren a plus 2 close paren both pass to the function f the address of the element a sub 2 because ampersand a sub 2 and a plus 2 are both pointer expressions that refer to the third element of A. Within f, the argument declaration can read f open paren array close paren int array open bracket close bracket semicolon or f open paren array close paren int star array semicolon . So far as f is concerned, the fact that the argument really refers to part of a larger array is really of no consequence. Section 5.4, Address Arithmetic. If p is a pointer, then p++ increments p to point to the next element of whatever kind of object p points to. And p plus equals I increments p to the point I elements beyond where it currently does. These and similar constructions are the simplest and most common forms of pointer or address arithmetic. C is consistent and regular in its approach to address arithmetic. Its integration of pointers, arrays, and address arithmetic is one of the major strengths of the language. Let us illustrate some of the properties by writing a rudimentary storage allocator, but useful in spite of its simplicity. There are two routines. Alloc, open paren, n, close paren, returns a pointer, p, to n consecutive character positions, which can be used by the caller of alloc for storing characters. Free, open paren, p, close paren, releases the storage thus acquired, so it can later be reused. These routines are rudimentary because the calls to free must be made in the opposite order to the calls on alloc. That is, storage managed by alloc and free is a stack, or last in, first out. The standard C library provides analogous functions which have no such restrictions, and in Chapter 8 we'll show how improved versions as well. In the meantime, however, many applications really only need a trivial alloc to dispense little pieces of storage of unpredictable sizes at unpredictable times. The simplest implementation is to have alloc hand out pieces of a large character array, which we will call alloc buff. This array is private to alloc and free. Since they deal in pointers and not array indices, no other routine need know the name of the array, which can be declared as external static, that is, local to the source file containing alloc and free and invisible outside it. In practical implementations, the array may well not even have a name. It might be obtained by asking the operating system for a pointer to some unnamed block of storage. The other information needed is how much alloc buff has been used. We use a pointer to the next free element called allocCP. When alloc is asked for n characters, it checks to see if there is enough room left in alloc buff. If so, alloc returns the current value of alloc p, i.e. the beginning of the free block, and then increments it by n to point to the next free area. Free p merely sets alloc p to p if p is inside alloc buff. This next code example is on page 97 of the textbook. You can see the code at www.cc4e.com/code. Pound include stdio.h. Pound define null 0. It's a pointer value for in the error report. Pound define alloc size 1000, the size of the available space. Static char alloc buff, open square bracket, alloc size, close square bracket, semicolon. Static char star alloc p equals alloc buff, next free position, initialized to the start of the array. Char star alloc, open paren, n, close paren, return a pointer to n characters. Int n semicolon, open curly brace. If alloc cp plus n less than or equal to alloc buff plus alloc size, close paren, open curly brace, meaning we have space, alloc cp plus equals n, return alloc cp minus n, close parenthesis, semicolon. Close curly brace. Else, if there's not enough room, return open paren, null, close paren, semicolon, close curly brace. Free, open paren, p, close paren. This function will free the storage pointed to by p. Char star p, open curly brace. If open paren, p greater than or equal to alloc buff and p less than alloc buff plus alloc size, alloc cp equals p, close curly brace. Some explanations. In general, a pointer can be initialized just as any other variable can, though normally only meaningful values are null, discussed below, or an expression involving the address of a previously defined data of the appropriate type. The declaration static char star alloc cp equals alloc buff defines alloc cp to be a character pointer and initializes it to point to alloc buff, which is the next free position when the program starts. This could also have been written static char star alloc cp equals ampersand alloc buff sub 0 semicolon, since the array name is the address of the 0th element, whichever is more natural. The test, if open paren alloc p plus n less than or equal to AlecBuff plus AlecSize checks if there's enough room to satisfy a request for n characters. If there is, the new value of AlecP would be at most 1 beyond the end of AlecBuff. If the request can be satisfied, Alec returns a normal pointer. Notice the declaration of the function itself. If not, Alec must return some kind of signal that there's no space left. C guarantees that no pointer that validly points to data will ever contain a 0, so a return value of 0 can be used to signal an abnormal event, in this case, no space. We write null instead of 0, however, to indicate more clearly that this is a special value for a pointer. In general, integers cannot be meaningfully assigned to pointers, but 0 is a special case. Tests like if, open paren, AlecP plus n less than or equal to AlecBuff plus AlecSize, and if, open paren, p greater than or equal to AlecBuff and p less than AlecBuff plus AlecSize, shows several important facets of pointer arithmetic. First, pointers may be compared on certain circumstances. If p and q point to members of the same array, then relations like less than, greater than, equal, etc. work properly. P greater than q is true, for example, if p points to an earlier member of the array than q. The relations double equals and not equals exclamation equals also work. Any pointer can be meaningfully compared for equality or inequality with null. But all bets are off if you do arithmetic or comparisons with pointers that point to different arrays. If you're lucky, you get obvious nonsense on all machines. If you're unlucky, your code will work on one machine but collapse mysteriously on another. Second, we've already observed that a pointer and an integer can be added or subtracted. The construction p plus n means the nth object beyond the one p currently points to. This is true regardless of the kind of object p is declared to point at. The compiler scales n according to the size of the objects p points to, which is determined by the declaration of p. For example, on the PDP-11, the factors are 1 for char, 2 for int and short, and 4 for long float and float, and 8 for double. Pointer subtraction is also valid. If p and q point to members of the same array, p minus q is the number of elements between p and q. This fact can be used to write yet another version of strlen. Strlen, open paren s, close paren, char star s, semicolon, open curly brace. Char star p equals s, semicolon, while star p not equal backslash single quote, backslash 0, single quote, close paren, p plus plus, semicolon. Return, open paren, p minus s, close paren, semicolon, close curly brace. In its declaration, p is initialized to s, that is to point to the first character. In the while loop, each character in turn is examined until backslash 0 at the end is seen. Since backslash 0 is 0, and since while tests only whether the expression is 0, it is possible to omit the explicit test, and such loops are often written as while, open paren, star p, close paren, p plus plus, semicolon. Because p points to characters, p plus plus advances p up to the next character each time, and p minus s gives the number of characters advanced over, that is, the string length. Pointer arithmetic is consistent. If we'd been dealing with floats, which occupy more storage than chars, and if p were a pointer to a float, p plus plus would advance to the next float. Thus, we could write another version of Alec which maintains, say, floats instead of chars, merely by changing char to float throughout Alec and free. All the pointer manipulations automatically take into the account the size of the object pointed to, so nothing else has to be altered. Other than the operations mentioned here, adding or subtracting a pointer in an integer, subtracting or comparing two pointers, all other pointer arithmetic is illegal. It is not permitted to add two pointers or to multiply or divide or shift or mask them or add float or double to them. Section 5.5, Character pointers and functions. A string constant, written as double quote, I am a string, double quote, is an array of characters. In the internal representation, the compiler terminates the array with the character \0, so programs can find the end. The length in storage is thus one more than the number of characters between the double quotes. Perhaps the most common occurrence of a string constant is arguments to functions, as in printf, open paren, double quote, hello, comma, world, \n, double quote. When a character string appears like this in a program, access to it is through a character pointer. What printf receives is a pointer to the character array. Character arrays, of course, need not be function arguments. If message is declared as char star message, then the statement message equals double quote now is the time double quote semicolon assigns message to a pointer to the actual characters. This is not a string copy. Only pointers are involved. C does not provide any operators for processing an entire string of characters as a unit in the language. We will illustrate more aspects of pointers and arrays by studying two useful functions from the standard I/O library to be discussed in Chapter 7. The first function is strcpy, open paren s, t, which copies the string t to the string s. The arguments are written in this order by analogy to assignment, where one would say s equals t to assign t to s. The array version is first. Strcpy, open paren s, t, close paren, char s, open square bracket, close square bracket, comma, t, open square bracket, close square bracket, semicolon, open curly brace, int I, semicolon, I equals 0, semicolon, while open paren, s sub I equals t sub I, close paren, not equal, quote, \0, quote, close parenthesis, I++, semicolon, close curly brace. You'll note in that while statement that there is a copying of the actual characters as an assignment, and then the side effect of the result of that assignment is compared to the new line, to the end of string, which terminates the while loop. For contrast, here is a version of strcpy with pointers, and this is on page 100 of the textbook, and you can see all the code in the textbook at www.cc4e.com/code. And again, this is example number 2 on page 100. Strcpy, open paren s, t, close paren, char star s, star t, semicolon, open curly brace, while open paren, star s equals star t, close paren, not equal, single quote, \0, single quote, close paren, open curly brace, s++, semicolon, t++, semicolon, close curly brace to end the function. Because the arguments are passed by value, strcpy can use s and t in any way it pleases. Here they are, conveniently initialized pointers, which are marched along the arrays, a character at a time, until the / terminates. Then t has been copied to s. In practice, strcpy would not be written as we showed above. A second possibility might be, and this is the third example on page 100 of the textbook. Strcpy, open paren s, t, close paren, char star s, star t, semicolon, open curly brace, while paren, star s++ equals star t++, close paren, not equal, quote, \0, quote, close paren, semicolon, curly brace. This moves the increment in s and t into the test part. The value of star t++ is the character that t pointed to before t was incremented. The postfix ++ doesn't change t until after this character has been fetched. In the same way, the character is stored in the old position of s before s is incremented. The character is also the value that is compared against \0 to control the loop. The net effect is that the characters are copied from t to s up to and including the terminating \0. As the final abbreviation of solving this problem, we can observe that the comparison against \0 is redundant, so the function is often written as, and now this is the first sample code on page 101 of the textbook. strcpy, open paren s, comma, t, close paren, char star s, comma, star t, semicolon, open curly brace, while open paren star s plus plus equals star t plus plus, close paren, semicolon, curly brace. Although this may seem cryptic at first, the notational convenience is considerable, and the idiom should be mastered if for no other reason than you will see it frequently in C programs. The second routine is strcomp, open paren s, comma, t, which compares the character strings s and t and returns negative, 0, or positive according to as s is lexicographically less than, equal to, or greater than t. The value returned is obtained by subtracting the characters at the first position where s and t disagree. This is the second example on page 101 of the textbook, which you can see at www.cc4e.com/code. strcomp, open paren s, comma, t, close paren, char s, open square bracket, close square bracket, comma, t, open square bracket, close square bracket, semicolon, open curly brace, int I, semicolon, I equals 0, semicolon, while s sub I double equals t sub I, close paren, open paren, s sub I plus plus, double equals, single quote, \0, single quote, close paren, return 0. Return, open paren, s sub I minus t sub I, close paren, semicolon, close curly brace. The pointer version of strcomp is the first example on page 102 of the textbook. strcomp, open paren s, comma, t, close paren, char star s, comma, star t, open curly brace, for open paren, semicolon, star s double equals star t, semicolon, s plus plus, comma, t plus plus, close paren, if open paren star s equal, single quote, \0, single quote, close paren, return, open paren 0, close paren, return, open paren star s minus star t, close paren, semicolon, close curly brace. Since plus plus and minus minus are either prefix or postfix operators, the combination of star and plus plus and minus minus occur, although less frequently. For example, star plus plus p increments p before fetching the character that p points to. Star minus minus p decrements p first. Section 5.6, pointers are not integers. You may notice in older C programs a rather cavalier attitude towards copying pointers. It has generally been true that on most machines a pointer may be assigned to an integer and back again without changing it. No scaling or conversion takes place and no bits are lost. Regrettably, this has led to the taking of liberties with routines that return pointers which are then merely passed to other routines. The requisite pointer declarations are often left out. For example, consider the function stir_save, open paren s, close paren, which copies the string s into a safe place, obtained by a call to alloc, and returns a pointer to it. Properly, this should be written as, this is the first example on page 103 of the textbook. You can see the sample code at www.cc4e.com/code. Pound include stdlib.h. Char star stir_save, open paren s, close paren, save a string somewhere. Char star s, semicolon, open curly brace, char star p star alloc, open paren, close paren, semicolon. If open paren p equals alloc, open paren stirlen, open paren s, close paren, plus 1, close paren, not equal null, close paren, strcpy, open paren p, comma s, close paren, semicolon, return, open paren p, close paren, semicolon, curly brace. In practice, there would be a strong tendency, mistaken tendency that is, to omit declarations. This is example 2 on page 103. Pound include stdlib.h. Stir save, open paren s, close paren. Open curly brace, char star p, semicolon. If, parenthesis, p equals alloc, open paren, stirlen, open paren s, close paren, plus 1, close paren, not equal no, close paren. Stir copy, open paren, p, comma, s, close paren, semicolon. Return, open paren, p, close paren, semicolon. This will work on many machines, since the default type for functions and arguments is int. An int and pointer can usually be safely assigned back and forth. Nonetheless, this kind of code is inherently risky, for it depends on the details of the implementation and machine architecture, which may not hold for the particular compiler you use. It is wiser to be complete in all declarations. The program lint will warn of such constructions in case they creep in inadvertently. Section 5.7, Multidimensional Arrays. In general, rectangular multidimensional arrays are used in computational programs like a weather simulation and were a way, back in the day, to write C code that could accept Fortran multidimensional arrays as parameters so that computational or statistical libraries could be written in C. Arrays of pointers are a better mapping to the typical operating system and string manipulation use cases that are more the core of C applications. We also call these ragged arrays because each row can be a different length. This also works well as data is dynamically allocated in C as compared to the more static allocation approach that's typical in Fortran's multidimensional arrays. Now to the textbook. C provides for rectangular multidimensional arrays, although in practice they tend to be much less used than the arrays of pointers. In this section we will show some of their properties. Consider the problem of date conversion, from the day of the month to the day of the year and vice versa. For example, March 1st is the 60th day of a non-leap year and 61st day of a leap year. Let us define two functions to do the conversions. Day of year converts month and day to the day of the year, and month day converts the day of the year into the month and the day. Since this latter function returns two values, the month and day arguments will be pointers. Month day, open parenthesis, 1977, comma 60, ampersand m, comma ampersand d, close parenthesis. Sets m to 3 and d to 1, which is March 1st. These functions both need the same information, a table of the number of days in each month, 30 days, half September, etc. Since the number of days per month differs for leap years and non-leap years, it's easier to separate them into two rows of a two-dimensional array, rather than try to keep track of what happens in February during computation. The array and the functions performing the transformations are as follows. This is example number 1 on page 104 of the textbook, and you can see the code at www.cc4e.com/code. Static int day tab, open paren 2, close paren, open paren 13, close paren, equals open curly brace, 0, comma 31, and then a number of numbers, close curly brace, comma, open curly brace, 0, comma 31, 29, and then a bunch of numbers, close curly brace, semicolon. Day of the year, open paren year, comma month, comma day, int year, comma month, comma day, semicolon, open curly brace, int I, comma leap, semicolon. Leap equals 0, year modulo 4 double equals 0, and year modulo 100 not equals 0, or year modulo 400 equals 0, semicolon. For open paren I equals 1, I less than month, I plus plus, close paren, day plus equals day tab, open square bracket leap, close square bracket, open square bracket I, close square bracket, semicolon. Return open paren day, close paren, semicolon, close curly brace. Then the month day function. Month day, open paren year, comma year day, comma p month, comma p day, close paren. Int year, year day, star p month, star p day, semicolon. Open curly brace. Int I, leap, semicolon. Leap equals year percent 4, double equals 0, and year percent 100, not equals 0, or year percent 1400, double equals 0. For I equals 1, year day greater than day tab, open square bracket, leap, close square bracket, open square bracket, I, close square bracket, semicolon, I plus plus, close parenthesis. Year day minus equal day tab, open square parenthesis, open square bracket, leap, close square bracket, open square bracket, I, close square bracket, semicolon. Star p month equals I, star p day equals year day, semicolon, close paren. The array day tab has to be external to both day of year and month day, so they can both use it. Day tab is the first two-dimensional array we've dealt with. In C, by definition, a two-dimensional array is really a one-dimensional array, each of which elements is also an array. Hence, subscripts are written as day tab, open square bracket, I, close square bracket, open square bracket, J, close square bracket, rather than day tab, open square bracket, I, J, close square bracket, as in most languages. Other than this, a two-dimensional array can be treated much the same in the same way as other languages. Elements are stored by rows, that is, the rightmost subscript varies fastest as elements are accessed in storage order. An array is initialized by a list of initializers and braces. Each row of a two-dimensional array is initialized by a corresponding sublist. We started the array day tab with a column of 0 so that month numbers can run from the natural 1 to 12 instead of 0 to 11. Since space is not a premium here, this is easier than adjusting indices. If a two-dimensional array is to be passed to a function, the argument declaration in the function must include the column dimension. The row dimension is irrelevant since what is passed in, as before, it is a pointer. In this particular case, it's a pointer to objects which are arrays of 13 ints. Thus, the array day tab, if it's to be passed to a function, f, the declaration would be f, open paren, day tab, close paren, int day tab, open square bracket 2, close square bracket, open square bracket 13, close square bracket, semicolon, open curly brace, close curly brace. The argument declaration in f could also be int day tab, open square bracket, close square bracket, open square bracket 13, close square bracket, semicolon. Since the number of rows is actually irrelevant, it could also be seen as int open paren star day tab, close paren, open bracket 13, close bracket, semicolon, which says that the argument is a pointer to an array of 13 integers. The parentheses are necessary since the brackets have higher precedence than asterisk. Without parentheses, the declaration int star day tab sub 13, close square bracket, semicolon, is an array of 13 pointers to integers, as we shall see in the next section. Section 5.8, Pointer Arrays, Pointers to Pointers. Since pointers are variables themselves, you might expect that there would be uses for arrays of pointers. This is indeed the case. Let us illustrate by writing a program that will sort a set of text lines into alphabetic order, then a stripped down version of the UNIX utility sort. In Chapter 3, we presented a shell sort function that would sort an array of integers. This same algorithm will work, except that now we have to deal with lines of text which are of different lengths and which, unlike integers, can't be compared or moved in a single operation. We will need a data representation, data structure, that will cope efficiently and conveniently with variable length text lines. This is where an array of pointers enters. If the lines to be sorted are stored end-to-end in one long character array, maintained by ALEC perhaps, then each line can be accessed by a pointer to its first character. The pointers themselves can be stored in an array. Two lines can be compared by passing their pointers to strcmp. When two out-of-order lines have to be swapped or exchanged, the pointers in the pointer array are exchanged, not the text lines themselves. This eliminates the twin problems of complex storage management and high overhead that would go with moving the text of the actual lines. The sorting process involves 3 steps. Read all the lines of input, sort them, and then print them in order. As usual, it's best to divide the program into functions that match this natural division, with the main routine controlling things. Let us defer the sorting step for a moment and concentrate on the data structures and the input and output. The input routine has to collect and save the characters in each line and build an array of pointers to the lines. It will also have to count the number of input lines, since that information is also needed for sorting and printing. Since the input function can only cope with a finite number of input lines, it can return some illegal line count like -1 if too much input is presented. The output routine only has to print the lines in the order in which they appear in the array of pointers. This next code segment is actually a combination of 3 successive sample code segments starting on page 106 of the textbook, and it's pretty complex, so it might be best for you to see them on www.cc4e.com/code, line 106, example 1. Okay. Pound include stdio.h, pound include string.h, pound define lines 100, the maximum lines supported to be sorted. Main, open paren, close paren. Char, line ptr, open square bracket lines, close square bracket, semicolon. Int n lines, which is the number of lines read. If open paren n lines equals read lines, open paren line ptr, comma, lines, close paren greater than or equal to 0, close paren, open curly brace, sort, open paren line ptr, comma, n lines, close paren, right lines, open paren line ptr, comma, n lines, close paren, semicolon, close curly brace, else, printf, open paren, double quote, input too big to sort, \n, close double quote, close paren, semicolon, and close curly brace to end the main program. This next routine is actually from page 107 of the textbook, but we combined them into one. Pound define maxlen 1000. Read lines, open paren, line ptr, comma, max lines, close paren. Char, star, line ptr, open square bracket, close square bracket, semicolon. This is an array of pointers to characters. An array of pointers being, long, like 4 bytes, characters being generally 1 byte. Int, max line, semicolon, open curly brace. Int, len, comma, n lines, semicolon, char, star p, star, alloc, open paren, close paren, comma, line, open square bracket, max len, close square bracket, semicolon. So just to recall, alloc is a function we did earlier that allows us to allocate some text of a varying length, and then lines of max len is a place that we're going to read each line into. Beginning the code of read lines. N lines equals 0, while open paren, len equals get line, open paren line, comma, max len, close paren, greater than or equal to 0, close paren. If open paren n lines greater than or equal to max lines, close paren, return open paren -1, close paren, semicolon. Else if open paren, p equals alloc, open paren, len, close paren, double equals null, close paren, return -1. So those two tests basically make sure that we don't get too many lines and that we have enough space in our dynamic data area that alloc is managing for us. So continuing with the if, we're at the else, open curly brace, line sub len -1 equals quote \0 quote semicolon, stir copy p comma line close paren semicolon, line ptr sub n lines plus equals p semicolon, close curly brace that finishes the else segment, return n lines semicolon, and close curly brace to finish the read lines function. Now, at a high level, we're reading a line into allocated automatic variable line, and then we are calling alloc to get another place to copy that line. Then we're making a copy of that line, and then we are remembering the pointer to the beginning of that line in line PTR, and that's the essence of it. Okay. Write lines, open paren line PTR comma end lines, close paren, char star line PTR open square bracket close square bracket semicolon. Again, an array of pointer characters, int end lines semicolon, which is the number of character pointers in line PTR. Open curly brace, int I semicolon. For paren I equals 0 semicolon, I less than n lines semicolon, I plus plus, close paren, printf, open paren, double quote, %s backslash n double quote, comma, line PTR sub I, close paren, semicolon, close curly brace. A simple loop that goes through the array of character pointers and then prints each one out using printf. The main new thing is the declaration for line PTR, char star line PTR sub open square bracket lines close square bracket semicolon. It says that line PTR is an array of lines elements, each element of which is a pointer to a char. That is, line PTR sub I is a character pointer, and star line PTR sub I accesses a character. Since line PTR itself is an array that was passed to write lines, it can be treated as a pointer exactly in the same manner as our earlier examples, and the function can be written instead as write lines, open paren, line PTR, comma, end lines, close paren, char star line PTR, open square bracket, close square bracket, semicolon, int end line semicolon, open curly brace, while open paren minus minus end lines greater than or equal to 0, close paren, printf, open paren double quote, %s backslash n double quote, comma, star line PTR plus plus, close paren, semicolon. That code, by the way, was on page 108, example 1 of the textbook. Star line PTR points initially to the first line, but each increment of line PTR advances it to the next line while end lines is counted down. With input and output under control, we can proceed to sorting. The shell sort from chapter 3 needs minor changes. The declarations have to be modified, and the comparison operation must be moved into a function. But the basic algorithm remains the same, which gives us some confidence that it will still work. And this is the second example on page 108 of the textbook, and you can see this example at www.cc4e.com/code. Sort open paren v comma n close paren, char star v open square bracket close square bracket semicolon, int n semicolon open curly brace. So we're getting an array of pointers to the beginnings of lines, and how many of those pointers matter. And the rest of it is shell sort, with the strcomp being used to do the string comparison. So it's a 3-nested for loop with a simple if test in it. So here we go. Open curly brace for the sort function. Int gap comma I comma j semicolon char star temp semicolon. And that's a pointer to a character. For open paren gap equals n over 2 semicolon, gap greater than 0 semicolon, gap slash equals 2 close parenthesis. For I equals gap semicolon, I less than n semicolon, I plus plus close parenthesis. For open paren j equals I minus gap semicolon, j greater than or equal to 0 semicolon, j minus equals gap close paren open curly brace. So that's sort of the shell part of the shell sort. And now we have to do our comparison. If open paren strcomp open paren v sub j comma v sub j plus gap close paren less than or equal to 0 close paren break. And note that that's only breaking the third deep for loop, which it just goes and then runs the next iteration of the second for loop. Now we do the swapping. Temp equals v sub j, semicolon. V sub j equals a v sub j plus gap, semicolon. V sub j plus gap equals temp. Now that's just swapping pointer values. So the strings that are pointed to by these two pointers, v sub j and v sub j plus gap, if they're out of order, we're going to swap the pointers in the array and move them so that if you then go through like we did in write lines earlier, then they come out in order. But we literally read the data once, we copy it once into its final destination using alloc and stir copy, but once we sort it, which is the most complex part of the calculation, we're only moving the pointers back and forth. So this sort is very efficient and requires no extra memory than what we had before the sort. So that's really nice, and it sorts in place. So back to the text. Since any individual element of v, which is an alias to line pointer, PTR, is a character pointer, temp should also be one, so one can be copied to the other. We wrote the program about as straightforwardly as possible so as to get it working quickly. It might be faster, for instance, to copy the incoming lines directly into an array made by readlines rather than copying them into line and then to a hidden place maintained by alloc. But it's wiser to make the first draft of something easy to understand and worry about efficiency later. The way to make this program significantly faster is probably not by avoiding an unnecessary copy of the input lines, just instead replacing the shell sort by something quicker and better, like quicksort, is much more likely to make a real difference that matters. In Chapter 1, we pointed out that because while and for loops test the termination condition before executing the loop body even once, they help to ensure that the programs will work at their boundaries, in particular with no input. It's illuminating to walk through the functions of the sorting program, checking what happens if there is no input text at all. Section 5.9, Initialization of Pointer Arrays. Consider the problem of writing a function month name, open paren and close paren, which returns a pointer to a character string containing the name of the nth month. This is an ideal application for an internal static array. Month name contains a private array of character strings and returns a pointer to the proper one when called. The topic of this section is how that array of names is initialized. The syntax is quite similar to the previous initializations. This is sample code from page 109 of the textbook, which you can see at www.cc4e.com/code. Char star month name open paren close paren. So the return value for this function is a character pointer. Int n semicolon open curly brace. Static char star name open square bracket close square bracket equals open curly brace. Quote illegal month quote comma double quote January double quote comma double quote February double quote comma and so forth down to double quote December double quote close curly brace semicolon. The body of the function is one line. Return open paren n less than 1 or n greater than 12 close paren question mark name sub 0 colon name sub n close paren semicolon close curly brace. The declaration of name, which is an array of character pointers, is the same as line PTR in the sorting example. The initializer is simply a list of character strings, each assigned to the corresponding position in the array. More precisely, the characters of the ith string are placed somewhere else, and a pointer to them is stored in name sub I. Since the size of the array name is not specified, the compiler itself counts the initializers and fills in the correct number. Section 5.10, Pointers versus Multidimensional Arrays. Newcomers to C are sometimes confused about the difference between a two-dimensional array and an array of pointers, such as name in the example above. Given the declarations int a open square bracket 10 close square bracket open square bracket 10 close square bracket semicolon and int star b open square bracket 10 close square bracket semicolon, The usage of A and B may be similar, in that A sub 55 and B sub 55 are both legal references to a single integer. But A is a true array. All 100 storage cells have been allocated, and the conventional rectangular subscript calculation is done to find any given element. For B, however, the declaration only allocates 10 pointers. Each must be set to point to an array of integers. Assuming that each does point to a 10-element array, then there will be 100 storage cells set aside, plus the 10 cells for the pointers. Thus, the array of pointers uses slightly more space and may require an explicit initialization step. But it has two advantages. Accessing an element is done by indirection through a pointer rather than by a multiplication and an addition, and the rows of the array may be of different lengths. That is, each element of B need not point to a 10-element vector. Some may point to 2 elements, others may point to 20, and some to none at all. Although we have phrased this discussion in terms of integers, by far the most frequent use of arrays of pointers is like that shown in month name, to store character strings of diverse lengths. Section 5.11, Command Line Arguments. In environments that support C, there is a way to pass command line arguments or parameters to a program when it begins executing. When main is called to begin execution, it is called with 2 arguments. The first, conventionally called argc, is the number of command line arguments the program was invoked with. The second, argv, is a pointer to an array of character strings that contain the arguments, 1 per string. Manipulating these character strings is a common use of multiple levels of pointers. I would note that back in 1978, the 2 largest bodies of C code were likely the AT&T Unix kernel itself and Unix utilities like grep, ls, or the login shell. So writing an operating system was fresh on the mind of the authors while writing this book. These topics find their way into the text of this book. In a sense, a likely second-order goal of the book was to train programmers that might learn C and then might help build and maintain Unix. The 1978 edition of this textbook fits nicely into a series of AT&T Bell Labs technical reports like The Portability of C Programs in the Unix System, written by Stephen C. Johnson and Dennis M. Ritchie, published in the Bell System Technical Journal, Volume 57, Number 6, Part 2, July through August 1978, pages 2021 through 2048. You can see this one online if you search for it. Back to the textbook. The simplest illustration of the necessary declarations and use is in the program echo, which simply echoes its command line arguments in a single line separated by blanks. That is, if the command echo hello, world is given, the output is hello, world. By convention, argv sub 0 is the name by which the program was invoked, so argc is at least 1. In the above example, argc is 3, and argv sub 0, argv sub 1, and argv sub 2 are echo, hello, and world, respectively. The first real argument is argv sub 1, and the last is argv sub argc minus 1. And if argc is 1, there are no command line arguments after the program name. This is shown in the source code to echo. And this source code is on page 111 of the textbook, and you can see this source code at www.cc4e.com/code. Pound include stdio.h. Pound include string.h. Main open paren argc, argv, close paren. Int argc semicolon. Char star argv open square bracket close square bracket semicolon open curly brace int I semicolon. For open paren I equals 1 semicolon I less than argc semicolon I plus plus close paren. Printf open paren double quote %s %c double quote comma argv sub I comma open paren I less than argc minus 1, close paren, question mark, single quote, space, single quote, colon, single quotes, backslash n, single quote, close parenthesis, semicolon, close curly brace to end it. Since argv is a pointer to an array of pointers, There are several ways to write this program that involve manipulating the pointer rather than indexing an array. Let us show two variations. And this is the example number 2 on page 111 of the textbook. #include stdio.h, #include string.h, main open paren argc, argv, close paren, int argc semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace, while open paren minus argc greater than 0, close paren, printf, open paren, double quote, %s, %c, double quote, comma, star plus argv, comma, open paren, argc greater than 1, close paren, question mark, single quote, space, single quote, colon, single quote, \n, single quote, close paren, semicolon, close curly brace. Since argv is a pointer to the beginning of an array of argument strings, incrementing it by 1, plus argv, makes it point to at the original array argv sub 1 instead of argv sub 0. Each successive increment moves it along to the next argument. Star argv is then the pointer to that argument. At the same time, argc is decremented, and when it becomes 0, there are no arguments left to print. Another version, the third version on page 111 of the textbook. #include stdio.h, #include string.h, main, open paren, argc, argv, close paren, int argc semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace, while open paren minus argc greater than 0, close paren, printf, open paren, argc greater than 1, close paren, question mark, double quote, %s blank, double quote, colon, double quote, %s \n, double quote, comma, star plus argv, close paren, semicolon, close curly brace. This version shows that the format argument of printf can be an expression just like any of the others. This usage is not very frequent, but worth remembering. As a second example, let's make some enhancements to the pattern finding program from chapter 4. If you recall, we wired the search pattern deep into the program, and this is an obviously unsatisfactory arrangement for flexible code. Following the lead of the UNIX utility grep, which stands for the Generalized Regular Expression Parser, let us change the program so that the pattern to be matched is specified by the first argument on the command line. This is example 1 on page 112 of the book, which you can see at www.cc4e.com/code. #include stdio.h, #include string.h, #define max line 1000, main, open paren, argc, argv, close paren, int argc, semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace. Char line, open square bracket, max line, close square bracket, semicolon. If open paren argc not equal to close paren, printf, double quote, usage, colon, find pattern, \n, double quote, close paren, semicolon. Else, while open paren get line, open paren line, max line, close paren, greater than 0, close paren, if index, open paren line, argv, sub 1, close paren, greater than or equal to 0, close paren, printf, open paren, double quote, %s, double quote, line, close paren, semicolon, close curly brace. The basic model can now be elaborated to illustrate further pointer constructions. Suppose we want to allow two optional arguments. One says print all the lines except those that match the pattern. The second says precede each printed line with its line number. A common convention for C programs is that an argument beginning with a minus sign introduces an optional flag or parameter. If we choose -x for except to signal the inversion and -n number to request line numbering, then the command find space -x space -n the with the input now is the time for all good men to come to the aid of their party should produce 2, for all good men. Optional arguments should be permitted in any order, and the rest of the program should be insensitive to the number of arguments which were actually present. In particular, the call to index should not refer to argv sub 2, where a single flag argument, and to argv sub 1, when there was no single flag. Furthermore, it's convenient for users if option arguments can be concatenated and, as in find space dash nx space the. Here is the program. And this program is on page 113 of the textbook. And it is complex enough that I suggest that you take a look at it at www.cc4e.com/code. It's about 35 lines long. The commentary on the program, hopefully now you're looking at it. argv is incremented before each optional argument, and argc is decremented. If there are no errors at the end of the loop, argc should be 1 and star argv should point to the pattern. Note that star plus plus argv is a pointer to an argument string. Open paren star plus plus argv close paren open square bracket 0 square bracket is its first character. The parentheses are necessary, for without them, the expression would be star plus plus open paren argv sub 0 close paren, which is quite different and wrong. An alternate valid form would be star star plus plus argv. Section 5.12, pointers to functions. In C, a function itself is not a variable, but it is possible to define a pointer to a function, which can be manipulated, passed to functions, placed in arrays, and so on. We will illustrate this by modifying the sorting procedure written earlier in this chapter, so that if the optional argument -n is given, it will sort the input lines numerically instead of lexigraphically. A sort often consists of 3 parts: a comparison, which determines the ordering of any pair of objects, an exchange, which reverses their order, and a sorting algorithm, which makes comparisons and exchanges until the objects are in order. The sorting algorithm is independent of the comparison and exchange operations. So by passing different comparison and exchange functions to it, we can arrange to sort by different criteria. This approach is taken in our new sort. The lexicographic comparison of the 2 lines is done by strcomp and swapping by swap as before. We'll also need a routine numcomp, which compares 2 lines on the basis of numeric value and returns the same kind of condition indication as strcomp does. These 3 functions are declared in main, and pointers to them are passed to sort. Sort, in turn, calls the functions via pointers. We have skimped on error processing for arguments so as to concentrate on the main issues. This sample code is from page 115 of the textbook, which you can view at www.cc4e.com/code. Pound include stdio.h, pound include string.h, pound define lines 100. Main, open paren, argc, argv, close paren. Int, argc, semicolon. Char, star, argv, open square bracket, close square bracket, semicolon. Open curly brace. Char, star, line, ptr, open bracket, lines, close square bracket, semicolon. This is the pointers to the text lines. So we're going to be reading in the lines, saving them, and keeping an array of the pointer, and then we're going to sort that way. Int, end lines, semicolon. Int, strcomp, open paren, close paren, numcomp, open paren, close paren, which are our comparison functions. Int, swap, open paren, close paren, semicolon. Int, numeric equals 0, and this is going to be 1 if it's a numeric sort. First, we parse the arguments. If open paren argc greater than 1, ampersand, argv sub 1 sub 0 equal, quote minus quote, and argv open bracket 1 close bracket, open bracket 1 close bracket, double equals quote end quote, close paren, numeric equals 1. If open paren, end lines equals read lines, open paren, line ptr, lines, close paren, greater than or equal to 0, close paren, open curly brace. If open paren numeric, close paren, sort, open paren, line ptr, n lines, numcomp, comma, swap, close paren, semicolon. Else, sort, open paren, line ptr, comma, n lines, comma, strcomp, comma, swap, close paren. Right lines, line ptr, comma, n lines, close paren. Close curly brace. Else, printf, open paren, double quote, input too big to sort, backslash n, double quote, close paren, semicolon. Strcomp, numcomp, and swap are addresses of functions. Since they're known to be functions, the ampersand operator is not necessary, in the same way that it is not needed before an array name. The compiler arranges for the address of the function to be passed. The second step is to modify our sort function, and this is the first example on page 116 of the textbook. Sort, open paren, v, comma, n, comma, comp, comma, exch, exchange, close paren. Char, star v, open square bracket, close square bracket, semicolon. That's our pointer array of pointers. Int, n, semicolon. Int, open paren, star comp, close paren, open paren, close paren, comma, open paren, star exchange, close paren, open paren, close paren, semicolon. That declared the type and the fact that these are pointers to functions. It's a little more complex here in the call to code. Open curly brace, int gap, comma, I, comma, j, semicolon. And now we're going to do the three nested for loops for the shell sort. And then the only really change is in the code checking to see if the pair of items are out of order, and then what we do. So for open paren gap equals n over 2, semicolon, gap greater than 0, semicolon, gap slash equals 2, close paren. For open paren I equals gap, semicolon, I less than n, semicolon, I plus plus, close paren. For open paren j equals I minus gap, semicolon, j greater than or equal to 0, semicolon, j minus equals gap, close paren, open curly brace. And now here starts the different code. If open paren, star comp, close paren, open paren v sub j, comma, v sub j plus gap, close paren less than or equal to 0, close paren, break. Open paren, star ex exchange, close paren, open paren, ampersand v sub j, comma, ampersand v sub j plus gap, close paren, semicolon, close curly brace for the for loop, and then close curly brace for the sort function. And so really all we're doing is we're checking the order of the two items, v sub j and v sub j plus gap, and if they're out of order, i.e. less than or equal to 0, greater than or equal to greater than 0, then we just exchange them with the provided exchange function. And so the key thing here is it looks exactly like the previous time we wrote this code, except we're calling the pointer to the comparison function and the pointer to the exchange function, which makes this flexible so it can handle different kinds of data. Back to the textbook. The declaration should be studied with some care. Int, open paren, star comp, close paren, open paren, close paren, says that comp is a pointer to a function that returns an int. The first set of parentheses are necessary. Without them, int star comp, open paren, close paren, would say that comp is a function returning a pointer to an int, which is a quite different thing. The use of comp in the line if open paren, star comp, close paren, open paren, v sub j, comma, v sub j plus gap, close paren, less than or equal to 0, close paren, is consistent with the declaration. Comp is a pointer to the function, and star comp is the function. And open paren, star comp, close paren, open paren, v sub j, comma, v sub j plus gap, close paren, is the call to it. The parentheses are needed so the components are correctly associated. We've already shown strcomp, which compares two strings. Here is numcomp, which compares two strings on a leading numeric value. This is sample code from page 117 of the textbook, which you can see at www.cc4e.com/code. Numcomp, open paren S1, comma S2, close paren, char star S1, comma star S2, semicolon, open curly brace. Double, A to F, open paren, close paren, comma V1, comma V2. V1 equals A to F, open paren S1, close paren, semicolon. V2 equals A to F, open paren S2, close paren, semicolon. If open paren V1 less than V2, close paren, return open paren -1. Else if open paren V1 greater than V2, close paren, return open paren 1, close paren, semicolon. Else return open paren 0, close paren, semicolon, close curly brace. The final step is to add the function swap, which exchanges the two pointers. This is adapted directly from what we presented earlier in the chapter. Swap, open paren px, comma py, close paren, char, star px, open square bracket, close square bracket, comma star py, open square bracket, close square bracket, semicolon. Open curly brace, char star temp, semicolon. Temp equals star px, semicolon, star px equals star py, semicolon, star py equals temp, semicolon, close curly brace. There are a variety of other options that can be added to the sorting program. Some make challenging exercises. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 6, Structures. A structure is a collection of one or more variables, possibly of different types, grouped together under a single name for convenient handling. While we talk about data structures and how to use them in every language, this section is about understanding how software developers carefully control the low-level shape of their data items to solve their problems. When you first learn about the C struct keyword, you might think it's equivalent to a Python dict, a dynamic key value store like a PHP array, Java, MyApp, or JavaScript object, but nothing is further from the truth. These other languages provide us with easy-to-use data structures where all of the challenging problems are solved. This chapter tells, or told, the creators of Python, PHP, Java, and JavaScript how to solve the complex problems and build convenient and flexible data structures, which we now all use in those object-oriented languages. One way to look at this code in this chapter is to think of it as a lesson on how one might build Python's list and dict data structures. If the code in the chapter takes you a little while to figure out, mentally make a note of thanks for all the hard work that modern languages invest to make their high-level data structures flexible and easy to use. Back to the textbook. The traditional example of a structure is a payroll record. An employee is described as a set of attributes such as name, address, social security number, salary, etc. Some of these in turn could be structures. A name has several components, as does an address and even a salary. Structures help organize complicated data, particularly in large programs, because in many situations they permit a group of related variables to be treated as a unit instead of separate entities. In this chapter, we'll try to illustrate how structures are used. The programs that we will use are bigger than many others in the book, but are still of modest size. Section 6.1 Basics. Let us revisit the date conversion routines of Chapter 5. A date consists of several parts, such as the day, month, and year, and perhaps the day of the year and the month name. These 5 variables can all be placed in a single structure, like this. Struct date, open curly brace, int day semicolon, int month semicolon, int year semicolon, int year day semicolon, char mun name, open square bracket 4, close square bracket semicolon, curly brace, semicolon. The keyword struct introduces a structure declaration, which is a list of declarations enclosed in braces. An optional name called the structure tag may follow the word struct, as with date here. The tag names this kind of a structure and can subsequently be used as shorthand for the detailed declaration. The elements or variables mentioned in a structure are called its members. A structure, member, or tag and ordinary, i.e. non-member variable, can have the same name without conflict, since they are always distinguished by context. Of course, as a matter of style, one would normally use the same names only for closely related objects. The right brace that terminates the list of members may be followed by a list of variables, just as for any basic type. That is, struct, open curly brace, ... close curly brace, x, y, z, semicolon, is syntactically analogous to int x, y, z, semicolon, in the sense that each statement declares x, y, and z to be variables of the named type and causes space to be allocated for them. A structured declaration that is not followed by a list of variables allocates no storage. It merely describes a template or the shape of the structure. If the declaration is tagged, however, the tag can be used in later definitions of the actual instances of the structure. For example, given the declaration of date above, struct date D defines a variable D, which is a structure of type date. An external or static structure can be initialized by following its definition with a list of initializers for the components. Struct date D equals open curly brace 14, 7, 1776, 186, double quote JUL, double quote, close curly brace, semicolon. A member of a particular structure is referred to in an expression by construction of the form structure name dot member. The structure member operator dot connects the structure name and the member name. To set leap from the date in structure D, for example, leap equals d dot year modulo 4 double equals 0 and d dot year modulo 100 not equal to 0, or d dot year modulo 400 double equals 0, semicolon. Or to check the month name, if open paren strcomp open paren d dot mon name, comma, double quote aug double quote, close paren double equals 0, close paren dot dot dot. Or, to convert the first character of the month name to lowercase, d.munname sub 0 equals lower open paren d.munname sub 0, close paren, semicolon. Structures may be nested. A payroll record might actually look like struct person open curly brace, char name open square bracket name size close square bracket semicolon, char address open square bracket address size close square bracket semicolon, long zip code semicolon, long SS number semicolon, double salary, struct date birth date semicolon, struct date hire date semicolon, close curly brace semicolon. The person structure contains 2 dates. If we declare emp as struct person emp semicolon, then emp.birthdate.month refers to the month of birth. The structure member operator dot associates left to right. Section 6.2, Structures and Functions. There are a number of restrictions on C structures. The essential rules are that only operations you can perform on a structure are to take its address with ampersand and access one of its members. This implies that structures may not be assigned or copied to as a unit, and that they cannot be passed or returned from functions. These restrictions will be removed in forthcoming versions. Bonus structures do not suffer these limitations, however, so structures and functions do work together comfortably. Finally, Automatic structures, like automatic arrays, cannot be initialized. Only external or static structures can. This prediction was indeed accurate. Modern C compilers do support the copying of a structure with a single assignment statement. Given that a C structure is just a fixed length block of memory, it's easy to generate machine code to copy it. A key bit to remember that when the C structure is copied, it is done as a shallow copy. A shallow copy copies the values of the variables and the pointers in the structure, but does not make copies of any data which the pointers point to. A structure that contains other structures, i.e. not pointers to structures, then those structures are shallow copied as well. Back to the text. Let us investigate some of these points by rewriting the date conversion functions in the last chapter to use structures. Since the rules prohibit passing of a structure to a function directly, we must either pass the component separately or pass a pointer to the whole thing. The first alternative uses of day of year, which as we wrote in chapter 5. d.yearday equals day of year, open paren, d.year, comma, d.month, comma, d.day, close paren, semicolon. The other way is to pass a pointer. If we've declared higher date as struct date, higher date, semicolon, and rewritten day of year, we could then say higher date.yearday equals day of year, open paren, ampersand, higher date, close paren, semicolon. To pass a pointer to higher date to day of year, the function has to be modified because its argument is now a pointer rather than a list of variables. This example code is on page 122 of the textbook, and you can see it at www.cc4e.com/code. Struct date, open curly brace, int day, semicolon, int month, semicolon, int year, semicolon, int year day, semicolon, int mon name, open square bracket 4, close square bracket, semicolon, close curly brace, semicolon. Static int daytab, open square bracket 2, close square bracket, open square bracket 13, close square bracket, equals, open curly brace, 0, 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31, close curly brace, comma, and then another list just as long as that with a close curly brace and a semicolon. That just initialized the lookup table for the days in each month. Now on to the function. Day of year, open paren, PD, close paren, struct date star PD, semicolon, open curly brace, int I, comma, day, comma, leap, semicolon. Day equals PD minus greater than day, semicolon. Leap equals PD minus greater than year, %4, double equals 0, and PD minus greater than year, %100, not equal to 0, or PD minus greater than year, %400, double equals 0, semicolon. For, open paren, I equals 1, semicolon, I less than PD minus greater than month, semicolon, I plus plus, close paren, day plus equals day tab, open square bracket leap, close square bracket, open square bracket I, close square bracket, semicolon. Return, open paren, day, close paren, semicolon, close curly brace. The declaration struct date star PD says that PD is a pointer to a structure of type date. The notion exemplified by PD minus greater than year. I think I'll call that at this point PD right arrow, because that's really what it is. It's the minus greater than looks like an arrow to the right. So I'm going to call it right arrow, but it's really 2 characters. PD right arrow year is new. If P is a pointer to a structure, then PD right arrow member of structure refers to the particular member. The operator right arrow is a minus sign followed by a greater than. Since PD points to the structure, the year member could also be referenced as open paren star PD close paren dot year. But pointers to structures are so frequently used that the right arrow notation is provided both as a convenient shorthand. The parentheses are necessary in open paren star PD close paren dot year because the precedence of the structure member operator dot is higher than the pointer lookup operator asterisk. Both right arrow and dot associate from left to right. So P, right arrow, Q, right arrow, mem, and emp.birthdate.month are open paren P, right arrow, Q, close paren, right arrow, mem, and open paren emp.birthdate, close paren, .month. For completeness, here is the other function, month day, rewritten to use the structure. This is the first example on page 123 of the text, which you can look at the source code at www.cc4e.com/code. I won't read the struct and the struct date definition and the struct int, static int day tab definition. We'll just go month day. Month day, open paren, PD, close paren, struct date, star PD, semicolon, open curly brace, int I, comma, leap, semicolon. Leap equals PD right arrow year, %4 double equals 0, and PD right arrow year, %100 not equal to 0, or PD right arrow year, %400 double equals 0, semicolon. PD right arrow day equals PD right arrow year day. 4, open paren I equals 1, semicolon, PD right arrow day greater than day tab sub leap sub I, semicolon, I++, close paren. PD right arrow day minus equals day tab sub leap sub I, semicolon, PD right arrow month equals I, semicolon, close curly brace. The structure operators right arrow and dot, together with parentheses for argument lists and square brackets for subscripts, are the top of the precedence hierarchy and then thus bind very tightly. For example, given the declaration struct, open curly brace, int x, int star y, semicolon, close curly brace, star p, semicolon, then plus p right arrow x increments x, not p, because the implied parenthesization is plus open paren p right arrow x, close paren. Parentheses can be used after the binding, open paren plus p right arrow x increments p before accessing x, and open paren p plus close paren right arrow x increments p afterward. The last set of parentheses is unnecessary. In the same way, star p right arrow y fetches whatever y points to. Star p right arrow y plus increments y after accessing whatever it points to, just like star s plus. Open paren star p right arrow y close paren plus increments whatever y points to, and star p plus right arrow y increments p after accessing whatever y points to. Section 6.3, Arrays of Structures. Structures are especially suitable for managing arrays of related variables. For instance, consider a program to count the occurrences of each C keyword. We need an array of character strings to hold the names and an array of integers to hold the counts. One possibility is to use two parallel arrays, keyword and key count, as in char star keyword, open square bracket, n keys, close square bracket, semicolon, int key count, open square bracket, n keys, close square bracket, semicolon. But the very fact that the arrays are parallel indicates a different organization is possible. Each keyword entry is really a pair. Char star keyword, semicolon, int key count, semicolon. And there's an array of the pairs. The structure declaration, struct key, open curly brace, char star keyword, semicolon, int key count, semicolon, close curly brace, key tab, open square bracket, n keys, close square bracket, semicolon, defines an array key tab of structures of this type and allocates storage to them. Each element of the array is a structure. This could also be written struct key, open curly brace, char star keyword, semicolon, int key count, semicolon, close curly brace, semicolon, struct key, key tab, open square bracket, n keys, close square bracket, semicolon. Since the structure key tab actually contains a constant set of names, it's easiest to initialize it once and for all when it's defined. The structural initialization is quite analogous to the earlier ones. The definition is followed by a list of initializers enclosed in braces. Struct key, open curly brace, char star keyword, semicolon, int key count, semicolon, close curly brace, key tab, open square bracket, close square bracket, equals, open curly brace, double quote, break, comma, 0, comma, double quote, case, comma, 0, comma, double quote, char, comma, 0, comma, and so forth, down to double quote, unsigned, double quote, comma, 0, comma, double quote, while, double quote, comma, 0, close curly brace, semicolon. These initializers are listed in pairs corresponding to the structure members. It would be more precise to enclose initializers for each row or structure in the braces, as in open curly brace, double quote, break, double quote, comma, 0, close curly brace, comma, open curly brace, double quote, case, double quote, comma, 0, close curly brace, comma, and so forth. But the inner braces are not necessarily when the initializers are simple variables or character strings, and when all are present. As usual, the compiler will compute the number of entries in the array key tab if the initializers are present and the open square bracket, close square bracket is left empty. The keyword counting program, which begins with a definition of key tab. The main routine reads the input repeatedly by calling a function getWord that fetches input one word at a time. Each word is looked up in key tab with a version of the binary search function we wrote in Chapter 3. Of course, the list of keywords has to be given in increasing order for this to work. Here's the first example on page 125 of the textbook. You can see this at www.cc4e.com/code. Pound include stdio.h. Pound define max word 20. Pound define letter, quote, a quote. Main, open paren, close paren, open curly brace. Int n comma t, semicolon. Char, word, open square bracket, max word, close square bracket, semicolon. While, open paren, t equals get word, open paren, word, comma, max word, close paren, not equal EOF, close paren. If, open paren, t double equal letter, close paren, if, double, open paren, n equals binary, open paren, word, comma, key tab, comma, n keys, close paren, greater than or equal to 0, close paren, key tab, sub n, dot, key count, plus, plus. For, open paren, n equals 0, semicolon, n less than n keys, semicolon, n plus, plus. If open paren key tab sub n dot key count greater than 0, close paren, printf, double quote, %4d space %s backslash n double quote, comma, key tab sub n dot key count, comma, key tab sub n dot keyword, close paren, semicolon, and then a close curly brace to finish main. Binary, to find the word in the table. Binary, open paren, word, comma, tab, comma, n, close paren. Char star word, semicolon. Struct key tab, open square bracket, close square bracket, semicolon. Int n. Open curly brace. Int low, comma, high, comma, mid, comma, cond. Low equals 0, semicolon. High equals n minus 1, semicolon. While, open paren, low less than or equal to high, close paren, open curly brace. Mid equals paren, low plus high, close paren, over 2, semicolon. If, open paren, cond equals stir comp, open paren, word, comma, tab, comma, open square bracket, mid, close square bracket, dot keyword, close paren, less than 0, close paren, high, equals mid minus 1, semicolon. Else if, open paren, con, greater than 0, close paren, low equals mid plus 1, semicolon, else, return, open paren, mid, close paren, semicolon, close curly brace to finish the while, and then return, open paren, minus 1, close paren, semicolon, close curly brace. And that's really a rewrite of the binary function from the earlier part where we were just taking the keyword and the count and looking up in the array but then using the dot keyword to find the actual keyword. Back to the text. We'll show function getWord in a moment. For now, it suffices to say it returns a letter each time it finds a word and copies the word into its first argument. The quantity n keys is the number of keywords in KeyTab. Although we could count this by hand, it's a lot easier and safer to do it by machine, especially if the list is subject to change. One possibility would be to terminate the list of initializers with a null pointer, and then the loop along KeyTab just runs until the end is found. But this is more than is needed, since the size of the array is completely determined at compile time. The number of entries is just the size of KeyTab divided by the size of the struct key. C provides a compile time unary operator called sizeOf, which can be used to compute the size of any object. The expression sizeOf open paren object close paren yields an integer equal to the size of the specified object. The size is given in unspecified units called bytes, which are the same size as a char, close paren. The object can be an actual variable or an array or structure, or the name of a basic type like int or double, or the name of a derived type like a structure. In our case, the number of keywords is the array size divided by the size of one array element, and this computation is used in a pound define statement to set the value of n keys. Pound define n keys, open paren sizeOf open paren KeyTab close paren divided by sizeOf open paren struct key close paren close paren. Now for the function getWord. We have actually written a more general getWord than is necessary for this program, but it is not really much more complicated. GetWord returns the next word from the input, where a word is either a string of letters or digits beginning with a letter or a single character. The type of the object that is the returned function as a function value. It is the letter if the token is a word, EOF for end of file, or the character itself if it's non-alphabetic. This sample code is on page 127 of the textbook, which you can see at www.cc4e.com/code. Pound define letter, quote, a quote. Pound define digit, quote, 0 quote. GetWord, open paren, w, comma, lim, close paren. Char, star w, colon, semicolon. Int, lim, semicolon, open curly brace. Int, c, comma, t, semicolon. If, open paren, type, open paren, c, equals star w plus plus, equals get ch, open paren, close paren, not equal letter, close paren, open curly brace, star w equals, quote, \0, quote, semicolon. Return, open paren, c, close paren, semicolon, close curly brace. That if statement has got some stuff going on in it. You might want to look at it very closely. While, open paren, minus minus lim, greater than 0, close paren, open curly brace, t equals type, open paren, c equals star w plus plus equals get ch, open paren, close paren, semicolon. If open paren, t not equal letter and t not equal digit, close paren, open curly brace, unget ch, open paren, c, close paren, semicolon, break, semicolon, close curly brace, star, open paren, w minus 1, close paren, equals, quote, \0, quote, semicolon, return, open paren, letter, close paren, semicolon, close curly brace, close curly brace. That example code has a lot of stuff about pointers and incrementing pointers and dereferencing pointers, etc. So take a good look at that code. Back to the text. GetWord uses the routines getCH and ungetCH, which we wrote in Chapter 4. When the collection of an alphabetic token stops, GetWord has gone one character too far. That call to ungetCH pushes that character back on the input for the next call. GetWord calls another function called type to determine the type of each individual character for input. Here is a version that's only for ASCII. This code is the second example on page 127 of the textbook at www.cc4e.com/code. Type open paren c close paren, int c semicolon. If, open curly brace. If open paren C greater than or equal to quote A quote and C less than or equal to quote Z quote, or C greater than or equal to quote uppercase A quote and C less than or equal to quote uppercase Z quote close paren, return letter semicolon. Else if open paren C greater than or equal to quote 0 quote and C less than or equal to quote 9 quote close paren, return open paren digit close paren semicolon. Else return open paren C close paren semicolon. Close curly brace. The symbolic constants, letter, and digits can have any values that do not conflict with non-alphanumeric values and EOF. The obvious choices are quote A quote and quote 0 quote. Get word can be faster if calls to the function type are replaced by references to the appropriate array type. The standard C library provides macros like isAlpha and isDigit, which operate in this manner. Section 6.4, Pointers to Structures. To illustrate some of the considerations involved with pointers and arrays of structures, let us write a keyword counting program again, this time using pointers instead of array indices. As an aside, I would note that it's a classic early assignment in any programming language to do a word frequency program. Here is a Python program from my Python for Everybody course to count words from an input stream. Handle equals open parenthesis, single quote, Romeo.txt, close, single quote, comma, quote, R quote, close parenthesis. Words equals handle.read, open paren, close paren, dot split, open paren, close paren. Counts equals dict, open paren, close paren. For word in words, colon, counts subword equals counts.get, open paren, word, comma, 0, close paren, plus 1. Print, open paren, counts, close paren. This section in this book implements a less general word counting program in C. The code depends on several functions from earlier in the book, and the code below is pretty complex, where the programmer only has access to low-level language without powerful and easy-to-use data types, like Python's list or dict. It is likely that Guido van Rossum read this book, took a long look at this code, and designed the dict data structure in Python so the rest of us could write a data parsing and word frequency program in the above 6 lines of code without worrying about dynamic memory allocation, pointer management, string length, and a myriad of other details that must be solved when you're solving this program in C. Since Python is open source, you can actually look at the C code that implements the dict object in a file called dictobject.c. It is almost 6,000 lines of code and includes other files or utility code. Thankfully, we only have to write one line of Python to use it. Counts equals dict, open paren, close paren. We will leave the complex bits to the C programmers that build and maintain. This section is not showing us how to use the Python dict object. Rather, it is showing how one would build a dict-like structure using C. So, continuing with section 6.4, pointers to structures. The external definition of key tab do not need to change, but main and binary do need modification. This is example on page 129 of the textbook, and that is available at www.cc4e.com/code. Pointer version of counting C keywords. Main, open paren, close paren, open curly brace, int t semicolon. Char word, open square bracket, max word, close square bracket, semicolon. Struct key, star binary, open paren, close paren, comma, star p, semicolon. While, open paren, t equals get word, open paren, word, comma, max word, close paren, not equal EOF, close paren. If, open paren, t equal letter, close paren. If, open paren, b equals binary, open paren, word, comma, key tab, comma, n keys, close paren, not equal null, close paren. P, right arrow, key count, plus plus. For p equals key tab, p less than key tab plus n keys, semicolon, p plus plus, close parenthesis. If, open paren, p right arrow, key count greater than 0, close paren, printf, open paren, double quote, %4d space %s, \n, double quote, comma, p right arrow key count, comma, p right arrow keyword. And now we look at the binary search. Struct key star binary, open paren word, comma, tab, comma, n, close paren, char star word, struct key tab, open square bracket, close square bracket, semicolon, int n, open curly brace, int cond, semicolon, struct key star low equals ampersand tab sub 0, semicolon, struct key star high equals ampersand tab sub n minus 1, semicolon, struct key equals mid. While open paren low less than or equal to high, close paren, open curly brace. Mid equals low plus high minus low divided by 2. If open paren, cond equals strcomp word, comma, mid, right arrow keyword, close paren, less than 0, close paren, high equals mid minus 1, semicolon. Else if, close paren, cond greater than 0, close paren, low equals mid plus 1, semicolon. Else return open paren, mid, close paren, semicolon, close curly brace to finish the while, and then return open paren, null, close paren, close curly brace. There are several things worthy of note here. First, the declaration of binary must indicate that it returns a pointer to the structure type key instead of an integer. This is declared both in main and in binary. If binary finds the word, it returns a pointer to it. If it fails, it returns null. Second, all the accessing elements of keydab is done by pointers. This causes one very significant change in binary. The computation of the middle element can no longer be simply mid equals paren low plus high, close paren, divided by 2, because the addition of 2 pointers will not produce any kind of useful answer, even when divided by 2, and is fact illegal. This must be changed to mid equals low plus open paren high minus low, close paren, divided by 2, which sets mid to the point to the element halfway between low and high. You should also study the initializers for low and high. It is possible to initialize a pointer to the address of a previously defined object, and that is precisely what we have done here. In main, we wrote for open paren p equals keytab semicolon, p less than keytab plus n keys semicolon, p plus plus close paren. If p is a pointer to a structure, any arithmetic on p takes into the account the actual size of the structure. So p plus plus increments p by the correct amount to get to the next element in the array of structures. But don't assume that the size of a structure is the sum of the sizes of its members, because alignment requirements for different objects potentially may cause holes in the structure. Finally, an aside on program format. When a function returns a complicated type, as in struct key star binary open paren word, comma, tab, comma, n, close paren, the function name can kind of be hard to see and or find with a text editor. Alternately, another style is sometimes used. On 2 lines now, struct key star on the first line, and binary open paren word, comma, tab, comma, n, close paren. The spacing is mostly a matter of personal taste. Pick the form you like and hold to it. Section 6.5, Self-Referential Structures. Before we start this section, a slightly longer aside from your narrator. Up to now, I've resisted the temptation to augment the book with my own bits of code. But we have reached the single point in the book where I feel that there is too big of a conceptual leap between 2 sections, so I'm going to add some of my own narrative between sections 6.4 and 6.5. The rest of this chapter talks very nicely about binary trees and hash tables, both essential low-level data structures in computer science, and both excellent ways to understand pointers, and how C can be used to build data structures like the Python dictionary. However, the author skips separately describing the structure of a dynamically constructed linked list, which is the first and foundational collection data structure in computer science, and should be understood before moving to tree and hash map structures. Linked lists form the foundation of the Python list object, Java array object, PHP numeric key arrays, and JavaScript arrays. The linked list can be dynamically extended, and items can be added in the middle efficiently as well as being pushed or popped on or off the front or back of the list. Linked lists are used also to implement queues as well as other aspects of operating system. I will attempt to mimic the author's writing style in this new section of the book. I'll write some sample code using a more modern dialect of C so it's easier to run on a modern compiler. Section 6.5.1, Linked Lists, Bonus Content. Suppose we want to read a file and print the file in reverse order. We don't know how many lines will be in the file before we read the file, so we can't simply use an array of pointers to strings and character arrays, like lines. In a sense, we need a dynamic array that grows as we encounter new lines. When we reach the end of the file, we then just loop through our stored lines from the end to the beginning so we can print them out in reverse order. One solution is to make a data structure called a doubly linked list of character strings. In addition to each line of data, we will store a pointer to the previous line and the next line as well as a pointer to the first item we add to the list, and then we'll call this the head of the list, and then the most recent item we've added to the list, which we'll call the tail of the list. We will see a singly linked list as part of the hash map data structure in a following section. A single linked list can only be traversed in a forward direction. A doubly linked list can be traversed either forwards or backwards. Given that our linked list of strings will keep expanding as we get new lines, we avoid hard-coding array sizes like #define maxlen 1000 in the previous chapter. We were building a program to sort a file. Going back to the description of a line in our doubly linked list, it is clearly a structure with three components: struct lnode open curly brace, char star text semicolon, struct lnode star prev semicolon, struct lnode star next semicolon, close curly brace. This recursive definition of lnode might look chancy, but it's actually quite correct. It is illegal for a structure to contain an instance of itself, but struct lnode star prev declares prev to be a pointer to an lnode, not an lnode itself. We'll write this code in a more modern C dialect using modern memory allocation and I/O routines provided by the standard C library. This code is on page 130 of the textbook, available at www.cc4e.com/code. #include stdio.h, #include stdlib.h, #include string.h, #define maxline 1000. This is the length of the line, not the number of lines. Struct lnode open curly brace, char star text semicolon, struct lnode star prev semicolon, struct lnode star next semicolon, close curly brace semicolon. Now we have our main program to print the lines in reverse. And we will use int main open paren close paren because we're coding in a modern dialect of C. Open curly brace. Struct lnode star head equals null semicolon. Struct lnode star tail equals null semicolon. Char line, submax line, semicolon. While open paren fgetS open paren line, comma max line, comma stdin, close paren not equal null, close paren open curly brace. Char star save equals open paren char star, close paren malloc, open paren stirlen, open paren line, close paren +1, close paren semicolon. Stir copy, save comma line. Struct lnode star new equals open paren struct lnode star close paren malloc open paren size of struct lnode close paren semicolon. New right arrow text equals save, new right arrow next equals null, new right arrow prev equals tail, and tail equals new. If head equals null, close paren, head equals new, semicolon. Close curly brace to finish the while. Now we'll print it all out. For open paren struct lnode star current equals tail, semicolon, current not equal to null, semicolon, current equals current right arrow prev, close parenthesis, open curly brace, printf, open paren, double quote, S, close, double quote, comma, current right arrow text, close paren, semicolon, close curly brace to finish the for, and then close curly brace to finish the main. Interestingly, if we wanted to print the list in forward order, or if we did have only a singly linked list, our loop would look as follows. For open paren struct lnode star current equals head, semicolon, current not equal to null, semicolon, current equals current right arrow next, close paren, open curly brace. Printf, open paren, double quote, %s, double quote, comma, current right arrow text, close paren, semicolon, close curly brace. In general, we use the variable names head, tail, and current, as well as next and prev, or similar names when writing code that builds or uses a linked list, so other programmers will quickly understand what we are talking about. After a while, reading a for loop to traverse a linked list becomes as natural as reading a for loop that progresses through a sequence of numbers. Section 6.5.2, Binary Trees. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. Since the list of words isn't known in advance, we can't conveniently sort it and use a binary search. Yet we can't do a linear search for each word that has arrived to see if it's already been seen. The program would take forever. More precisely, what is the expected running time? And it would grow quadratically with the number of input words. How can we organize the data to cope efficiently with a list of arbitrary words? Our solution is to keep the set of words seen so far sorted at all times by placing each word into its proper position in the order as it arrives. This shouldn't be done by shifting the words in a linear array, though. That takes too long. Instead, we will use a data structure called a binary tree. The tree contains one node per distinct word. Each node contains a pointer to the text of the word, a count of the number of occurrences of the word, a pointer to the left child node, and a pointer to the right child of node. No node may have more than two children. It might have only 0 or 1. The nodes are maintained so that any node in the left tree contains only words that are less than the words at the node, and the right tree only contains words that are greater. To find out whether a new word is already in the tree, one starts at the root and compares the new word to the word starting at that node. If they match, we found it. If the new word is less than the tree word, the search continues down the left. Otherwise, the right child is searched. If there is no child in the required direction, then the word is not in the tree. And in fact, the proper place for it to be is the missing child. This search process is inherently recursive, since the search from any node uses a search from one of its children. Accordingly, recursive routines for inserting and printing will be the most natural. Going back to the description of a node, it is clearly a structure with 4 components. Struct tnode, open curly brace. Char star word, int count, semicolon. Struct tnode star left, semicolon. Struct tnode star right, semicolon, close curly brace. This recursive declaration of a node might look chancy, but actually it's quite correct. It's illegal for a structure to contain an instance of itself, but struct tnode star left semicolon declares left to be a pointer to a node, not a node itself. The code for the whole program is surprisingly small, given the handful of supporting routines that we've already written. These are getWord to fetch input and alloc to provide space for squirreling the words away. The main routine simply reads words with getWord, installs them in the tree with tree. This is the first example on page 131 of the textbook, which you can see at www.cc4e.com/code. Pound include stdio.h. Pound define max word 20. Pound define letter, single quote A, single quote. Main, open paren, close paren, open curly brace. Struct tnode, star root, comma, star tree, open paren, close paren, semicolon. Char word, open square bracket, max word, close square bracket, semicolon. Int t, semicolon. Root equals null. While, open paren, t equals getWord, open paren, word, comma, max word, close paren, not equal EOF, close paren, If open paren t double equal letter, close paren, root equals tree, open paren, root, comma, word, close paren, semicolon. Tree print, open paren, root, close paren, semicolon, close curly brace. Tree itself is straightforward. A word is presented by main to the top level root of the tree. At each stage, that word is compared to the word already stored at the node and is percolated down either to the left or right subtree by a recursive call to tree. Eventually, the word either matches something already in the tree, in which case the count simply is incremented, or a null pointer is encountered, indicating the node must be created and added to the tree. If a new node is created, tree returns a pointer to it, which is installed in the parent node. This is the example on page 132 of the textbook at www.cc4e.com/code. Pound includes string.h, struct, tnode, open curly brace, char, star word, semicolon, int, count, semicolon, struct, tnode, star left, semicolon, struct, tnode, star right, semicolon, close curly brace, semicolon. Struct, tnode, star tree, open paren, p, comma, w, close paren. We're going to install w at or below p. Struct, tnode, star p, semicolon, char, star w, open curly brace. Struct, tnode, star t alloc, open paren, close paren, semicolon, char, star stir save, open paren, close paren, semicolon, int cond, semicolon. If open paren p double equal null, close paren, open curly brace. We've got a new word. P equals t alloc, open paren, close paren, to make a new node. P right arrow word equals stir save, open paren, w, close paren, semicolon. P right arrow count equals 1. P right arrow left equals P right arrow right equals null. Close curly brace. Else if open paren, cond equals stir comp, w, comma, p, right arrow word, close paren, double equals 0, close paren, p, right arrow count, plus, plus. Indicate that we've seen the word one more time. Else if open paren, cond less than 0, close paren, lower will go into the left part of the tree. P right arrow left equals tree, P right arrow left, comma, W, close paren, semicolon. Else, P right arrow right equals tree, open paren, P right arrow right, comma, W, close paren, semicolon. Return, open paren, P, close paren, semicolon, close curly brace. And that's a bit of code. It's not much, and it's beautiful. Recursion is happening. The return P at the very end is really, really important because we're kind of always overriding it, but we're okay. So the overriding works its way back up to the recursion because it's recursive, it's using pointers, away we go. Back to the text. Storage for the new node is fetched by a routine called talloc, which is an adaptation of the alloc we wrote earlier. It returns a pointer to a free space suitable for holding a tree node. We'll discuss this more in a moment. The new word is copied to a hidden place by stir save. The count is initialized and the two children are made null. This part of the code is executed only at the edge of the tree when a new node is being added. We have, unwisely for a production program, omitted error checking on the values returned by stir save and talloc. Tree print prints the tree in left subtree order. At each node, it prints its left subtree, all the words less than this word, then the word itself, then the right subtree, all the words greater. If you feel shaky about recursion, draw yourself a tree and print it with tree print. It's one of the cleanest recursive routines you can find. This example code is on page 133 of the textbook, which you can see at www.cc4e.com/code. I won't read the struct tnode code, just tree print. Tree print, open paren, P, close paren. struct tnode star p semicolon, open curly brace, if open paren p not equal to null, close paren, curly brace, open curly brace, tree print, open paren p right arrow left, close paren, semicolon, printf, percent 4d space percent s backslash n double quote, comma, p right arrow count, comma, p right arrow word, close parenthesis, semicolon. Tree print, open paren, p right arrow right, close paren, semicolon. Close curly brace for the if, and then close curly brace for the tree print function. Again, I agree with the authors, and that is one of the cleanest and most beautiful and most applicable uses of recursion that you will probably ever see in all your career. I'm not a fan of recursion in all cases, but you really can't do this any other way well. Back to the text. As a practical note, if the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too fast. As a worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree, notably 2-3 trees, AVL trees, and I would add balanced binary trees, which do not suffer from this worst case behavior, but we will not describe them here. Before we leave this example, it's also worth a brief digression on a problem related to storage allocators. Clearly, it's desirable that there only be one storage allocator in a program, even though it allocates different kinds of objects. But if one allocator is to process requests for, say, pointers to chars and pointers to struct tnodes, two questions arise. First, does it meet the requirement of most real machines that objects of a certain types must satisfy alignment restrictions? For example, integers must often be located on even addresses. Second, what declarations can cope with the fact that alloc necessarily returns different kinds of pointers? Alignment requirements can generally be satisfied easily at the cost of some wasted space merely by ensuring the allocator always returns a pointer that meets all alignment restrictions. For an example, on the PDP-11, it is sufficient that alloc always returns an even pointer since any type of object may be stored at an even address. The only cost is a wasted character on the odd length requests. Similar actions are taken on other machines. Thus, the implementation of alloc may not be portable, but its usage is. The alloc of Chapter 5 does not guarantee any particular alignment. In Chapter 8, we'll show how to do the job right. As an aside, by now you know that when the authors mention the PDP-11, they are sharing some aspects of the challenge of making C work on previous generation computers with short memory words and small amounts of memory, and at the same time making them work well on the incoming generation of computers with larger words and more memory. The research, thought, and care that went into making sure the C code was portable across multiple generations of computer hardware is on display in the previous paragraph. The question of the type declaration for alloc is a vexing one for any language that takes its type checking seriously. In C, the best procedure is to declare that alloc returns a pointer to char and then explicitly coerce the pointer into the desired type with a cast. Therefore, if P is declared as char star P semicolon, then open paren struct tnode star close paren P converts it into a tnode pointer expression. Thus, talloc is written as struct tnode star talloc open paren close paren, open curly brace, char star alloc, return open paren struct tnode star close paren, alloc open paren size of open paren struct tnode close paren close paren close paren. This is more than is needed for current compilers, but represents the safest course for the future. I would add that these concerns that the authors mention in this section are also nicely resolved in modern C compilers. In the NC version of C, they introduced the notion of the void type. The void type indicates the lack of a type, much like null is used to indicate not a valid pointer or not a flying toy. In 1978, because the char type was generally the most native type on any system, it was often used as the generic pointer needed to return memory from an allocation function. In modern C, we use pointers to void and then cast the returning pointer to be a pointer to whatever struct or other data we just allocated. If we were writing alloc, the alloc routine in this book using modern C, it would return a pointer to void. The 1978 version is char star alloc open paren close paren, and the modern version is void star alloc open paren close paren. We've left the book alone. We haven't used void throughout the book, but it is a testament to the foresight of the authors that all the pointer casting code in this book still works today the same, regardless of whether the memory allocation functions return char or void pointers to the allocated data. Section 6.6, Table Lookup. As an aside, in this section, we finish our quick tour of the implementations of the 3 core data structures in computer science. 1, the linked list, 2, the tree, and 3, the hash map, as described in this section. A singly linked list is also part of a hash map implementation, so you can compare it to the doubly linked list code introduced in the earlier bonus section 6.5.1. This section is worth understanding well because not only is it an excellent review of pointers and structures, but also because one of the most common questions on a face-to-face programming interview is, draw a hash map on the whiteboard and explain how it works. This is an easy question if you study and understand this section of the book, and almost impossible if you have not. In some ways, this section is the most intricate data structure that's described in the book. It is why it is so popular in coding interviews. Chapters 7 and 8 talk about lots of practical things like input-output of the UNIX operating system. Elegant data structures and their use are core concepts in computer science. Understanding them highlights the difference between a good programmer and a computer scientist. In a sense, understanding how a hash map is the secret handshake of computer science. And it is the secret handshake because of this book and this section of this book, written back in 1978 and used in a course that the person interviewing you may have took when they were in college. Hash maps were difficult for them to understand back then, and so if you understand the concept, then you must be solid. So I hope you pay close attention to this section and remember the handshake. Back to the text. In this section, we will write the innards of a table lookup package as an illustration of more aspects of structures. This code is typical of what might be found in the symbol table management routines of a macro processor or a compiler. For example, consider the C #define statement. When a line like #define yes 1 is encountered, the name yes and the replacement text 1 are stored in a table. Later, when the name yes appears in a statement like in-word equals yes semicolon, it must be replaced by 1. There are 2 major routines that manipulate the names and replacement text. Install open paren s, t, close paren, records the name s and the replacement t in the table. S and t are just character strings. Lookup open paren s, close paren, searches for s in the table and returns a pointer to the place where it was found, or null if it wasn't there. The algorithm used is a hash search. The incoming name is converted to a small positive integer, which is then used to index into an array of pointers. An array element points to the beginning of a chain of blocks describing the names that have the hash value, and if it is null, then no names have hashed to that value. A block in the chain is a structure containing pointers to the name, the replacement text, and the next block in the chain. A null next pointer marks the end of the chain. Struct endlist open paren, char star name semicolon, char star def semicolon, struct endlist star next semicolon, close curly brace semicolon. The pointer array is just #define hash size 100, static struct endlist star hash tab open square bracket hash size close square bracket semicolon. The hashing function, which is used by both lookup and install, simply adds up the character values in the string and forms the remainder modulo the array size. This is not the best possible algorithm, but it has the merit of extreme simplicity. Hash open paren s close paren, char star s semicolon, open curly brace, int hash val. For open curly brace, hash val equals 0, star s not equal, quote, single quote, backslash 0, single quote, semicolon, close paren. Hash val plus equals star s plus plus, semicolon, return, open paren, hash val modulo, percent, hash size, close paren, semicolon, close curly brace. As an aside, hashing functions are one of the foundational notions in computer science. Hashing functions are used for everything from high-performance in-memory structures, organizing databases, data, digital signing, network packet checksums, security algorithms, and much more. The above text is a really great example of a really simple hashing function. You should understand this simple presentation well so that when you encounter a more complex implementation or use of hashing, you can fall back on this text to understand that at its core, hashing is a very simple concept. So much of this chapter is a succinct example of some of the most powerful concepts in computer science. Please don't look at the 8 lines of code above and think, I got that, and just jump to the next bit. This chapter is showing you the way of the master programmer. Wax on, wax off. Be patient, slow down, and enjoy your time here. Back to the text. The hashing process produces a starting index in the array hash tab. If the string is to be found anywhere, it will be in the chain of blocks beginning there. The search is performed by lookup. If lookup finds the entry already present, it just returns a pointer to it. If not, it returns null. Here's the code. Struct enlist star lookup open paren s close paren, char star s semicolon, open curly brace, struct enlist star np semicolon. For open paren np equals hash tab sub hash open paren s close paren close square bracket semicolon, np not equal null semicolon, np equals np right arrow next close parenthesis. If strcomp open paren s comma np right arrow name close paren double equals 0, return open paren np close paren semicolon, return open paren null close paren semicolon close curly brace. Install uses lookup to determine whether the name installed is already present. If so, the new definition must supersede the old one. Otherwise, a completely new entry is created. Install returns null if for any reason there's no room for a new entry. Struct enlist star install open paren name comma def close paren, jar star name comma star def semicolon, open curly brace, struct enlist star np comma star lookup open paren close paren semicolon, char stir save comma star alloc open paren close paren semicolon, int hash val semicolon. If open paren np equals lookup open paren name close paren double equal null close paren open curly brace, i.e. it's not found, np equals open paren struct enlist star close paren alloc open paren size of open paren star np close paren semicolon. If np equals null, return null. That means the allocation failed. If open paren np right arrow name equals stir save open paren name close paren double equals null close paren, return open paren null close paren semicolon. Hash val equals hash open paren np right arrow name close paren semicolon. np next equals hash tab open square bracket hash val close square bracket second semicolon. Hash tab open square bracket hash val, close square bracket equals NP semicolon. We're actually pushing these new ones to the head of this singly linked list. And so those last two statements push the most recent top of the list forward and then replace with the new one at the top of the list. The list does not stay in any order. So we have a closed curly brace to end all that if for the not found code, close curly brace, else, this is the already there code, free, open paren, NP, right arrow def, close paren, semicolon, free the previous definition. That's the string part of the pound define. If open paren, NP, right arrow def equal stir save, open paren, def, close paren equals null, close paren, return open paren, null, close paren, semicolon, return open paren, NP, close paren, semicolon, close curly brace. So that last bit there was to, if you have a pound define with the same keyword and a different later, you have a different definition, you can replace the definition. And so that last bit was replacing the definition. Again, this code is pretty intricate. It's really both the hash table and a singly linked list going on at the same time. So take a close look at this on page 136 of the book. Stir save merely copies the string given its argument to a safe space obtained by a call to alloc. We've showed this code in chapter 5. Since calls to alloc and free may occur in any order, and since alignment matters, the simple version of alloc is just not adequate here. See more in chapters 7 and 8. As an aside, one of the reasons that the authors make vague forward-looking statements whenever they talk about dynamic memory is that large-scale memory management in a programming language is still a subject of active research 40 years later. Back in 1978, it was absolutely not a settled topic. You can see this when the authors build a simple non-production memory allocation scheme with their own alloc and free routines backed by a fixed-length static extern array of characters. Dynamic allocation is essential to writing competent C programs, but it is likely that the production-grade dynamic memory support was still somewhat non-portable when the book was written, so they used simple, self-contained implementations in this book. Modern dynamic memory support is through the malloc, calloc, and free functions in the standard library. These functions request dynamic memory blocks from the operating system and manage those areas on behalf of your C code. On Unix and Unix-like systems, the memory allocation layer asks the underlying operating systems for blocks of memory through the SBRK interface. Even with virtual memory, programmers must carefully manage their use of dynamically allocated memory because memory is never unlimited. Section 6.7 Fields. When storage space is at a premium, it may be necessary to pack several objects into a single machine word. One especially common use is a set of single-bit flags in applications like compiler symbol tables. Externally imposed data formats, such as interfaces to hardware devices, also often require the ability to get at pieces of a word. As an aside, we are going to go now from low-level programming to even lower-level programming. The Unix operating system is written in C, and Unix needs to have, for example, an implementation of the Internet Protocol so it can be connected to the Internet. One of the most important Internet protocols is the Transmission Control Protocol, TCP. In order to implement TCP, you need to send very precisely formatted data across the network. The data is very tightly packed in order to save precious network bandwidth. The exact format of a TCP header is described in the TCP Wikipedia page. If you look at the header, you will find that at bits 96 through 99, TCP expects a 4-bit integer that defines the data offset. Exactly what this data means is less relevant unless you're actually writing the TCP implementation, but it does demonstrate that we need to control our data layout at times on a bit-by-bit basis. This section covers how we can use struct to build up a TCP header in C, which can be parsed and set without using masking and shifting operations with hard-coded numbers. The section below is simpler than constructing a valid TCP header using a carefully packed struct, but it does lay the groundwork for these more complex situations. Now back to the text. Imagine a fragment of a compiler that manipulates a symbol table. Each identifier in a program has certain information associated with it, for example, whether or not it's a keyword, whether or not it's external and or static, and so on. The most compact way to encode such information is a set of 1-bit flags in a single char or int. The usual way this is done is to define a set of masks corresponding to the relevant bit positions, as in pound-define keyword 01, pound-define external 02, and pound-define static 04. The numbers, of course, must be powers of 2 so that the shifting works. Then accessing the bits become a matter of bit fiddling with shifting, masking, and complementing operators, which were described in Chapter 2. Certain idioms appear frequently. Flags, vertical bar equals external, vertical bar static. Turns on the external and static bits in flags, while flags ampersand equal tilde open paren external or static close paren semicolon turns them off. And if open paren flags ampersand paren external vertical bar static close paren equal 0 ... is true if both bits are off. Although these idioms are readily mastered, as an alternative, C offers the capability of defining and accessing fields within a word directly, rather than by bitwise logical operators. A field is a set of adjacent bits within a single int. The syntax of field definition and access is based on structures. For example, the symbol table pound defines above could be replaced by the definition of 3 fields. Struct unsigned is keyword : 1 semicolon. Unsigned is extern : 1 semicolon. Unsigned is static : 1 semicolon. Close curly brace flags. This defines a variable called flags that contains 3 1-bit fields. The number following the colon represents the field width in bits. The fields are declared unsigned to emphasize that they are really unsigned quantities. Individual fields are referenced as flags.isKeyword, flags.isExtern, etc., just like other structure members. Fields behave like small unsigned integers and may participate in arithmetic expressions just like the other integers. Thus, the previous examples may be written much more naturally as flags is underscore extern equals flags is static equals 1 semicolon. Turn the bits on. Flags is extern equals flags is static equals 1 semicolon to turn the bits on. Flags.isExtern equals flags.isStatic equals 0 turns them off. And if open paren flags.isExtern double equals 0 and flags.isStatic double equals 0 close paren ... to test them. A field may not overlap an int boundary. If the width would cause this to happen, the field is aligned to the next int boundary. Fields need not be named. Unnamed fields with a colon in width only are used for padding. The special width 0 may be used to force alignment to the next int boundary. There are a number of caveats that apply to fields. Perhaps the most significant, fields are assigned left to right on some machines and right to left on others, reflecting the nature of different hardware. This means that although fields are quite useful for maintaining internally defined data structures, the question of which end comes first has to be carefully considered when picking apart externally defined data. Other restrictions to bear in mind: fields are unsigned. They may only be stored in ints or equivalently unsigned. They are not arrays and they do not have addresses, so the ampersand operator cannot be applied to them. Section 6.8 Unions. A union is a variable which may hold at different times objects of different types and sizes, with the compiler keeping track of the size and alignment requirements. Unions provide a way to manipulate different kinds of data in a single area of storage without embedding any machine-dependent information in the program. For example, again from a compiler symbol table, suppose constants may be ints, floats, or character pointers. The value of a particular constant must be stored in a variable of the proper type. Yet it is most convenient for table management if the value occupies the same amount of storage and is stored in the same place, regardless of its type. This is the purpose of a union, to provide a single variable which can legitimately hold one of several types. As with fields, the syntax is based on structures. Union, utag, open curly brace, int ival semicolon, float fval semicolon, char star pval semicolon, close curly brace, uval. The variable uval will be large enough to hold the largest of these three types, regardless of the machine it is compiled on. The code is independent of hardware characteristics. Any one of these types may be assigned to uval and then used in expressions, so long as the usage is consistent. The type retrieved must be the type most recently stored. It is the responsibility of the programmer to keep track of what type is currently stored in a union. The results are machine dependent if something is stored as one type and extracted as another type. Syntactically, members of a union are accessed as unionname.member or union pointer right arrow member. Justice for structures. If the variable utype is used to keep track of the current type stored in uval, then one might see code as if open paren utype double equals int, close paren, printf, paren, double quote, %d \n, double quote, comma, uval dot ival, close paren, semicolon, else if, open paren, utype double equal float, close paren, printf, open paren, double quote, %f \n, double quote, comma, uval dot fval, close paren, semicolon, else if, open paren, utype double equal string, close paren, printf, double quote, %s \n, double quote, comma, uval dot pval, close paren, semicolon, else, printf, open paren, double quote, bad type, %d, and utype, \n, double quote, comma, utype, close paren, semicolon. Unions may occur in structures and arrays and vice versa. The notion for accessing a member of a union in a structure or vice versa is identical to that for nested structures. For example, in the structure array defined by struct, open curly brace, char star name, semicolon, int flags, semicolon, int utype, semicolon, union, open curly brace, int ival, semicolon, float fval, semicolon, char star pval, semicolon, close curly brace, uval, semicolon, close curly brace, symtab, open square bracket, nsim, close square bracket, semicolon. The variable ival is referred to as symtab sub I dot uval dot ival, and the first character of the string pval by star symtab sub I dot uval dot pval. In effect, a union is a structure in which all the members have offset 0. The structure is big enough to hold the widest member, and the alignment is appropriate for all types in the union. As with structures, the only operations currently permitted on unions are accessing a member and taking the address. Unions may not be assigned to, passed to functions, or returned by functions. Pointers to unions can be used in a manner identical to pointers to structures. As an aside, the above limitations on unions are just no longer accurate. Like structures, modern C compilers can assign the contents of the union to another union variable. You can also pass unions into functions by value and receive a union as the return type of a function. The storage allocator in Chapter 8 shows how a union can be used to force a variable to be aligned on a particular kind of storage boundary. Section 6.9 Typedef. C provides a facility called typedef for creating new data type names. For example, the declaration typedef space int space length semicolon makes the name length a synonym for int. The type length can be used in declarations, casts, etc. in exactly the same ways int can be. Length, len, comma, maxlen, semicolon. Length, star lengths, open square bracket, close square bracket, semicolon. Similar, the declaration typedef char star string semicolon makes string a synonym for char star, or a character pointer, which then may be used in declarations like string p, comma, line ptr, open square bracket, lines, close square bracket, comma, alloc, open paren, close paren, semicolon. Note that the type being declared in a typedef appears in the position of a variable name, not right after the word typedef. Syntactically, typedef is like the storage class, extern, static, etc. We've used uppercase letters in these examples to emphasize the names. A more complicated example, we could make typedefs for the tree nodes shown earlier in the chapter. Typedef struct tnode open curly brace, char star word semicolon, int count semicolon, struct tnode star left semicolon, struct tnode star right semicolon, close curly brace, tree node, comma, star tree ptr. This creates two new type keywords called tree node, which is a structure, and tree ptr, which is a pointer to the structure. Then the routine talloc could become tree ptr, talloc, open paren, close paren, open curly brace, char star alloc, open paren, close paren, semicolon, return, open paren, tree ptr, close paren, alloc, open paren, size of, open paren, tree node, close paren, semicolon, close curly brace. It should be emphasized that a typedef declaration does not exactly create a new type in any sense. It merely adds a new name for some existing types, nor are there any new semantics. Variables declared this way have exactly the same property as variables whose declarations are spelled out explicitly. In effect, typedef is like define, except that since it's interpreted by the compiler, it can cope with textual substitutions that are beyond the capabilities of the C macro preprocessor. For example, typedef int open paren star pfi close paren open paren close paren semicolon creates the type pfi to mean pointer to a function returning integer, which can be used in contexts like pfi strcomp, numcomp, swap in the sort program in chapter 5. There are two main reasons for using typedef declaration. The first is to parameterize a program against portability problems. If typedefs are used for the data types, which may be machine dependent, only typedefs need to change when the program is moved. One common situation is to use typedef names for various integer quantities and then make an appropriate set of choices of short, int, and long for each host machine. The second purpose of typedefs is to provide better documentation for a program. A type called tree ptr may be easier to understand than one declared only as a pointer to a complicated structure. Finally, there's always the possibility that in the future the compiler or some other program such as lint may make use of the information contained in typedef declaration to perform some extra checking on the program. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 7, Input and Output. Input and output facilities are not part of the C language, so we've de-emphasized them in our presentation thus far. Nonetheless, real programs do interact with their environment in much more complicated ways than those we've shown before. In this chapter, we will describe the standard I/O library, a set of functions designed to provide a standard I/O system for C programs. The functions are intended to present a convenient programming interface yet reflect only operations that can be provided on most modern operating systems. The routines are efficient enough that users should seldom feel the need to circumvent them for efficiency, regardless of how critical the application. Finally, the routines are meant to be portable, in the sense that they will exist in compatible form on any system where C exists, and that programs which confine themselves to facilities provided by the standard library can be moved from one system to another essentially without change. We will not try to describe the entire I/O library here. We are more interested in showing the essentials of writing C programs that interact with our operating system environment. Section 7.1, Access to the Standard Library. Each source file that refers to the standard library function must contain the line #include stdio.h near the beginning. The file, stdio.h, defines certain macros and variables used by the I/O library. The use of angle brackets, less than and greater than, instead of the usual double quotes, directs the compiler to search for the file in a directory containing the standard header information. In UNIX, this is often somewhere like /user/include. Furthermore, it may be necessary when loading the program to specify the library explicitly. For example, on the PDP-11 UNIX system, the command to compile a program would be cc source files, etc. -ls, capital S, where -l capital S indicates loading from the standard library. Section 7.2, Standard Input and Output. Getchar and putchar. The simplest input mechanism is to read a character at a time from the standard input, generally the user's terminal or keyboard, with getchar. Getchar returns the next input character each time it's called. In most environments that support C, a file may be substituted for the terminal by using the less than convention. If a program, prog, uses getchar, then the command line prog less than infile causes prog to read infile instead of the terminal or keyboard. The switching of input is done in such a way that prog is oblivious to the change. In particular, the string less than infile is not included in the command line arguments in argv. The input switching is also invisible if the input comes from another program via a pipe mechanism. The command line, other prog, vertical bar prog, runs two programs, other prog and prog, and arranges for the standard input for prog to come from the standard output of other prog. Getchar returns the value EOF when it encounters end of file on whatever input is being read. The standard library defines the symbolic EOF constant to be -1, with a #define in the file stdio.h. But text should be written in terms of EOF, not -1, so as to be independent of the specific value. For output, putchar, open paren C, close paren, puts the character C on the standard output, which is also by default the terminal or screen. The output can be directed to a file by using greater than. If prog uses putchar, prog greater than outfile will write the standard output onto outfile instead of the terminal. On the UNIX system, a pipe can also be used. Prog, vertical bar, another prog, puts the standard output of prog into the standard input of other prog. Again, prog is not aware of the redirection. Output produced by printf also finds its way to the standard output, and calls to putchar and printf may be interleaved. A surprising number of programs read only one input stream and write only one output stream. For such programs, I/O with getchar, putchar, and printf may be entirely adequate and is certainly enough to get started. This is particularly true given file redirection in a pipe file for connecting the output of one program to the input of the next. For example, consider the program lower, which maps its input to lowercase. This is an example on page 145 of the textbook that you can see at www.cc4e.com/code. #include stdio.h, #include ctype.h, main open paren close paren, open curly brace, int c, while open paren c equals getchar open paren close paren not equal to EOF close paren. Putchar is upper open paren c close paren question mark 2 lower, open paren C, close paren, colon, C, close paren, semicolon, close curly brace. The functions is upper and 2 lower are actually macros defined in ctype.h. The macro is upper tests whether its argument is an uppercase letter, returning non-zero if it is and 0 if it's not. The macro 2 lower converts an uppercase to lowercase letter. Regardless of how these functions are implemented on a particular machine, their external behavior is the same. So programs that use them are shielded from the knowledge of their character set. To convert multiple files, you can use a program like the UNIX cat to collect files. Cat, file1, file2, ... vertical bar, lower, greater than, output, and thus avoid learning how to access files from a program. The cat example is presented later as example code in this chapter. As an aside, the standard I/O library functions getChar and putChar can actually be macros and thus avoid the overhead of a function call per character. We'll show how this is done in Chapter 8. Section 7.3, Formatted Output, printf. The two routines printf for output and scanf for input, which we describe in the next section, permit translation to and from character representations of numerical quantities. They also allow generation or interpretation of formatted lines. We've used printf informally throughout the previous chapters. Here is a more complete and precise description. Printf, open paren, control, arg1, carg2, etc., close paren. Printf converts, formats, and prints its arguments on the standard output under the control of the string control. The control string contains two types of objects, ordinary characters, which are simply copied to the output stream, and conversion specifications, each of which causes conversion and printing of the next successive argument to printf. Each conversion specification is introduced by the character % sign and ended by a conversion character. Between the % and the conversion character, there may be a minus sign, which specifies left adjustment of the converted argument in its field. A digit string specified a minimum field width. The converted number will be printed in a field at least this wide and wider if necessary. If the converted argument has fewer characters than the field, it will be padded on the left or right if the left adjustment indicator has been given to make up the field width. The padding character is normally blank in 0 if the field width is specified with a leading 0. This 0 does not imply an octal field width. A period, which separates the field width from the next digit string. A digit string that specifies the precision, which specifies the maximum number of characters to be printed from a string or the number of digits to be printed to the right of the decimal point of a float or a double. A length modifier, the letter L, which indicates that the corresponding data item is a long rather than an int. The conversion characters and their meanings are D, the argument is converted to decimal notation. O, the argument is converted to unsigned octal notation without a leading 0. X, the argument is converted to unsigned hexadecimal notation without a leading 0x. U, the argument is converted to unsigned decimal notation. C, the argument is taken to be a single character. S, the argument is a string. Characters from the string are printed until a null character is reached or the number of characters indicated by the precision specification is exhausted. E, the argument is taken to be a float or a double and converted to decimal notation of the form optional minus sign m.nnn capital E plus or minus xx, where the length of the string of the ends is specified by the precision. The default precision is 6. F, the argument is taken to be a float or double and converted to decimal notation of the form optional minus sign mmm dot nnnnn, where the length of the string of ends is specified by precision. The default precision is 6. Note that the precision does not determine the number of significant digits printed in the F format. G says use %E or %F, whichever is shorter, and non-significant zeros are not printed. If the character after the % is not a conversion character, the character is simply printed. Thus, % may be printed as %%. Most of the format conversions are obvious and have been illustrated in the earlier chapter. One exception is the precision field as it relates to strings. The following table shows the effect of a variety of specifications in printing hello, world, which is 12 characters. We put colons around each field so you can see its actual width. %10s : hello world : It's 12 characters long, and so we get 12 characters printed because we haven't really told it to strictly limit that. %-10s : hello, world : no extra spaces. Again, 12 characters are used, even though we said 10, it expands it to 12. And the fact that it's left justified, seems we're printing more than the width of the field, doesn't make any difference. %20s : 8 spaces, then hello, world : 8 spaces are put in on the left because it by default is right justified. %-20s : prints : hello, world, and then 8 spaces, and then :. We've told it to left justify, so the 8 spaces are added to fill it out to 20 spaces after hello world. %20.10s : gives us : and then 10 blanks, and then hello, WOR : Now in this case, we've told it we really only want 10 characters from the string, and so the LD is truncated. %-20.10s : hello, WOR, and then 10 spaces, and it's left justified, so the 10 spaces are at the end, right before the colon. %.10s : hello, WOR : So now the overall field that's printed is exactly 10 characters, and it is the leftmost 10 characters. Warning: printf uses its first argument to decide how many arguments follow and what their types are. It will get confused, and you will get nonsense answers if there are not enough arguments, or they are of the wrong type. As an aside, formatted output is difficult. The design of cprintf was inspired by the earlier format statement in Fortran and Alcol. In order to compete with those languages, C needed to ship with solid support for formatted output. The approach chosen by C percolated into C-like languages. PHP and Java simply have a function called printf that mimics most of the C formats. Python has evolved its approach to formatted output over the years. An early initial solution had a syntax that used % to provide C-like formatting. There was also a format method on the string object. For example, x equals 421.34. Print, open paren, double quote, x is %7.2f, double quote, %, open paren, x, comma, close paren, close paren. That uses the % operator and sends a tuple, but the syntax of %7.2f is the same. Another option is print, open paren, double quote, x is, open curly brace, y, colon, 7.2f, close curly brace, double quote, dot, format, open paren, y equals x, close paren, close paren. This sends a set of key value pairs, and it's a little clunky. The latest and least clunky way to do it in modern Python is what we call f-strings. And the code is print f, double quote, print, open paren, f, double quote, x is, open curly brace, x, colon, 7.2f, close curly brace, double quote, close paren. But even after all this evolution, much of this output formatting still traces its design inspiration from the C printf capabilities back in 1978. Formatted input, scanf. The function scanf is the input analog of printf, providing many of the same conversion facilities, but in the opposite direction. Scanf, open paren control, arg1, arg2, etc., close paren. Scanf reads characters from standard input interprets them according to the format specified in control, and stores the results in the remaining arguments. The control argument is described below. The other arguments, each of which must be a pointer, indicate where the corresponding converted input should be stored. The control string usually contains conversion specifications, which are used to direct interpretation of input sequences. The control string may contain blanks, tabs, or new lines, we call these whitespace characters, which are ignored, ordinary characters, not %, which are expected to match the next non-white space character of the input stream, conversion specifications consisting of the character %, an optional assignment suppression character asterisk, and an optional number specifying the maximum field width, and a conversion character. A conversion specification directs the conversion of the next input field. Normally, the result is placed in the variable pointed to by the corresponding argument. If assignment suppression is indicated by the asterisk character, however, the input field is parsed but then simply skipped. No assignment is being made. An input field is defined as a string of non-whitespace characters. It extends to either the next whitespace character or until the field width, if specified, is exhausted. This implies that scanf will read across line boundaries to find its input, since new lines are whitespace. The conversion character indicates the interpretation of the input field. The corresponding argument must be a pointer, as required by the call-by-value semantics of C. The following conversion characters are legal. D. A decimal integer is expected on input. The corresponding argument should be an integer pointer. O. An octal integer, with or without a leading 0, is expected on input. The corresponding argument should be an integer pointer. X. A hexadecimal integer, with or without the leading 0x, is expected in the input. The corresponding argument should be an integer pointer. H. A short integer is expected in the input. The corresponding argument should be a pointer to a short integer. C. A single character is expected. The corresponding argument should be a character pointer. The next input character is placed at the indicated spot. The normal skip over whitespace characters is suppressed in this case. To read the next non-whitespace character, use %1s. S. A character string is expected. The corresponding argument should be a character pointer pointing to an array of characters large enough to accept the string and a terminating \0, which will be added. F. A floating point number is expected. The corresponding argument should be a pointer to a float. The conversion character E is a synonym for F. The input formats for floats is an optional sign, a string of numbers possibly containing a decimal point, and an optional exponent field containing an upper or lowercase e, followed by possibly a signed integer. The conversion characters D, O, and X may be preceded by L, the letter L, to indicate that a pointer to a long rather than int appears in the argument list. Similarly, the conversion characters E or F may be preceded by the letter L to indicate that it's a pointer to a double rather than a float in the argument list. For example, the call int I, float x, char, name, open square bracket 50, close square bracket, semicolon. Scanf, open parenthesis, double quote, %d space %f space %s, double quote, comma, %I, comma, %x, comma, name, close paren, semicolon, with the input line 25 space 54.32e-1 space Thompson. We'll assign the value 25 to I, the value 5.432 to x, and the string Thompson properly terminated with a \0 to name. The three input fields may be separated by as many blanks, tabs, and new lines as desired. The call int I semicolon, float x semicolon, char name open square bracket 50, close square bracket semicolon, scanf, double quote, %2d space %f space %*d space %2s, double quote, comma, %I, comma, %x, comma, name, close parenthesis, with input 56789 space 0123 space 45A72 will assign 56 to I, 789.0 to X, skip over 0, 1, 2, 3, and place the string 45 in name. The next call to any input routine will begin searching at the letter A. In these two examples, name is a pointer and thus must not be preceded by an ampersand. As another example, the rudimentary calculator of Chapter 4 can now be written with scanf to do the input conversion. This is example code on page 150 of the textbook, which you can see at www.cc4e.com/code. Pound include stdio.h, main, open paren, close paren, open curly brace, double, sum, comma, v, semicolon, sum equals 0. While, open paren, scanf, open paren, double quote, %lf, double quote, comma, ampersand v, close parenthesis, not equal EOF, close parenthesis, printf, open parenthesis, double quote, \t, %.2f, \n, double quote, comma, sum plus equals v, close parenthesis, semicolon, close curly brace. Scanf stops when it exhausts its control string or when some input fails to match the control specification. It returns as its function residual value the number of successfully matched and assigned input items. This can be used to decide how many input items were found. On end of file, EOF is returned. Note that this is different from 0, which means that the next input character does not match the first specification in the control string. The next call to scanf resumes searching immediately after the last character already returned. A final warning. The arguments to scanf must be pointers. By far, the most common error is writing scanf, open paren, double quote, %d, comma, n, close paren, semicolon, instead of scanf, open paren, double quote, %d, double quote, comma, ampersand, n, close paren, semicolon. Section 7.5, in-memory format conversion. The functions scanf and printf have siblings called scanf and sprintf, which perform the corresponding conversion but operate on a string instead of a file. The general format is sprintf, open paren, string, comma, control, comma, arg1, comma, arg2, ... close paren, scanf, open paren, string, comma, control, comma, arg1, comma, arg2, etc., close paren. Sprintf formats the arguments in arg1, arg2, etc. according to control as before, but it places the result in a string instead of on the standard output. Of course, string had better be big enough to receive the result. As an example, if the name is a character array and n is an integer, then sprintf, open paren, name, comma, double quote, temp, %d, double quote, comma, n, close paren, semicolon, creates a string of the form temp nnn, where in name, where nnn is the value for n. scanf does the reverse conversion. It scans the string according to the format in control and places the results in arg1, arg2, etc. These arguments must be pointer. The call scanf, open paren, name, comma, double quote, temp, %d, double quote, comma, ampersand n, close parenthesis, semicolon, sets n to the value of the digits following temp in name. Section 7.6, File Access. As an aside, the next two sections do a nice job of covering file input and the notion of the standard error with simple sample code. But the authors are also making a subtle point about UNIX and how the design of C makes it easy to build UNIX utilities. By the end of section 7.6, we see a 29-line program that is pretty much a complete implementation of the core functionality of the UNIX cat command. Part of the philosophy of UNIX was to build commands that are each simple building blocks that can be composed using standard input, standard output, redirection, as well as pipes. These next two sections are a gentle celebration of the design principles that underlie the UNIX operating system. Also, while we're talking about the linkage between C and UNIX, there is a UNIX-related Easter egg earlier in the chapter. See if you can find it. Bonus points if you already noticed it. The programs written so far have all read the standard input and written the standard output, which we have assumed are magically predefined for a program by the local operating system. The next step in I/O is to write a program that accesses a file which is not already connected to the program. One program that clearly illustrates the need for such operations is cat, which concatenates a set of name files onto standard output. Cat is used for printing files on a terminal and is a general-purpose input collector for programs which do not have the capability of accessing files by name. For example, the command cat x.c y.c prints the contents of the files x.c and y.c on the standard output. The question is how to arrange for the named files to be read, that is, how to connect the external names that the user thinks of to the statements which actually read the data. The rules are simple. Before it can be read or written, a file has to be opened by the standard library function fopen. Fopen takes an external name like x.c or y.c, does some housekeeping and negotiating with the operating system, some details of which do not need to concern us, and returns an internal name which then must be used for subsequent reads or writes of the file. The internal name is actually a pointer, called the file pointer, to a structure which contains information about the file, such as the location of a buffer, the current character position in the buffer, whether the file is being read or written, and similar. Users don't need to know the details because part of the standard I/O definitions are obtained from stdio.h, and it's a structured definition called file. The only declaration needed for a file pointer is exemplified by file $fopen, open paren, close paren, comma, $fp, semicolon. That says that fp is a pointer to a file, and fopen returns a pointer to a file. Note that file is a type name, like int, not a structure tag. It's implemented as a type def. Details on how all this works on the UNIX system are given in Chapter 8. The actual call to fopen in a program is fp equals fopen, open paren, name, comma, mode, close paren, semicolon. The first argument of fopen is the name of the file as a character string. The second argument is the mode, also a character string, which indicates how one intends to use the files. Allowable modes are read, R, write, W, or append, A. If you open a file which does not exist for writing or appending, it is created if possible. Opening an existing file for writing causes the old contents to be discarded. Trying to read a file that does not exist is an error, and there may be other causes of error as well, like trying to read a file when you don't have permission. If there is any error, fopen will return the null pointer with a value of null, which for convenience is also defined in stdio.h. The next thing needed is a way to read or write the file once it is open. There are several possibilities, of which getC and putC are the simplest. getC returns the next character from a file. It needs the file pointer to tell what file. Thus, C equals getC, open paren, fp, close paren, places in C the next character from the file referenced by fp and EOF when it reaches end of file. PutC is the inverse of getC. PutC, open paren, C, comma, fp, close paren, puts the character C on the file fp and returns C. Like getchar and putchar, getC and putC may be macros instead of functions. When a program is started, 3 files are automatically opened and file pointers are provided for them. These files are the standard input, the standard output, and the standard error output. The corresponding file pointers are called stdin, stdiout, and stderr. Normally, these are all connected to the terminal, but stdin and stdout may be redirected to files or pipes as described in section 7.2. Getchar and putchar can be defined in terms of getC, putC, stdin, and stdout as follows. Pound define getchar, open paren, close paren, getC, open paren, stdin, close paren, pound define putchar, open paren, C, close paren, putC, open paren, C, comma, stdout, close paren. For formatted input or output files, the function fscanf and fprintf may be used. These are identical to scanf and printf. Save that the first argument is a file pointer that specifies the file to be read or written. The second string is the second argument is the control string. With these preliminaries out of the way, we are now in a position to write the program cat to concatenate files. The basic design is one that has been found convenient for many programs. If there are command-line arguments, they are processed in order. If there are no arguments, the standard input is processed. This way, the program can be used standalone or part of a larger process. This example is on page 153 of the textbook, and you can see it at www.cc4e.com/code. Pound include stdio.h. Main, open paren, argc, argv, close paren. Int argc semicolon. Char star argv, open square bracket, close square bracket, semicolon. Open curly brace. File, star fp, star f open paren, close paren, semicolon. If open paren argc double equals 1, close paren, there's no arguments, so we're going to copy the standard input. File copy, open paren stdin, close paren, semicolon. Else, while, open paren --argc greater than 0, close paren. If, open paren fp equals f open paren star plus argv, quote r quote, close paren, double equals null, close paren, open curly brace. Print f, open paren, double quote, cat, can't open, space, %s, \n, double quote, star argv, close paren, semicolon. Break, semicolon. Close curly brace, else, open curly brace, file copy, open paren fp, close paren, semicolon, f close, open paren fp, close paren, semicolon, close curly brace for the if then else, and then close curly brace for the main. And now we have the file copy function. We're going to read all the contents of a file pointer and send it to standard output. File copy, open paren fp, close paren, file star fp, semicolon, open curly brace, int c, semicolon, while open paren c equals get c, open paren fp, close paren, not equal eof, close paren, put c, open paren c, stdout, close paren, semicolon, close curly brace. The file pointers stdin and stdout are predefined in the IO library as the standard input and the standard output. They may be used anywhere an object of type file star can be. They are constants, however, not variables, so don't try to assign to them. The function fclose is the inverse of fopen. It breaks the connection between the file pointer and the external name that was established by fopen, freeing the file pointer for another file. Since most operating systems have some limit on the number of simultaneously open files a program may have, it's a good idea to free things when they're no longer needed, as we did above in cat. There's also another reason for fclose on an output file. It flushes the buffer in which put C is collecting output. Fclose is called automatically for each open file when a program terminates normally. Section 7.7, Error Handling, stderr, and exit. The treatment of errors in the previous implementation of cat is not ideal. The trouble is that if one of the files can't be accessed for some reason, the diagnostic is printed at the end of the concatenated output. That is acceptable if the output's going to a terminal, but it's really bad if it's going to a file or some other program via pipeline. To handle this situation better, a second output file called stderr is assigned to the program in the same way that stdin and stdout are. If at all possible, output written on stderr appears on the user's terminal, even if the standard output is redirected. Let's revise cat to write its error messages onto the standard output file. This is really only a couple of lines of code different between the example on page 153. This is the example on page 154 of the textbook, which of course you can see at www.cc4e.com/code. pound include stdio.h, pound include stdlib.h, main, open paren, argc, comma, argv, close paren, int argc, semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace, file, star fp, comma, star f open paren, close paren, semicolon. If, open paren, argc double equal 1, close paren, here we have no arguments, file copy, open paren, stdin, close paren, semicolon, else, while, open paren, minus minus argc greater than 0, close paren, if, open paren, fp equals fopen, open paren, star plus plus argv, comma, double quote r, double quote, close paren, double equal null, close paren, open curly brace, fprintf, open paren, stderr, comma, double quote, cat colon, can't open %s backslash n, double quote, comma, star argv, close paren, semicolon. Exit, open paren, 1, close paren, semicolon. Close curly brace, else, open curly brace. File copy, open paren, fp, close paren, semicolon. File close, open paren, fp, close paren, semicolon. Close curly brace to finish the if, and then exit, open paren, 0, close paren, semicolon, close curly brace to finish the main. And file copy is the same from the previous. So this program signals errors two ways. The diagnostic output produced by fprintf goes to stderr, so it finds its way to the user's terminal instead of disappearing down a pipeline or into an output file. The program also uses the standard library function exit, which terminates execution when it's called. The argument of exit is available to whatever process called this one, so the success or failure of the program can be tested by another program that uses this one as a subprocess. By convention, a return value of 0 signals all is well, and various non-zero values signal abnormal situations. Exit calls fclose for each open output file to flush any buffered output, then calls a routine named _exit. The function _exit causes immediate termination without any buffer flushing. Of course, it may be called directly if desired. Section 7.8, line input and output. The standard library provides a routine fgetS, which is quite similar to the getLine function we've used throughout the book. The call fgetS, open paren, line, comma, max line, comma, fp, close paren, reads the next input line, including the new line, from the file fp into the character array line. At most, max line minus 1 characters will be read. The resulting line is terminated with \0. Normally, fgetS returns line. On end of file, it returns null. Our getLine returns line length and 0 for end of file. For the output, the function fputS writes a string, which need not contain a new line, to a file. fputS, open paren, line, comma, fp, close paren. To show there's nothing magic about the functions like fgetS and fputS, here they are, copied directly from the UNIX standard I/O library. This code example is on page 155 of the textbook, which you can view at www.cc4e.com/code. Char star fgetS, open paren, s, comma, n, comma, iop, close paren, char star s, semicolon, int n, semicolon, register file star iop, semicolon, open curly brace, register int c, semicolon, register char star cs, semicolon, cs equals s, semicolon, while open paren minus minus n greater than 0, double ampersand, open paren c equals get c, open paren iop, close paren, not equal eof, close paren, if open paren star cs plus plus equals c, close paren, equal, quote, \n, quote, close paren, break, semicolon. Star cs equals, quote, \0, quote, semicolon. Return, open paren, c double equals eof, and cs double equals s, close paren, question mark, null, colon, s, close paren, semicolon, close curly brace. The function f put s is as follows. F put s, open paren s, comma, IOP, close paren, register char star s, register file star IOP, semicolon, open curly brace, register int c, semicolon, while, open paren, c equals star s plus plus, close paren, put c, open paren, c, comma, IOP, close paren, semicolon, close curly brace. Section 7.9, some miscellaneous functions. The standard library provides a variety of functions, a few which stand out as especially useful. We've already mentioned the string functions, strlen, strcpy, strcat, and strcomp. Here are some others. Character class testing and conversion. Several macros perform character tests and conversions. The function isAlpha, open paren c, close paren, returns non-zero if c is alphabetic, 0 if not. The function isUpper, open paren c, close paren, returns non-zero if c is uppercase, 0 if not. IsLower, open paren c, close paren, is non-zero if c is lowercase, 0 if not. IsDigit, open paren c, close paren, is non-zero if c is a digit, 0 if not. IsSpace, open paren c, close paren, is non-zero if c is blank, tab, or new line, 0 if not. ToUpper, open paren c, close paren, convert c to uppercase. ToLower, open paren c, close paren, convert c to lowercase. Those all worked on single characters. UngetC. The standard library provides a rather restricted version of the function ungetch, which we wrote in Chapter 4. It's called ungetC. UngetC, open paren, c, comma, fp, close paren, pushes the character c back onto the file fp. Only one character of pushback is allowed per file. UngetC may be used with any of the input functions in macros like scanf, getC, or getchar. System call. The function system, open paren, s, close paren, executes the command in the character string s, then resumes the execution of the current program. The contents of S depend strongly on the local operating system. As a trivial example, on UNIX, the line system, open paren, double quote, date, double quote, close paren, semicolon, causes the date program to be run. It prints the time and date of the day on UNIX. Storage management. The function calloc is rather like the alloc we have used in previous chapters. Calloc, open paren n, comma, size of, open paren object, close paren, returns a pointer to enough space for n objects of the specified size, or null if the request cannot be satisfied. The storage is initialized to 0. The pointer has the proper alignment for the object in question, but it should be cast to the appropriate type, as in char star calloc, open paren, close paren, semicolon, int star ip, semicolon, IP equals open paren int star close paren calloc open paren n comma size of open paren int close paren semicolon. Free open paren p close paren free space pointed to by p, where p is originally obtained by a call to calloc. There are no restrictions on the order in which space is freed, but it is a ghastly error to free something not obtained by calling calloc. Chapter 8 shows the implementation of a storage allocator like calloc, in which the allocated blocks may be freed in any order. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Chapter 8, the UNIX System Interface. The material in this chapter is concerned with the interface between C programs and the UNIX operating system. Since most C programs are on UNIX systems, this should be helpful to a majority of the readers. Even if you use C on a different machine, however, you should be able to glean more insight into C programming from studying these examples. This chapter is divided into 3 major areas: input-output, file system, and a storage allocator. The first 2 parts assume a modest familiarity with the external characteristics of UNIX. Chapter 7 was concerned with a system interface that is uniform across a variety of operating systems. On any particular system, the routines of the standard library have to be written in terms of the I/O facilities that are actually available on the host system. In the next few sections, we'll describe the basic system entry points for I/O on the UNIX operating system and illustrate how parts of the standard library can be implemented with them. As an aside, the dual nature of C and UNIX has been on display throughout the book. And while this chapter is called the UNIX System Interface, in a sense, it's less about UNIX itself and very much about why C is such a great programming language. Let me explain. Before Unix and C became the norm, operating systems and operating system utilities, those commands we used interactively and in batch jobs, were quite often written in the assembly language of the computer which it was supporting. Often, there were not well-documented API calls between utilities in assembly language and the assembly language which implemented the operating system. Smart vendor programmers would just look at the operating system code and write their utility code to work with it. This section shows that a language that has features like structures, arrays, pointers, a preprocessor, and unions was sufficiently rich so that we could document all the intricate interfaces with an operating system using a relatively high-level language, and then we could write our utility code, like cat, in a high-level language as well. In this chapter, the authors are almost shouting, "Quit using assembly language to build your operating system and utility code." Further, they are showing us examples designed to answer the question that might come from programmers used to the old ways, like, can we do X, Y, Z in C? The author's emphatic answer in the increasingly intricate code samples is, C is not a toy language that's only something used by a few AT&T computer scientists in a research lab. If you're doing serious system stuff that needs maximum performance and readability and reliability, use C. This chapter shows C in all its glory and shows why it was such an important language to enable the world of technology we have 40 years later. At the end of the chapter, we'll talk a little bit about C, how C enabled the creation of easier-to-use programming languages, and why it was so important to invent C-inspired languages like Python, PHP, and Java once C became the established systems programming language. Section 8.1, File Descriptors. In the Unix operating system, all input and output is done by reading or writing files, because all peripheral devices, even the user's terminal, are files in the file system. This means that a single homogeneous interface handles all communications between a program and peripheral devices. In the most general case, before reading or writing a file, it is necessary to inform the system of your intent to do so, a process called opening the file. If you're going to write on a file, it may also be necessary to create it. The system checks for your right to do so. Does the file exist? Do you have permission to access it? And if all is well, returns to the program a small positive integer called the file descriptor. Whenever I/O is to be done on the file descriptor is used instead of the name to identify the file. This is roughly analogous to the use of read open paren 5, and write open paren 6, in Fortran. All information about an open file is maintained by the system. The user refers to the file only by the file descriptor. Since input and output involving the user terminal is so common, Special arrangements exist to make this convenient. When the command interpreter, the shell, runs a program, it opens 3 files with files descriptors 0, 1, and 2 called the standard input, standard output, and standard error output. All of these are normally connected with a terminal, so if a program reads file descriptor 0 and writes to file descriptors 1 and 2, it can do terminal I/O without worrying about opening the files. The user of the program can redirect input-output to and from files with less than and greater than. For example, prog less than in file, greater than out file. In this case, the shell changes the default assignments for file descriptors 0 and 1 from the terminal to the named files. Normally, file descriptor 2 remains attached to the terminal, so error messages can go there. Similar observations hold if the input or output is associated with a pipe. In all cases, it must be noted that the file assignments are changed by the shell, not the program. The program does not know where its input comes from, nor where its output goes, so long as it uses file 0 for input and 1 and 2 for output. Section 8.2, Low-Level I/O, Read and Write. The lowest level of I/O in UNIX provides no buffering or any other services. It is, in fact, a direct entry into the operating system. All input and output is done by 2 functions called read and write. For both, the first argument is a file descriptor. The second argument is a buffer in your program where the data is to come from or go to. The third argument is the number of bytes to be transferred. The calls are nread equals read open paren fd, buff, n, close paren, semicolon. Nwritten equals write open paren fd, buff, n, close paren, semicolon. Each call returns a byte count, which is the number of bytes actually transferred. On reading, the number of bytes returned may be less than the number asked for. A return value of 0 bytes implies end of file, and -1 indicates an error of some sort. For writing, the return value is the actual number of bytes written. It is generally an error if this isn't equal to the supposed number that was asked to be written. The number of bytes to be read or written is quite arbitrary. The 2 most common values are 1, which means 1 character at a time, or unbuffered, and 512, which corresponds to the physical block size on many early peripheral devices. This latter size will be most efficient, but even a character at a time I/O is not inordinately expensive. Putting these facts together, we can write a simple program to copy its input to its output, the equivalent of the file copying program written for Chapter 1. In UNIX, this program will copy anything to anything, since input and output can be redirected to any file or device. This example is on page 161 of the textbook, which you can view at www.cc4e.com/code. Pound include standard stdio.h. Pound define buff size 512. This is the best size for PDP-11 UNIX. Modern computers, it probably should be larger. Main, open paren, close paren, open curly brace. Char, buff, open square bracket, buff size, close square bracket, semicolon. Int n, semicolon. While, open paren, n equals read, open paren, 0, buff size, close paren, greater than 0, close paren, write, open paren, 1, buff, n, close paren, semicolon, close curly brace. If the file size is not an exact multiple of buff size, some read will return a smaller number of bytes to be written by write. The next call after that read will return 0. It is instructive to see how read and write can be used to construct higher level routines like getChar and putChar. For example, here is a version of getChar which does unbuffered input. This is the second example on page 162 of the textbook. Pound include stdio.h. Pound define cmask 0377. And this is a mask, an octal mask, to make sure characters are greater than 0. GetChar, open paren, close paren, open curly brace. Char, C, semicolon. Return, open paren, read, open paren 0, comma, ampersand C, comma 1, close paren, greater than 0, close paren, question mark, C, ampersand C mask, colon, EOF, semicolon, close curly brace. C must be declared char because read accepts a character pointer. The character being returned must be masked with 0377 to ensure that it's positive. Otherwise, sign extension might make it negative. The constant 0377 is appropriate for ASCII and the PDP-11, but not necessarily for every other machine. The second version of getChar does its input in big chunks and hands out the characters one at a time. This is the first example on page 162 of the textbook, which you can see at www.cc4e.com/code. Pound include stdio.h. Pound define CMask 0377. Pound define buff size 512. Now we do the buffered version of getChar. getChar, open paren, close paren, open curly brace. Static char buff, open square bracket, buff size, close square bracket. Static char star buff, p equals buff, semicolon. Static int n equals 0, semicolon. Those variables are static so that they are long-lived and exist from call to call. The beginning of the code. If open paren n double equals 0, close paren, open curly brace, n equals read, open paren 0, comma, buff size, close paren, semicolon, buff p equals buff, semicolon, close curly brace. Return, open paren, minus n greater than equal to 0, close paren, question mark, star buff p plus plus, ampersand C mask, colon, EOF, close paren, semicolon, close curly brace. Section 8.3, open, create, close, unlink. Create is not create, it's create without the E, so I'll just call it create for now. Other than the default standard input and output and error files, you must explicitly open files in order to read or write them. There are two system entry points for this, open and create. Open is rather like the fopen discussed in Chapter 7, except that instead of returning a file pointer, it returns a file descriptor, which is just an int. Int fd semicolon, fd equals open paren, name, comma, rw mode, close paren, semicolon. As with fopen, the name argument is a character string corresponding to the external file name. The access mode argument is different, however. RW mode is 0 for read, 1 for write, and 2 for read-write access. Open returns -1 if any error occurs, otherwise it returns a valid file descriptor. It is an error to open a file that does not exist. The entry point create is provided to create new files or to rewrite old ones. fd equals create, open paren, name, comma, pmode, close paren, semicolon. Returns a file descriptor if it was able to create the file name, and -1 if not. If the file already exists, create will truncate it to 0 length. It is not an error to create a file that already exists. If the file is brand new, create creates it with the protection mode specified in the pmode argument. In the UNIX file system, there are 9 bits of protection information associated with each file, controlling read, write, and execute permission for the owner of the file, for the owner's group, and for all others. Thus, a 3-digit octal number is the most convenient format for specifying permissions. For example, 0755 specifies read, write, and execute permission for the owner, and read and execute permission for group and for everyone else. To illustrate here, a simplified version of the UNIX utility CP, a program that copies one file to another. The main simplification is that our version only copies one file and does not permit the second argument to be a directory. And this example code is on page 163 of the textbook, which you can see at www.cc4e.com/code. Pound include stdio.h, pound include stdlib.h, pound define buff size 512, pound define pmode 0644, RW, read and write for owner, read for group, and others. Int, open paren, argc, argv, close paren. The format will be, we're going to have two files, copy file 1, file 2. Int, argc, semicolon, char, star, argv, open square bracket, close square bracket, semicolon, open curly brace. Int, f1, f2, n, semicolon, char, buff size, semicolon. If, open paren, argc, not equal to 3, close paren, error, open paren, double quote, usage, cp, from 2, double quote, null, close paren, semicolon. If, open paren, f1 equals open paren, argv sub 1, 0, close paren, equal, minus 1, close paren, error, open paren, double quote, cp, can't open, %s, double quote, argv sub 1, close paren, semicolon. If, open paren, f2 equals creat, open paren, argv sub 2, p mode, close paren, equal, minus 1, close paren, error, open paren, quote, cp, can't create, %s, double quote, argv sub 2, close paren, semicolon. While, open paren, n equals read, open paren, f1, buff size, close paren, greater than 0, close paren. If, open paren, write, open paren, f2, buff, n, close paren, not equal, n, close paren, error, open paren, double quote, cp, write error, double quote, null, close paren, semicolon, exit, open paren, 0, close paren, semicolon, close curly brace. That's the end of the main program. The error routine is going to print the error message. Error, open paren, s1, s2, close paren, char, star, s1, star, s2, semicolon, open paren, printf, open paren, s1, s2, close paren, semicolon, printf, double quote, \n, double quote, close paren, semicolon, exit, open paren, 1, close paren, semicolon, close curly brace. There is a limit on the number of files which the program may have open simultaneously. Accordingly, any program which intends to process many files must be prepared to reuse file descriptors. The routine close breaks the connection between a file descriptor and an open file, and frees the file descriptor for use with some other file. Termination of a program via exit or return from the main program closes all open files. The function unlink open paren file name close paren removes the file name from the file system. Section 8.4 Random Access Seek and LSeek. File I/O is normally sequential. Each read or write takes place at a position in the file right after the previous one. When necessary, however, a file can be read or written in any arbitrary order. The system call LSeek provides a way to move around in a file without actually reading or writing. LSeek, open paren, fd, offset, origin, close paren, semicolon, forces the current position in the file, whose descriptor is fd, to move to the position offset, which is taken relative to the location specified by origin. Subsequent reading or writing will begin at that position. Offset is a long, fd and origin are ints. Origin can be 0, 1, or 2 to specify that the offset is to be measured from the beginning, from current position, or from the end of file respectively. For example, to append to a file, seek to the end before writing. LSeek, open paren, ft, 0l, 2, close paren, semicolon. To get back to the beginning, i.e. rewind to the beginning, LSeek, open paren, fd, 0l, 0, parenthesis, semicolon. Note that the 0l argument could also be written as open paren, long, close paren, 0. With LSeek, it's possible to treat files more or less like large arrays at the price of slower access. For example, the following simple function reads any number of bytes from any arbitrary place in a file. Get, open paren, fd, pos, comma buff, comma n, close paren. Int fd, comma n, long, pause, semicolon, char, star buff, semicolon, open curly brace. lseek, open parenthesis, fd, comma pause, comma 0, close paren, semicolon. Return, open paren, read, open paren, fd, comma buff, comma n, close paren, semicolon, close curly brace. In pre-version 7 UNIX, the basic entry point to the I/O system is called seek. Seek is identical to lseek, except that its offset argument is an int rather than a long. Accordingly, since PDP-11 integers only have 16 bits, the offset specified for seek is limited to 65,535. For this reason, origin values of 3, 4, and 5 cause seek to multiply the given offset by 512, which is the number of bytes in one physical block on a PDP-11, and then interpret origin as if it were 0, 1, or 2 respectively. Thus, to get to an arbitrary place in a large file requires two seeks. The first one selects the block, then one which has origin equal to 1, and then moves to the desired byte within the block. Once again, we see C and Unix straddling a major improvement in computer hardware in 1978. The natural name for a function to randomly move around a file would be seek. But in early versions of Unix, seek took an integer as the offset, but on small word computers like PDP-11 have an integer that can't represent a large number, so seek used a complex set of rules to handle larger files. The only logical thing was to have the offset be a long, and then for upwards compatibility, make a new function called lseek that we use to this day. Section 8.5, an example implementation of fopen and getC. Let us illustrate how some of these pieces fit together by showing an implementation of the standard library routines fopen and getC on the PDP-11. Recall that files in the standard library are described by file pointers rather than file descriptors. A file pointer is a pointer to a structure that contains several pieces of information about the file. A pointer to a buffer, so the file can read in large chunks, count of the number of characters left in the buffer, a pointer to the next character position in the buffer, and some flags describing read-write mode and the file descriptor. The data structure that describes a file is contained in the file stdio.h, which must be included by #include in any source file that uses routines from the standard library. It is also included by functions in that library. In the following excerpt from the PDP-11 stdio.h, names which were intended for use only by functions of the library begin with underscore, so they are less likely to collide with the names of the user program. As a side note, I won't read the underscores because they confuse your understanding. So the underscores are there in the code. You can look at it online, but I'm not going to read the underscores. So this is basically some definitions for stdio.h. Define buff size 512. Define end file 20. Type def struct IOBuff open curly brace char star ptr int cnt semicolon char star base semicolon int flag semicolon int fd semicolon close curly brace file semicolon extern file IOB open square bracket end file close square bracket semicolon define stdin open paren ampersand IOB sub 0 close paren define std out open paren ampersand IOB sub 1 close paren define std air open paren ampersand IOB sub 2 close paren define read 01 define write 02 define unbuff 04 define big buff 010 define EOF 020 define air 040 define null 0 define EOF open paren -1 close paren define getC open paren p close paren open paren minus open paren p close paren right arrow cnt greater than or equal to 0 question mark star open paren p close paren right arrow ptr plus plus ampersand 0377 colon fill buff open paren p close paren define get char open paren, close paren, get C, open paren, stdin, close paren, pound define put C, open paren x comma p, close paren, open paren, minus minus, open paren p, close paren, right arrow, cnt, greater than or equal to 0, question mark, star, open paren p, close paren, right arrow, ptr plus plus equals, open paren x, close paren, colon, flush buff, open paren x, close paren, comma, p, close paren, pound define, put char, open paren x, close paren, put c, open paren x, comma, std out, close paren. The get C macro normally just decrements the counts, advances the pointer, and returns the character. We do this in a very long define continued by a backslash. If the count goes negative, however, getC calls the function fillBuff to replenish the buffer, reinitialize the structure contents, and return a character. A function may present a portable interface, yet itself contain non-portable constructs. getC masks the character with 0377, which defeats the sign extension done by the PDP-11 and ensures that all characters will be positive. Although we will not discuss any details, we've included the definition of putC to show that it operates in much the same way as getC, calling a function flushBuff when its output buffer is full. The function fopen and fillBuff can now be written. Most of fopen is concerned with getting a file opened and positioned at the right place, and setting the flag bits to indicate the proper state. fopen does not allocate any buffer space. This is done by fillBuff when the file is first read. You can look at this sample code from page 167 at www.cc4e.com/code. I won't read it here because it's pretty long and intricate, so you'll have to go watch it online or view it online. Back to the text. The function fillBuff is rather more complicated. The main complexity lies in the fact that fillBuff attempts to permit access to the file even though there may not be enough memory to buffer the I/O. If the space for a new buffer cannot be obtained from calloc, all is well. If not, fillBuff does unbuffered I/O using a single character stored in a private array. The first call to getC for a particular file finds a count of 0, which forces a call of fillBuff. If fillBuff finds that the file is not open for reading, it returns EOF immediately. Otherwise, it tries to allocate a large buffer, and, failing that, a single character buffer, setting the buffering information in flag appropriately. Once the buffer is established, fillBuff simply calls read to fill it, and sets the count and pointers, and returns the character at the beginning of the buffer. Subsequent calls to fillBuff will find a buffer already allocated. The only remaining loose end is how everything gets started. The array IOB must be defined, initialized for stdin, stdout, and stderr. File IOB, open square bracket, end file, close square bracket, equals, open curly brace, null, comma, 0, comma, null, comma, underscore read, comma, 0, comma, close curly brace, comma, and that's the standard in. The next one is open curly brace, null, comma, 0, comma, null, comma, underscore right, comma, 1, comma, close curly brace, comma, and that's the standard out definition, the sub 1 position. And then the next one is open curly brace, null, comma, 0, comma, null, comma, underscore right, vertical bar, underscore unbuff, comma, 2, close paren, and that is the standard error entry. Close curly brace, semicolon. The initialization of the flag part of the structure shows that standard in is to be read, standard out is to be written, and standard error is to be written unbuffered. Section 8.6, example, listing directories. I would note that the sample code in section 8.6 shows how we can write applications like ls to interact with directories in a Unix file system. However, the code in this section is not portable to modern Unix systems, so we'll leave the code as it is in this section. It's a good idea to read the code and get an outline of how to work with directories on Unix. If you want to write code to handle directories, you'll need to consult more modern documentation. Given the complexity of the code in this section, we are not going to include it in the copy of this book in this particular medium. Similarly, section 8.7 example, a storage allocator consists of a lot of really complex code, and so we will leave that for you to see online at www.cc4e.com/book/chap08.md. Dynamic memory is hard. Modern languages like Python, Ruby, and Java give us high-level objects like strings, lists, and dictionaries. These structures automatically expand and contract and can be copied into a temporary variable, used, and then discarded. Modern languages depend on efficient memory allocation. A problem when dynamic memory is heavily used is a fragmentation of the free space. You can get to the point where you have plenty of memory, but each of the free memory areas is so small that you can't allocate a new memory block. When this happens, the runtime implementations of these systems run a step called garbage collection, where everything pauses and free areas are moved around to make sure that the free memory is in a few large contiguous areas rather than many small non-contiguous areas. Language developers have been improving garbage collection algorithms for the past 40 years, and there is still much work to do. Now that the authors have established all the reasons that make C the ideal portable systems programming language, which I heartily agree with, it's time to talk about where C comes up short as a general-purpose language for those of us not working on the source code to Linux. The most challenging aspect of C is the lack of dynamic structures that we can use without the need to carefully allocate, use without the regard to the length of dynamically allocated memory, and not worry about calling C-free every single time we call C-alloc. If a programmer without strong programming skills, a good understanding of a testing regimen, and a proper defensive programming attitude is let loose in C, they will invariably write poor code. Their C code will make poor use of resources, run the system out of memory, or produce code that is riddled with security holes and bugs that seem to randomly appear. A decade after C emerged and became popular, Guido van Rossum designed a language called Python. It was one of a number of languages that was built using C and added an object-oriented layer that greatly simplified writing programs that used dynamic memory and added guardrails so programmers did not unintentionally write dangerous or insecure code. The key value-add features that make Python more appropriate for general-purpose programming are the string object, list object, and dict object that handle all aspects of creating and using variables and collections of variables. The book has one footnote. UNIX is a trademark of Bell Laboratories. But, of course, there's more. Actually, the trademark for UNIX is no longer owned by AT&T. It is owned by the Open Group. But that is a story for another day. The UNIX story arc includes AT&T UNIX, Berkeley Software Distribution, which we call BSD, Sun Microsystems, Minix, Linux, the Open Software Foundation, UNIX International, and others. The short version of that story is that AT&T UNIX was poised to take over the world as an open source product long before the words open source were ever spoken. AT&T should have and could have defined open source and changed everything by the early 1980s, except for a few AT&T intellectual property lawyers. It took over a decade for computer science to pivot away from a nearly exclusive focus on C and AT&T UNIX. The Linux operating system was open source from its inception and became the standard bearer for Unix-like operating systems and continues to be the way most of us encounter, quote, Unix. It is almost certain that the computer that served this media to you runs Linux, but that is a story for another time. In 1978, Unix and C were in their glory days and showed the entire computer science field and technology industry the right way forward. From that point forward, hardware could evolve independently from software. With the systems programming language and operating systems patterns sorted, the previous 40 years have seen an amazing innovation in hardware capability and performance. This 1978 C programming book by Brian W. Kernighan and Dennis M. Ritchie was the big bang moment for modern computing and computer science. We owe them a debt of gratitude for making whatever we do today possible. If you have made it to the end of this chapter in this book, as your narrator, I would like to congratulate and thank you. It has been an honor to record and narrate a book of such historical significance for you. Cheers. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.